The universe is a vast and mysterious expanse, filled with wonders that have intrigued us for ages. Since the beginning of time, every star, planet, and galaxy holds clues to our origins and place in the cosmos. From the search for alien life to the secrets of starlight and space, the universe invites us to explore and discover layers of knowledge just waiting to be revealed. The origin of the universe has fascinated humans for centuries, leading to various theories that attempt to explain how it all began. The most widely accepted idea among scientists today is the Big Bang theory. This theory suggests that the universe started from an extremely hot and dense state about 13.8 billion years ago. It wasn't an explosion in the traditional sense, but rather a rapid expansion of space itself, creating all the matter and energy we see today. As the universe expanded, it began to cool. This cooling allowed particles to form, which eventually combined to create atoms, mainly hydrogen and helium. These gases coalesced due to gravity, leading to the birth of stars and galaxies. Over billions of years, these celestial bodies evolved, giving rise to the complex structures we now observe. The remnants of the early universe can still be detected today in the form of cosmic microwave background radiation, a faint glow that permeates the cosmos. Another intriguing perspective involves theories that go beyond the Big Bang. Some scientists explore the idea of a multiverse, where our universe is just one of many, each with its own unique set of physical laws and constants. This suggests that the Big Bang may not be a singular event, but part of a continuous cycle of expansions and contractions. Such theories challenge our traditional view of beginnings and endings, opening up fascinating possibilities about the nature of existence itself. Regardless of which theory resonates more, the quest to understand the origin of the universe is one of humanity's most profound journeys. Each theory invites us to ponder our place in the cosmos and the underlying principles that govern it, inspiring a sense of wonder as we explore the very fabric of reality. The universe is not just a collection of stars and planets. It is a dynamic tapestry, woven from the threads of time, space, and matter itself. The Big Bang theory is a cornerstone of modern cosmology and has dramatically reshaped our understanding of the universe's origins. It posits that approximately 13.8 billion years ago, the universe began as an extremely hot and dense point, which suddenly expanded. This expansion marks the beginning of all space and time, offering a framework for understanding how the universe has evolved since that momentous event. Before the acceptance of the Big Bang theory, various ideas existed about the universe's beginnings. Some folks envisioned an eternal and unchanging cosmos, while others proposed a static universe that fluctuated between expansion and contraction. However, observations of distant galaxies revealed that they are moving away from us, leading to the conclusion that the universe is expanding. This expansion, along with further discoveries such as cosmic background radiation, provided compelling evidence in favor of the Big Bang theory. One captivating feature of the Big Bang theory is its implication that the universe was once in a state of extreme energy. As space expanded and cooled, it created conditions that allowed for the formation of basic particles like protons and neutrons, which eventually led to the creation of atoms. This process set in motion the formation of stars and galaxies. The cosmic background radiation we detect today is a faint echo of that early hot state, a remnant that fills the universe and acts as a snapshot of its infancy. The Big Bang theory not only helps us understand how the universe began, but also has profound implications for its future. As scientists study how the universe continues to expand, they are piecing together the mysteries surrounding dark matter and dark energy, phenomena that still perplex us. This ongoing journey ignites curiosity about our place in the cosmos and the ultimate fate awaiting us, making the Big Bang more than just an origin story. It is a dynamic narrative that continues to unfold. Cosmic inflation is a theory that suggests our universe underwent a rapid expansion just after the Big Bang. This idea helps to explain some puzzling features of the universe today. One of the strongest pieces of evidence supporting inflation comes from observations of the cosmic microwave background radiation. This radiation is like a faint afterglow from the Big Bang, permeating our universe. When scientists analyzed this afterglow, they discovered it has tiny fluctuations or variations in temperature that match predictions made by inflationary models. These fluctuations are not merely random. They reveal a pattern that suggests the universe expanded incredibly quickly in its earliest moments. The uniformity of the temperature across vast regions of space points to inflation as well. Without such rapid expansion, areas of the universe should display greater differences in temperature, given that they would not have been in thermal contact prior to inflation. Instead, the microwave background shows a striking uniformity, which aligns beautifully with the theory. Another important aspect comes from the distribution of galaxies and large-scale structures in the universe. When we look at how galaxies cluster together, we notice they form a web-like structure. This can be traced back to the density fluctuations generated by inflation. These tiny deviations grew over time under the influence of gravity, leading to the formation of galaxies and clusters. This alignment between the theory and what we observe in the cosmos serves as a powerful testament to the validity of inflation. Lastly, advancements in technology and observation continue to strengthen the case for inflation. High-precision measurements from satellite missions like the Planck spacecraft have provided detailed maps of the cosmic microwave background. These observations reveal the subtle features that match the predictions of inflation, further solidifying its role in our universe's history. The combination of these pieces of evidence paints a compelling portrait of an early universe that expanded at an astonishing rate, shaping the cosmos we see today. In the grand tapestry of the universe, dark matter and dark energy hold crucial roles. Yet they remain elusive and mysterious. Dark matter, which makes up about 27% of the universe, acts like a cosmic glue. It is invisible and does not emit light or radiation, but its presence can be inferred through the gravitational effects it has on visible matter. It helps to hold galaxies together, ensuring they don't simply fly apart as they spin. Without dark matter, the structure of the universe would look very different, possibly chaotic and far less organized. On the other hand, dark energy, which constitutes around 73% of the universe, fuels the expansion of space itself. Unlike dark matter, which pulls things together, dark energy pushes galaxies apart. It is thought to be responsible for the acceleration in the universe's expansion observed since the late 20th century. This phenomenon has profound implications for the ultimate fate of the cosmos. Will it expand forever, drifting apart into a cold, sparse void, or will gravitational forces one day bring it back together? During the formation of the universe, known as the Big Bang, dark matter provided the scaffolding within which baryonic matter, the ordinary matter that makes up stars, planets, and living beings, could coalesce. As clouds of gas and dust fell into the gravitational wells created by dark matter, they collapsed to form galaxies, stars, and the intricate structures of the cosmos we see today. Thus, dark matter serves as the framework that allowed the visible universe to emerge and evolve. In contrast, dark energy complicates this story. As galaxies formed and evolved, dark energy began to dominate the landscape of the universe. Initially, the gravitational pull of dark matter was strong enough to slow down the expansion. However, as the universe aged, the repulsive force of dark energy took over, leading to the speeding up of acceleration. Thus, dark matter and dark energy are intertwined, shaping the cosmos in exquisite ways, influencing its past, and setting the stage for its future. The cosmic microwave background radiation, often abbreviated as CMB, holds a crucial place in our understanding of the universe. This faint glow permeates all of space and can be detected in every direction we look. It is a remnant of the early universe, specifically stemming from an event known as recombination, which occurred about 388,000 years after the Big Bang. At this time, the universe had cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms, allowing light to travel freely through space for the first time. The significance of the CMB lies in the information it carries about the early universe. By studying its subtle temperature fluctuations, scientists can gain insights into the density variations that preceded the formation of galaxies and larger structures. These fluctuations represent the earliest seeds of cosmic structures, informing our understanding of how matter clumped together over billions of years to create the universe we see today. The CMB acts like a snapshot of the infant universe, capturing conditions that have long since disappeared. Furthermore, the CMB has provided strong evidence for the Big Bang theory, shifting the paradigm of our understanding of cosmology. Measurements of its temperature and spectrum align remarkably well with predictions made by this theory, reinforcing our grasp of cosmic evolution. Researchers have meticulously analyzed this radiation, resulting in groundbreaking discoveries, including the expansion of the universe and the existence of dark energy. The study of the cosmic microwave background radiation continues to be a vibrant area of research, expanding our knowledge about the universe's origins and evolution. As technology advances and new instruments are developed, we can expect even deeper insights into this background radiation, unlocking mysteries that have persisted since the dawn of time. This small slice of the universe's history beckons us to explore further, inviting questions about the nature of everything around us. The universe is a vast and intricate tapestry, woven from countless galaxies, and its large-scale structures reveal fascinating patterns that shape our cosmic landscape. At the foundation of this structure lie galaxies. These immense collections of stars, gas, dust, and dark matter can contain millions or even trillions of individual stars. Galaxies are not scattered randomly. Instead, they form groups and clusters. Some of these clusters can house hundreds or thousands of galaxies, all interacting through the gravitational pull of their combined mass. As we step back to examine the universe at an even larger scale, we encounter superclusters. These are massive groups of galaxies and galaxy clusters stretched out across vast distances. For instance, the Laniakea supercluster, which includes our Milky Way, is an astonishing collection of over 100,000 galaxies. The distances between superclusters often exceed several hundred million light-years, highlighting both the sheer scale and the vast emptiness of the universe in between. An even more significant framework emerges when we look at the distribution of these superclusters. Scientists have discovered a structure known as the cosmic web, which features a network of filaments made of galaxies and dark matter. These filaments connect vast voids, regions of space that contain few, if any, galaxies. The formations of the cosmic web can be likened to bubbles, with the filaments representing the soap threads connecting them. This large-scale structure is shaped by gravity, influencing how matter clumps together over time. Understanding these colossal structures not only reveals the universe's current state, but also its past. The distribution of galaxies and their clusters tells us about the evolution of the cosmos, its expansion, and how matter has organized itself over billions of years. From the smallest galaxies to vast superclusters, each layer of structure adds another chapter to our story of the universe, captivating our imaginations and deepening our understanding of existence itself. Galaxies are colossal systems made up of stars, gas, dust, and dark matter, and their formation is a fascinating journey that dates back to the early universe. Shortly after the Big Bang, particles began to clump together due to gravity, leading to the formation of gas clouds. Over millions of years, these clouds collapsed under their own weight, igniting the process that creates stars. As these stars were born, they began to interact, merging and forming larger structures, eventually giving rise to the diverse galaxies we see today. The characteristics that define different types of galaxies, and there are 3 primary classifications, are largely determined by their shapes and star content. Spiral galaxies like our Milky Way feature distinct arms that spiral out from a central bulge and are rich in younger stars. They often contain abundant gas and dust, making them vibrant sites of ongoing star formation. The arms of these galaxies are where the magic happens, as new stars are birthed in stellar nurseries formed from collapsing gas clouds. On the other end of the spectrum are elliptical galaxies, which are generally more spherical or oval in shape. These galaxies tend to contain older stars and have much less gas and dust compared to spiral galaxies. As a result, they exhibit little new star formation, giving them a more subdued appearance. The lack of active star creation leads to a smooth, featureless look, reflecting the passage of time and the aging of the stars within them. Lastly, we have irregular galaxies. These lack the distinct shape of spiral or elliptical galaxies and often appear chaotic. Their irregularity can result from gravitational interactions with neighboring galaxies or from earlier mergers. They frequently contain large amounts of gas and dust and are rich in young, hot stars, making them lively yet complex entities in the grand tapestry of the universe. The diversity among galaxies not only highlights the various stages of cosmic evolution, but also beckons us to explore the mysteries of our astronomical backyard. The diversity among galaxies not only highlights the various stages of cosmic evolution, but also beckons us to explore the mysteries of our astronomical backyard. The universe is structured in an astonishingly intricate network known as the cosmic web. Within this cosmic tapestry, superclusters and vast voids play pivotal roles. Superclusters are enormous groupings of galaxies, often containing thousands of them, bound together by gravity. These colossal formations are the largest known structures in the universe, where galaxies group closely and interact in fascinating ways. Superclusters can span hundreds of millions of light-years, serving as the dense nodes of the cosmic web. In stark contrast to these filled regions are the voids, which are substantial areas that contain very few, if any, galaxies. These voids can stretch over tens of millions of light-years and comprise about 80% of the universe's volume. Instead of a bustling collection of stars, these vast spaces are mostly empty. Yet they are vital to the overall structure of the universe, acting as the spaces between the superclusters, creating a balance that defines the cosmic web. The interplay between superclusters and voids reflects not just the distribution of matter, but also the underlying forces that shape the cosmos. Superclusters evolve through gravitational attraction, where the massive amounts of matter pull galaxies towards them. On the other hand, voids emerge as the gravitational influence of matter causes the surrounding regions to attract more densely, leaving vast spaces largely devoid of galaxies. This dance of formation and emptiness hints at the history of the universe, showcasing how it has evolved over billions of years. Each supercluster and void contributes to the dynamic structure we observe today, providing critical insights into the behavior of dark matter, the mysteries of dark energy, and the very expansion of the universe itself. It's a reminder of how complex and beautiful the cosmos truly is, where every galaxy, cluster, and void tells a story etched in the fabric of space and time. The distribution of matter in the universe plays a crucial role in the cosmos's evolution. From the very moment of the Big Bang, matter began to coalesce into larger structures driven by gravity. This gravitational pull led to the formation of galaxies, clusters, and superclusters. Each piece of matter influenced the others, creating a complex web of cosmic architecture that has shaped the universe's past and continues to do so today. As matter began to clump together, regions of higher density attracted more matter, which in turn influenced the speed and direction of cosmic expansion. This clustering contributed to various phenomena, such as the formation of stars and galaxies. These structures have a profound effect on their surroundings, creating areas of low density between them, known as cosmic voids. Understanding this distribution helps astronomers piece together the history of the cosmos, revealing how galaxies evolved and interacted over billions of years. Furthermore, the distribution of dark matter, which constitutes a significant part of the universe's mass, unveils even deeper insights. Though invisible, dark matter influences the motion of galaxies through its gravitational pull, guiding the evolution of these majestic structures. It acts like a scaffolding, helping to shape visible matter into the familiar galaxies we observe today. The interplay between dark and visible matter is a central theme in modern cosmology, sparking ongoing research and discoveries. Overall, the intricate tapestry of how matter is spread throughout the universe not only influences the cosmic landscape, but also acts as a driving force in the ongoing expansion and evolution of the universe itself. As scientists continue to study these patterns, they unravel the profound mysteries of our existence and the nature of reality. Each discovery offers a glimpse into the past, shaping our understanding of the cosmos's future as well. The ultimate fate of galaxies is one of the most captivating mysteries in cosmology. Our universe is expanding, but the rate of that expansion is not uniform. This has led scientists to consider what might happen to galaxies over cosmic time. Some models suggest that as the universe continues to expand, galaxies will drift further apart, eventually leading to a chilling scenario where the night sky grows dark and empty. This outcome is often referred to as the Big Freeze, where galaxies, stars, and potentially even black holes dissolve into a vast, cold expanse. Another possibility is the Big Crunch, a hypothesis where the expansion of the universe could eventually halt and reverse, causing galaxies to collapse back into a dense state. In this scenario, the gravitational forces would dominate, pulling everything back together. However, current observations of the universe's accelerating expansion, driven by dark energy, seem to favor the Big Freeze over the Big Crunch. Still, this concept challenges our understanding of gravity and the fundamental forces at work in the universe. There's also a scenario known as the Big Rip, proposed by some theorists. In this theory, dark energy grows stronger over time, leading to an eventual tearing apart of galaxies, stars, and even atoms. Such a fate would suggest an abrupt ending to everything as we know it. Each of these scenarios opens up profound questions about the future of cosmic structures, the nature of dark energy, and the very fabric of space and time. Researchers continue to probe these profound questions using advanced telescopes and cosmic observations, unveiling clues about the behavior of galaxies over billions of years. The variations between these possible fates not only fuel scientific inquiry, but also invite us to ponder our place within this vast, ever-evolving universe. The fate of galaxies is not just a question about the future of celestial objects. It compels us to reflect on the nature of existence itself and the timeline of the universe as a whole. Humans tend to think of time as a uniform and steady progression, much like a straight line from the past to the present and into the future. We measure this familiar passage with clocks and calendars, breaking it into hours, days, and years. This understanding works well for our daily lives, but when we look at the cosmos, the nature of time presents a far more complex and fascinating picture. In the vastness of the universe, time does not flow equally everywhere. Instead, it can stretch and warp due to gravitational forces, a concept brought to light by Albert Einstein's theory of relativity. For instance, near a massive object, like a black hole or a neutron star, time moves slower compared to a distant observer. This phenomenon is known as time dilation, and it starkly illustrates that time is not a constant but a variable affected by gravity and motion. This means that if you were to orbit a black hole, you could return to find that much more time has passed for those left behind on Earth. Furthermore, when considering the universe's expansion, time takes on yet another dimension. Since the universe began with the Big Bang, time itself has been intertwined with the expansion of space. As galaxies drift farther apart, the experience of time at cosmic scales alters, suggesting that our understanding is framed by the specific conditions of our small corner of the universe. This creates an intriguing juxtaposition. While we live our lives within a defined structure of time, the universe's vastness holds a different reality, one that can feel both alien and awe-inspiring. In conclusion, while our day-to-day lives operate within a consistent framework of time, the cosmos reveals a much more intricate relationship. Time can bend and stretch, influenced by gravity and the expansion of the universe. This not only highlights the unique nature of our existence, but it also invites us to ponder the broader truths about reality and the universe we inhabit, igniting our curiosity and deepening our sense of wonder. The theory of relativity, introduced by Albert Einstein over a century ago, revolutionized our understanding of time and space. Traditionally, we perceive time as a constant progression and space as a fixed layout of distances and positions. However, relativity shows us that these concepts are not so straightforward. Instead, they are intertwined and influenced by factors such as speed and gravity, leading to surprising and counterintuitive conclusions. One of the most captivating aspects of relativity is time dilation. This phenomenon suggests that time moves at different rates depending on how fast an object is moving relative to another. For example, if a person were to travel in a spacecraft at speeds close to that of light, they would age much more slowly compared to someone remaining on Earth. This means that if they took a journey into space and returned, they could find themselves younger than their peers who stayed behind. This idea prompts us to rethink the very nature of aging and the experience of time itself. Similarly, relativity alters our perception of space. According to Einstein, the faster an object travels, the shorter it appears along the direction of its motion. This effect, known as length contraction, is negligible at everyday speeds, but becomes significant as one approaches the speed of light. Thus, two observers moving relative to one another may disagree on the lengths of objects and the distance between them, further complicating our traditional views of space and distance. Gravity also plays a substantial role in shaping our experience of time and space. According to general relativity, the presence of mass warps the fabric of space-time, effectively influencing how time flows. For instance, clocks located closer to a massive object like a planet will tick more slowly compared to those positioned farther away. This means that time is not just a constant, it is affected by gravity, leading to fascinating implications for how we understand the universe and our place within it. Through relativity, we realize that our perceptions of reality are not as fixed as they seem, making the cosmos an even more mysterious and wondrous place. Time is a fascinating concept, woven deeply into the fabric of various cultures and their understandings of the universe. In many Western traditions, time is often viewed linearly. There is a clear progression from the past through the present and into the future. This idea aligns neatly with scientific perspectives, where time is treated as a continuum, measurable and consistent, much like a river flowing steadily onward. The clocks and calendars we rely on today are reflections of this linear understanding, segmenting life into hours, days, and years. However, other cultures offer an intriguing contrast. For example, many indigenous cultures view time as cyclical, seeing it as a series of repeating patterns and seasons. This perspective emphasizes a deep connection to nature, where events like harvests and migrations occur in rhythms that recur year after year. From this point of view, the universe is not just a place of linear progress, but a place of ongoing renewal, where history informs the present and shapes what will come next. In Hinduism, time is viewed through the lens of the vast cosmic cycles known as yugas. These cycles describe an intricate dance of creation and destruction, where epochs come and go. This notion reflects an understanding of the universe as a living, breathing entity that evolves over eons, lending a profound sense of continuity and change. Similarly, in ancient Chinese philosophy, the concept of time is interwoven with the natural world, where harmony and balance dictate the passage of time, as seen in the cycles of yin and yang. As we consider these varied interpretations of time, we gain a richer perspective on how humanity grapples with our place in the cosmos. Whether viewed as a linear march or a cyclical dance, these cultural beliefs illuminate our shared quest for meaning in an ever-expanding universe. Ultimately, our interpretation of time shapes our connection to the stars above and to the rhythms of life itself. To understand the relationship between black holes and the fabric of space-time, we first need to grasp how space-time itself is envisioned in the realm of physics. Imagine space as a flexible fabric that can stretch and bend depending on the mass of objects within it. When massive celestial bodies like stars create a significant gravitational pull, they warp this fabric, influencing the movement of everything around them. Black holes, in particular, are the most extreme manifestations of this warping. They form when a massive star collapses under its own gravity, creating a point of infinite density known as a singularity. This singularity pulls nearby matter and energy toward it, creating an area around it where the pull of gravity is so strong that not even light can escape. This is what defines a black hole, essentially a region where space-time is bent to such an extent that conventional laws of physics break down. The boundary surrounding a black hole, known as the event horizon, marks the point of no return. Once something crosses this boundary, it cannot escape the gravitational grip of the black hole. This marks a profound interaction between gravity and the structure of space-time. It changes how we understand motion, with trajectories of objects being forced into spirals and curves as they approach. This relationship between black holes and space-time has far-reaching implications for our understanding of the universe. By examining how space-time behaves in the presence of these enigmatic entities, scientists gain insights into the nature of gravity itself and the fundamental laws governing the cosmos. As we continue to explore these phenomena, we uncover the mysteries of black holes and their role in the universe's grand tapestry, revealing how intricately connected everything truly is. Wormholes, often depicted in science fiction, present a fascinating possibility for traveling across the universe. Imagine a tunnel connecting two distant points in space and time, potentially allowing for instantaneous travel from one location to another. The concept arises from Einstein's theory of general relativity, where the fabric of space-time can be warped. This idea leads to the mind-bending notion that gateways to distant regions of the cosmos could exist. However, the very nature of wormholes challenges our traditional understanding of physics. For one, not all wormholes are stable. Many could collapse before anything could traverse them. Theoretical physicists have proposed that exotic matter, which possesses negative energy density, could keep a wormhole open. Throughout human history, several cosmic events have captured our imaginations and influenced our cultures. From the ancient times of celestial observations to modern astronomical advancements, some events stand out due to their significance and impact. One of the most notable is the appearance of Halley's Comet. Historically, this comet has been recorded for over 2,000 years. Its next appearance in the year 1076 caused awe and fear, believed to be an omen. Halley's Comet reminds us of the intricate dynamics of our solar system, with a predictable return every 76 years. Another pivotal event was the supernova that occurred in the year 1001. This explosion was so bright that it was visible during the day for weeks. Known as SN 1006, it resulted from a dying star and provided astronomers with a valuable opportunity to study the life cycle of stars. Such spectacular occurrences not only broaden our understanding of stellar evolution, but also ignite questions about the fundamental nature of the universe. The total solar eclipse of 1919 holds a special place in cosmic events. During this date, scientists, including the renowned physicist Albert Einstein, observed the bending of starlight around the Sun, confirming his theory of general relativity. This event reshaped our understanding of gravity and the fabric of space and time. The successful predictions and observations during this eclipse enhanced our understanding of how mass influences the curvature of space-time, propelling physics into new realms. Lastly, the launch of the Hubble Space Telescope in 1990 marks an extraordinary leap into our exploration of the cosmos. It has captured stunning images and provided invaluable data, vastly expanding our knowledge of distant galaxies, black holes, and the age of the universe itself. Each of these events not only displays the marvels of the universe, but also highlights the human drive to explore and understand the cosmos that envelops us. Supernovae are remarkable celestial events that play a crucial role in the formation of heavy elements in the universe. When a massive star exhausts its nuclear fuel, it can no longer support its own gravity. This leads to a catastrophic collapse of the star's core, followed by a powerful explosion that ejects the outer layers into space. This explosion not only marks the end of the star's life, but also serves as a stellar forge for a range of elements, particularly those heavier than iron. During the violent explosion of a supernova, the temperatures and pressures reach extraordinary levels. In these extreme conditions, nuclear reactions occur that allow for the creation of heavier elements through a process called nucleosynthesis. Elements like gold, silver, and uranium are synthesized in the aftermath of this explosion. The energy released is so immense that it can fuse lighter elements into the heavier ones that we often take for granted here on Earth. Once the supernova ejects these newly formed heavy elements into the surrounding space, they enrich the interstellar medium, the gas and dust that fill the universe. This material then becomes part of new stars and planetary systems. The very elements that make up our bodies and the Earth were formed in the hearts of ancient stars, only to be scattered across the cosmos by supernovae, where they would contribute to the next generations of celestial bodies. This intricate process illustrates the interconnectedness of the universe. The death of one star leads to the birth of new stars and planets, all made from the remnants of past supernovae. As scientists study these cosmic events, they gain a deeper appreciation for the rich tapestry of matter that surrounds us, and how the universe continually recycles itself through processes that are both awe-inspiring and fundamental to our existence. Pulsars and quasars, though vastly different in nature, provide significant insights into the mysteries of our universe. Pulsars, which are highly magnetized, rotating neutron stars, emit beams of electromagnetic radiation. As these beams sweep across the cosmos, they create a pulsing effect, much like a lighthouse beacon. When observed from Earth, these pulses can be remarkably regular, allowing scientists to use them as cosmic clocks. Through the study of pulsars, we gain valuable information about the properties of neutron stars themselves, but they also offer clues about extreme conditions in the universe, such as strong gravitational fields and matter under intense pressure. On the other hand, quasars represent some of the most luminous objects in the universe. They are the very active centers of distant galaxies, where supermassive black holes consume surrounding material at an extraordinary rate. This process generates immense energy, making quasars outshine entire galaxies. By observing quasars, astronomers can probe the early universe, since many of these objects existed when the universe was still young. The light from quasars allows us to study the formation of galaxies, the conditions of the early cosmos, and the expansion of the universe itself. The ability to observe both pulsars and quasars has led to groundbreaking discoveries in astroparticle physics and cosmology. Pulsars help refine our understanding of gravity, as their movements can reveal the warping of space-time caused by massive objects. Meanwhile, quasars challenge our knowledge of galaxy evolution by showcasing how black holes influence their surroundings and fuel growth over billions of years. Together, these objects serve as cosmic signposts, guiding scientists through the vast expanse of time and space. Ultimately, pulsars and quasars not only enhance our comprehension of extreme astrophysical phenomena, but also connect us to the broader narrative of the universe. They remind us that even in the farthest reaches of space, there are tools at our disposal to decode the past and contemplate the future. Through ongoing research and observation, these celestial bodies continue to unveil the tapestry of cosmic history, deepening our understanding of how the universe works. Gravitational waves are like ripples in space-time, caused by some of the most violent events in the universe, such as merging black holes or colliding neutron stars. They were first predicted by Albert Einstein more than a century ago, and their detection has opened an entirely new window for astronomical research. Unlike light, which can be blocked or altered by obstacles, gravitational waves travel through the universe almost unimpeded, providing a clear signal of the cataclysmic events that created them. The first detection of gravitational waves in 2015 confirmed a major prediction of Einstein's general theory of relativity and marked a significant leap in our understanding of cosmic events. Observatories like LIGO and Virgo have since recorded numerous events, revealing not just the existence of black holes but also their sizes, spins, and the dynamics of their interactions. Each observation allows scientists to observe the universe in a fundamentally different way, as they can hear the sounds of these cosmic collisions rather than merely seeing them through light. These waves have profound implications for understanding the behavior of matter under extreme conditions. For instance, when neutron stars collide, they produce not only gravitational waves, but also heavy elements like gold and platinum. This connection between the cosmos and the origins of elements allows researchers to piece together a fuller picture of how the universe evolves over time. It emphasizes the dynamic nature of the cosmos, offering clues to the fundamental processes that shape our existence. As gravitational wave detection technology advances, we can expect even more groundbreaking discoveries. Researchers are developing future observatories that will be sensitive to smaller, more distant events, allowing us to observe the early universe and potentially unravel some of its greatest mysteries. With every new detection, gravitational waves deepen our understanding of the cosmos and challenge us to reconsider our place within it, reminding us of the incredible forces at play beyond our planet. Gamma-ray bursts, often shortened to GRBs, are among the most intense and energetic explosions observed in the universe. These celestial events release an enormous amount of energy, equivalent to what the sun will emit over its entire lifetime, all in just a few seconds or minutes. By studying gamma-ray bursts, astronomers gain invaluable insights into the most extreme conditions in space, allowing us to expand our understanding of cosmic phenomena. One of the key aspects we learn from GRBs is the process of stellar evolution. Many gamma-ray bursts are thought to result from the collapse of massive stars, leading to the formation of black holes. This connection to stellar death provides a unique opportunity to observe the life cycles of stars and the dramatic ways they end, shedding light on the synthesis of heavy elements that will eventually form planets and life. Additionally, GRBs allow scientists to probe the early universe. Because these bursts can be detected from billions of light-years away, They serve as beacons that illuminate the intergalactic medium through which they travel. Analyzing the light from GRBs helps astronomers understand the conditions of the universe during its infancy and the formation of galaxies. This is crucial for piecing together the history of our cosmos and exploring its evolution over time. Finally, the study of gamma-ray bursts pushes the boundaries of our technological capabilities. Harnessing the power of advanced telescopes and detectors, researchers develop new methods to observe and analyze these fleeting events. The techniques used in gamma-ray astronomy often lead to breakthroughs in other fields of science and technology, creating advancements that may seem far removed from cosmology but have profound effects on our daily lives. Thus, the investigation of gamma-ray bursts not only reveals stunning cosmic truths, but also inspires innovation and progress in our quest for knowledge. When scientists search for potentially habitable exoplanets, a set of crucial criteria guides their investigation. The very first criterion revolves around the planet's location in relation to its star. This zone, often referred to as the Goldilocks zone, is the region where conditions might be just right for liquid water to exist. Too close to a star, and all water could evaporate. Too far away, and it might freeze. The ideal spot allows for a stable environment where life as we know it could conceivably thrive. Another important factor is the planet's size and composition. Ideally, a potentially habitable planet should be rocky, much like Earth, as opposed to being gas giant like Jupiter. A planet in the right size range is thought to have the capability to hold onto an atmosphere, which plays a crucial role in regulating temperature and protecting any potential life forms from harmful radiation. A planet that is too small may not possess enough gravity to retain an atmosphere, while one that is too large may become a gas giant with extreme surface conditions. Atmospheric conditions also significantly impact habitability. Researchers look for signs that an atmosphere exists, as well as its composition. To support life in a way that is familiar to us, an atmosphere would ideally contain essential gases like oxygen and carbon dioxide, and sustain pressures that allow liquid water to persist. The presence of certain gases can also indicate biological processes, which might hint at the existence of life. Lastly, the stability of a planet's environment is critical. This includes its orbital stability and what kind of cosmic events it might face. Habitable planets benefit from a consistent climate over long periods, allowing time for life to evolve. By evaluating these criteria, scientists continue to expand their catalogue of potential worlds, each with its unique possibilities for life beyond our own. The Drake equation is a fascinating tool used to estimate the number of detectable civilizations in our galaxy. Formulated by the astrophysicist Frank Drake in the early 1960s, this equation provides a framework for scientific inquiry and a means to systematically consider the various factors that would contribute to the existence of intelligent life beyond Earth. Though it appears mathematical, at its core, the equation encourages scientists and researchers to think critically about what we know and don't know about the universe. The equation incorporates several variables, each representing different aspects essential for the development of intelligent civilizations. These include the rate of star formation in our galaxy, the fraction of stars that have planetary systems, and the number of planets that can potentially support life. Each of these factors invites further exploration and research, emphasizing that our understanding of life's potential in the cosmos is still evolving. By identifying these key elements, the Drake equation acts as a guide for prioritizing research in astrobiology and planetary science. Crucially, the Drake equation also highlights the uncertainty we face. Many of the variables are not well understood, leaving room for speculation and debate. For instance, while we know there are numerous stars and many have planets, the question of how many of these planets could harbor life remains largely unanswered. This uncertainty drives the scientific community to gather more data through missions to other planets in our solar system, studies of exoplanets, and searches for extraterrestrial signals. Ultimately, the equation serves both as a call to action and a reminder of the vastness of the unknown. It frames the search for alien civilizations as not just a quest for numbers, but an exploration of the fundamental conditions that allow life to exist. As we endeavor to answer its questions, the Drake equation continues to inspire the quest for knowledge about our place in the universe and the possibility that we are not alone. Astrobiology is a fascinating field that explores the possibility of life beyond our planet. It investigates the conditions necessary for life to exist, drawing insights from our own Earth as a starting point. Within this discipline, extremophiles play a crucial role. These are organisms that thrive in extreme environments on Earth, such as deep sea vents, acidic lakes, and the icy conditions of Antarctica. By studying these resilient life forms, scientists gather invaluable information about the potential for life in the harsh conditions of space. Extremophiles demonstrate that life can adapt to environments previously thought uninhabitable. For instance, certain bacteria can survive intense radiation, freezing temperatures, and extreme pressure. This adaptability sparks excitement about the search for extraterrestrial life. If life can flourish in the most inhospitable areas of our own planet, why not elsewhere in the universe? This prompts researchers to explore places within our solar system, like Mars, Europa, and Enceladus, which may harbor similar extremes. Moreover, the study of extremophiles has revealed the biochemical flexibility of life. These organisms often possess unique metabolic pathways and structural adaptations that allow them to utilize resources in ways we are only beginning to comprehend. This knowledge helps astrobiologists refine their search strategies, focusing on worlds where life might exist and what forms it might take. The diverse attributes of extremophiles also guide the types of experiments conducted in search of life beyond Earth. In conclusion, astrobiology and the study of extremophiles are interconnected disciplines that deepen our understanding of life's potential across the cosmos. The remarkable ability of life to endure extreme challenges not only ignites curiosity, but also shapes the direction of space exploration. As we look to the stars, the lessons learned from Earth's most resilient organisms may lead us to discover that we are not alone in the universe. The discovery of water on other planets has significantly reshaped our understanding of the potential for extraterrestrial life. For many years, scientists pondered whether life existed beyond Earth, often imagining what organisms might look like in various environments. When evidence emerged showing that water, a vital ingredient for life as we know it, is present on bodies throughout our solar system, it sparked new excitement and possibilities. For instance, the detection of water ice on the Moon and Mars opened new avenues for exploration. On Mars, the presence of liquid water, though sporadic, indicates a dynamic climate that may have nurtured life in its distant past. Additionally, the discovery of subglacial lakes on Europa, one of Jupiter's moons, and the plumes of water vapor erupting from Enceladus, a moon of Saturn, suggest that these icy worlds might harbor environments suitable for life. Scientists now realize that life could thrive in extreme conditions, far different from those on Earth. This realization has led researchers to expand the criteria for habitability. No longer solely relying on Earth-like conditions, scientists are exploring what life might be like in places we once dismissed as too hostile. The variety of water sources, from ice to salty brines, encourages the idea that life could adapt in unexpected ways. In fact, extremophiles, or organisms that thrive in extreme environments on Earth, inspire theories about how life might exist in similarly harsh conditions on other planets. As we continue to explore these celestial bodies, curiosity about life beyond Earth is igniting new scientific missions and innovations. Upcoming missions aim to investigate these potentially life-supporting environments, paving the way for deeper exploration. It's a thrilling time in astrobiology, as the search for life has transitioned from a distant dream to a tangible scientific endeavor fueled by our growing understanding of where water exists in the universe. The search for intelligent life beyond Earth raises a multitude of ethical implications that touch upon our values, responsibilities, and our very understanding of life itself. First and foremost, one key consideration is the potential impact on human civilization. If we were to discover intelligent extraterrestrial beings, it would beg crucial questions about how we engage with them. Do we approach them as equals, or do we view them through the lens of our own superiority? The prospect of miscommunication or misunderstanding could lead to unforeseen consequences, advocating for a careful and respectful approach. Additionally, there's the ethical dilemma surrounding our responsibilities toward these intelligent entities. Should the discovery of extraterrestrial life prompt us to share knowledge and resources with them? Conversely, If we find that their technological advancement is significantly lower than ours, do we have the ethical obligation to assist or protect them from exploitation? This situation mirrors historical events on Earth, where more advanced civilizations have interacted with less technologically developed cultures, often with detrimental outcomes. The lessons from our own history urge us to consider the long-term effects of our actions. Moreover, we must reflect on the implications of changing our own definition of life. As we study the cosmos, we are faced with the realization that life can manifest in forms that differ vastly from our own. This realization not only broadens the scope of what we consider sentient, but also calls for an ethical evaluation of how we regard and treat all forms of life. Are we willing to embrace a more inclusive ethical framework that accounts for these diverse manifestations of existence? Lastly, the search itself invites scrutiny regarding the allocation of resources and priorities. Are we, as a society, justified in spending vast amounts of time, effort, and money on the quest for extraterrestrial intelligence while pressing issues on our home planet remain inadequately addressed? This question challenges us to weigh our curiosity about the universe against our responsibilities to humanity and the environment. Balancing exploration with compassion for our own planet is a tightrope walk that defines not only our search for life in the cosmos, but also our very identity as stewards of Earth. Throughout history, ancient civilizations looked to the skies and interpreted celestial phenomena in ways that were deeply intertwined with their cultures, beliefs, and everyday lives. The movements of the sun, moon, and stars were not merely understood as natural occurrences, they were often seen as omens or messages from the gods. For many societies, celestial events such as eclipses, comets, and planetary alignments carried significant meaning, often influencing agricultural practices, religious rituals, and even governance. The ancient Egyptians, for instance, meticulously observed the stars and aligned their pyramids with specific stars like Sirius. This star's heliacal rising signaled the annual flooding of the Nile, which was crucial for agriculture. In a similar vein, the Mayans had an intricate calendar system based on their observations of celestial cycles, which informed their agricultural planting times and significant religious events. Their ability to predict eclipses and other celestial events demonstrated a profound understanding of astronomy that was central to their civilization. In contrasting regions such as Mesopotamia, the Sumerians developed one of the earliest known forms of astrology. They believed that the positions of celestial bodies could influence earthly events. These interpretations guided various aspects of life, from agriculture to warfare and personal decisions. The sky was viewed as a heavenly realm filled with divine influences, making it crucial for leaders and citizens alike to observe and heed celestial signs. Even in ancient Greece, philosophers like Ptolemy synthesized existing knowledge, linking celestial movements to earthly experiences. Such insights laid the groundwork for modern astronomy. Therefore, it becomes evident that ancient civilizations, through their observations of celestial phenomena, wove science, spirituality, and practicality into a rich tapestry that highlighted their profound connection to the cosmos. This quest to understand the heavens remains a testament to humanity's enduring relationship with the stars. Early astronomers laid the foundational blocks of our modern understanding of the universe, changing our perception of the cosmos in profound ways. Before their inquiries, humanity viewed the heavens through a largely mythological lens, attributing celestial phenomena to the whims of gods or mysterious forces. However, astronomers like Ptolemy, Copernicus, and Galileo shifted this paradigm. They moved us towards a more systematic and empirical approach to studying the stars and planets. Ptolemy's influence, for instance, dominated Western thought for many centuries. His geocentric model, which positioned the Earth at the center of the universe, provided an organizational framework despite its inaccuracies. Although this model eventually fell short, it was instrumental in fostering interest in celestial observations. The meticulous records of planetary movements laid the groundwork for future astronomers to derive more accurate models. The transition initiated by Copernicus was revolutionary. He proposed the heliocentric model, placing the sun at the center of our solar system, an idea that contradicted prevalent beliefs. Copernicus's work ignited a chain reaction, leading researchers to adopt more observational strategies. With tools like the telescope, individuals such as Galileo began to gather evidence that challenged conventional ideas about the universe. Observations of planets and moons revealed a complex cosmos that was far more dynamic than previously imagined. This surge of inquiry reached a pivotal moment with the work of Isaac Newton, who unified the principles of motion and gravity. His laws explained how celestial bodies interact, allowing for the predictions of planetary orbits and behavior. Together, these early astronomers ignited a scientific movement that has continued to evolve, shaping our understanding of the universe from mere speculation to data-driven exploration, and inspiring generations to further unveil the mysteries of the cosmos. Throughout history, many cultures have played a vital role in the development of astronomy, each contributing unique observations and interpretations of the night sky. Ancient civilizations, from the Babylonians in Mesopotamia to the Maya in Central America, meticulously recorded celestial events, laying the groundwork for our understanding of the cosmos. Their observations were often tied to agricultural cycles, religious practices, and navigation, emphasizing the close relationship between astronomy and daily life. The Babylonians are particularly notable for their early contributions. They developed one of the earliest known star catalogues and created detailed records of astronomical phenomena. They observed and tracked planetary movements, leading to the formation of a lunar calendar. This intricate system not only enhanced their agricultural planning, but also influenced later Greek astronomy, bridging cultures and knowledge. In the southern hemisphere, the indigenous peoples of Australia mapped the stars in ways deeply connected to their storytelling and cultural beliefs. They saw constellations as ancestors and spirits, embedding astronomy in their traditions and daily lives. The skillful navigation techniques they employed, guided by the stars, showcase a profound understanding of celestial navigation that was developed over thousands of years. The influence of these diverse cultures is still felt today. Modern astronomy continues to explore the foundations laid by these early practitioners, who demonstrated that understanding the universe was not solely a scientific pursuit, but a deeply human one, intertwined with culture, religion, and daily existence. Their contributions remind us that the night sky has always been a source of wonder and inquiry across all societies. In ancient times, astronomers relied primarily on their own observations of the night sky. With the naked eye, they studied the stars, planets, and moon, noting their positions and movements over time. This direct observation laid the groundwork for our understanding of celestial patterns. They recorded the shifting positions of stars across seasons and the cycles of the moon, using simple tools like sticks in the ground to mark positions or stones to create early star maps. As the centuries progressed, early astronomers created instruments like the astrolabe and the armillary sphere. The astrolabe, a sophisticated device designed for solving problems related to time and the position of stars, allowed observers to measure the altitude of celestial bodies above the horizon. This involved a disk with a rotating arm, which helped astronomers make more precise calculations about the location of stars and planets. Meanwhile, the armillary sphere, a model of the celestial sphere, aided in visualizing the complex movement of celestial bodies in relation to Earth. The invention of the telescope in the 17th century marked a revolutionary leap in astronomy. Initially crafted by pioneers like Galileo, this instrument magnified distant stars and planets, revealing details previously invisible to the naked eye. Galileo's observations, such as the moons of Jupiter and the phases of Venus, provided undeniable evidence that the cosmos was far more dynamic and complex than earlier models had suggested. In addition to telescopes, early astronomers utilized mathematical calculations to predict celestial events. They developed models to explain the movements of the heavens, looking for patterns that would predict occurrences like eclipses or the positions of planets. With these tools and methods, early astronomers laid a crucial foundation for modern astronomy, continuously expanding our understanding of the universe. These early efforts remind us of our enduring quest to interpret the mysteries of the night sky. The mythology of the cosmos is a fascinating tapestry woven from the threads of countless cultures and eras, reflecting humanity's enduring quest to understand the universe. In ancient cultures, celestial bodies often took on divine attributes, leading to a diverse array of stories that explained their movements and influences on life on Earth. For example, in Egyptian mythology, the sun god Ra was believed to fight against darkness each night, symbolizing the cycle of day and night, while the Greeks bestowed personalities on celestial objects, creating gods and heroes tied to constellations and planets. As societies evolved, so did their cosmologies. In Eastern traditions, such as Hinduism and Buddhism, the cosmos is often viewed through the lens of cycles and rebirth, suggesting a universe that is infinite and ever-changing. The concept of time in these traditions does not flow linearly, but instead circles back on itself, mirroring the cycles of nature. These differing views reveal how cultures perceive their place within the universe, illustrating a profound relationship between humanity and the cosmos. In contrast, the scientific revolution brought about a more empirical approach to understanding the heavens. This shift saw mythological narratives giving way to observations and theories grounded in evidence. The heliocentric model proposed by Copernicus challenged the long-held geocentric view and transformed humanity's position in the cosmic order. With each discovery, from Newton's laws of motion to the theories of relativity, our understanding of the universe has continued to evolve, merging the poetic myths of old with the rigorous inquiry of modern science. Today, the conversation around the cosmos continues to expand, blending ancient myths with contemporary theoretical physics. As we explore the vastness of space with ever-advancing technology, we find ourselves returning to that age-old question: what is our place in the universe? This ongoing dialogue between myth and science not only reveals the depth of human imagination, but also highlights our innate desire to connect with the cosmos in meaningful ways, ensuring that the mythology surrounding the universe remains vibrant and ever-changing. The anthropic principle is a fascinating concept that invites us to ponder our existence and the nature of the universe. At its core, this principle suggests that the universe's physical properties must allow for the emergence of conscious observers like us. In simpler terms, the universe is shaped in a way that facilitates the existence of life, and particularly intelligent life. This concept challenges us to consider not just the mechanics of the cosmos, but what it means for our very being. There are actually two main interpretations of the anthropic principle: the weak anthropic principle and the strong anthropic principle. The weak version points out that the universe's observed values of physical constants are conditions where life can emerge. For example, if the force of gravity were slightly different, stars might not form, and life as we know it could not exist. The strong interpretation goes a step further, suggesting that the universe must be able to develop intelligent life to even ask the question of why the universe exists in the first place. The anthropic principle nudges us to reflect on our place in the cosmic scale. It implies that we are not just passive observers of the universe, but integral parts of it. It raises profound questions. Are we a rare anomaly in a vast, indifferent cosmos? Or is there a deeper connection that ties together all conscious beings and the universe they inhabit? It encourages both scientists and philosophers to seek explanations that combine empirical evidence with existential inquiry. The anthropic principle enriches our understanding of cosmology. It invites us to remain curious about the universe's vastness and complexity, and deepens our appreciation for the delicate balance that allows life to flourish. By pondering our existence in light of this principle, we not only explore the mechanics behind the stars, but also embark on a journey into the very heart of what it means to be human in a universe that seems, against the odds, designed for consciousness to arise. Philosophy has long shaped our understanding of the cosmos, providing different lenses through which we can interpret our universe. Ancient philosophical traditions, such as those of the Greeks, set the groundwork for how we think about reality. Pythagoras and Plato considered the cosmos to be a harmonious and ordered system, suggesting that mathematics and philosophy were intertwined in explaining the universe. This belief in an underlying order inspired centuries of scientific exploration, revealing the universe as a grand, interconnected tapestry. In contrast, the materialist perspective, which emerged prominently in the Enlightenment era, emphasizes a universe governed by physical laws and observable phenomena. This approach leads to a more empirical observation of the cosmos, focusing on what can be measured and tested. Materialists argue that understanding the physical properties of stars, planets, and galaxies carries more weight than exploring metaphysical meanings. As a result, the materialist viewpoint pivoted scientific inquiry toward observation and experiment, paving the way for breakthroughs in cosmology. On the flip side, Existentialist and spiritual philosophies encourage interpretations of the cosmos that delve into meaning and our place within it. These perspectives provoke deeper questions about why the universe exists and what it signifies for human existence. For instance, existentialists wonder about the implications of a seemingly indifferent universe, while spiritual approaches may view the cosmos as a magnificent tapestry woven with purpose. Such perspectives can inspire us to reflect on our connections to the cosmos and each other, enhancing our sense of wonder. These philosophical orientations not only influence how we interpret the cosmos, but also shape the questions we ask and the pursuits we undertake in science and beyond. The interplay between science and philosophy invites a richer dialogue about existence, pushing us to explore not just the mechanics of the universe, but also the meanings that arise from our quest for knowledge. In this ever-expanding dialogue, we find ourselves contemplating timeless questions about life, existence, and our place in the grand scheme of things. Existentialism is a philosophical movement that explores the nature of existence, freedom, and individuality. In humanity's quest to understand the universe, existentialism plays a significant role by emphasizing our personal search for meaning within a vast and often incomprehensible cosmos. It prompts us to confront the profound questions about our place in the universe and the nature of reality itself. When we gaze at the stars or ponder the intricacies of the universe, existentialist thought encourages us to recognize the inherent uncertainty of existence. Rather than relying solely on scientific explanations, existentialism invites us to reflect on the subjective experiences that shape our understanding of the universe. This perspective can lead to a deeper appreciation of the mysterious and sometimes chaotic nature of existence, allowing us to find meaning even in uncertainty. Moreover, existentialism underscores the importance of individual responsibility in the face of an indifferent universe. As humanity reaches out into the cosmos seeking answers, we are reminded that it is our choices, actions, and interpretations that give our lives significance. In embracing this notion, we not only strive to understand the universe, but we also engage in self-discovery and personal growth, shaping our own paths amid the stars. Ultimately, existentialism enriches our cosmic exploration by linking the scientific pursuit of knowledge with the personal search for meaning. It urges us to embrace the questions rather than just the answers, allowing us to forge a deeper connection to the universe and to ourselves as we navigate the profound mysteries that lie beyond our world. The question of whether the universe can exist independently of human observation and thought delves deep into the heart of both science and philosophy. Our universe, with its vast galaxies, countless stars, and intricate laws of nature, is a reality that existed long before humans set foot on Earth. This universe, composed of matter, energy, and the fundamental forces of physics, operates based on principles that don't require human awareness or perception to exist. However, the fascinating interplay between observation and reality becomes particularly pronounced in the realm of quantum physics. Here, the act of observing particles can influence their behavior in ways that are not seen at larger scales. This has led to discussions about the nature of reality and how our consciousness might play a role in shaping it. Some interpretations of quantum mechanics suggest that observation is pivotal in determining the state of a particle, sparking debates about the objective nature of the universe. Despite these intriguing concepts, most scientists agree that the universe is not contingent upon human thought. The stars would continue to shine and the galaxies would swirl, regardless of whether there were observers to witness them. Our understanding of the cosmos may be shaped by our perspectives and the advancements of our science, but these discoveries reflect a reality that has always been there, continuing to evolve independently of our awareness. In exploring these profound questions, we encounter an intersection of science, philosophy, and the experience of existence itself. The cosmos, in its grandeur, holds mysteries that far exceed our current understanding, inviting us to ponder not just who we are, but our place within the great tapestry of the universe. The cosmos beckons us to explore, revealing its wonders and truths, irrespective of human interpretation. The concept of infinity has long intrigued thinkers and scientists throughout history, profoundly shaping our understanding of the universe. When we say something is infinite, we're often referring to something without boundaries or limits. In cosmology, this idea opens up compelling discussions about the cosmos itself. For instance, if the universe is infinite, It could mean that it stretches endlessly in all directions, housing endless galaxies beyond our observable limits. Infinity also plays a pivotal role in theoretical physics. When we study the universe's beginnings, we encounter the notion of an infinitely dense point where time and space themselves began, what we call the Big Bang. This singularity challenges our typical understanding of physics and pushes the boundaries of what we can comprehend. It invites questions like, what came before the Big Bang? What does it mean for the universe to have originated from such a point? Such inquiries highlight how infinity can stretch our imagination, drawing us to wonder about concepts that defy conventional reasoning. Moreover, infinity evokes thoughts about the vastness of space. The observable universe is immense, yet it barely scratches the surface of what might lie beyond. Some scientists suggest that there may be multiple universes, each potentially infinite itself, leading to the intriguing idea of a multiverse. This tantalizing possibility suggests that there are countless other realities, where different versions of events unfold, reinforcing the limitless nature of existence and the complexity of what is around us. Finally, the idea of infinity influences our understanding of mathematical concepts tied to the physical world. For example, scientific models often rely on the notion of infinitely small points in time and space. In reality, this helps us make sense of phenomena like black holes and the behavior of subatomic particles, though these constructs may seem abstract. Infinity brings a sense of wonder to scientific exploration, reminding us that while we have gathered incredible knowledge, the universe remains a vast, enigmatic realm, inviting further investigation and discovery. Over the past several decades, technology has transformed our ability to explore space in remarkable ways. One of the foundational advancements has been in the development of powerful rockets. Early missions relied on simple designs with limited payload capacities. Today's rockets, equipped with cutting-edge materials and engineering, can carry heavier and more sophisticated spacecraft into orbit and beyond. This evolution allows us to send larger and more complex scientific instruments to explore distant worlds. Communication technology has also seen substantial improvements. Initially, our ability to send signals to space was limited, struggling with delays and interference. With advancements in radio frequency technology and satellite communications, we can now transmit data from distant spacecraft back to Earth with incredible clarity and speed. This has not only enhanced our ability to gather scientific data, but has also enabled real-time communication with missions, allowing scientists to make quick decisions based on the incoming information. Moreover, our tools for observation have dramatically changed. Telescopes, once reliant on optical lenses, now utilize advanced digital sensors and adaptive optics to look deeper into the universe than ever before. With telescopes like the Hubble Space Telescope and the more recent James Webb Space Telescope, we can observe the cosmos in various wavelengths. This allows us to study everything from the birth and death of stars to the composition of exoplanets, revealing secrets of the universe that were once out of reach. Finally, advancements in artificial intelligence and robotics have opened new frontiers in space exploration. Robotic spacecraft, equipped with smart systems, can perform complex tasks autonomously, reducing the need for human oversight. Rovers on Mars are exploring the surface and sending back data that provide invaluable insights into the planet's geology and atmosphere. Together, these technological advancements not only enhance our understanding of space, but also fuel our curiosity, inspiring future generations to continue looking toward the stars. The advent of powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope has revolutionized our understanding of the universe. Hubble, launched in 1990, provided stunning images and crucial data that helped reveal the vastness and complexity of the cosmos. It offered insights into galaxy formation, stellar evolution, and even the accelerating expansion of the universe. Hubble's ability to observe distant galaxies allowed scientists to peer back in time, seeing light that had traveled billions of years to reach us, effectively letting us witness the universe as it was when it was much younger. With its launch in December 2021, the James Webb Space Telescope advanced these capabilities even further. Webb is designed to observe infrared light, which allows it to see through cosmic dust and gas, revealing objects that are too cold or too faint for Hubble's optical observations. This means that Webb can capture the faint glow of the first galaxies that formed after the Big Bang, offering insights into conditions and processes in the early universe. The detailed data provided by Webb helps astronomers improve their models of cosmic evolution, which deepens our understanding of how structures like galaxies and stars formed. Moreover, these telescopes play a vital role in exoplanet studies. Webb's unparalleled ability to analyze the atmospheres of distant planets increases our chances of identifying potentially habitable worlds. By scrutinizing the chemical compositions of these atmospheres, scientists can search for signs of life beyond Earth. This quest ignites profound questions about our place in the cosmos and whether we are alone in the universe. The implications of telescopes like Hubble and Webb extend beyond just fascinating images. They represent significant strides in cosmology and our quest for knowledge. They challenge our perceptions, making the cosmos more comprehensible while simultaneously opening the door to new mysteries. With every discovery, we seem to get closer to answering age-old questions while inevitably raising new ones about the universe and our existence within it. Robotic missions have transformed our understanding of distant planets and moons in profound ways. These remarkable spacecraft, equipped with advanced instruments and technologies, venture where humans cannot easily go. By exploring the far reaches of our solar system, they collect invaluable data that helps us piece together the mysteries of these distant worlds. From imaging to analyzing the atmospheres and surfaces, each mission offers insights that no telescope on Earth could provide. One of the standout features of robotic missions is their ability to operate in environments that are often hostile to human life. For instance, the Mars rovers have been essential in examining the Martian landscape, analyzing soil and rocks for past signs of water, and determining whether conditions were ever suitable for life. Similarly, missions like the Cassini spacecraft, which explored Saturn and its moons, have revealed extraordinary details about their atmospheres, rings, and potential habitability. These discoveries are made possible by the scientific instruments aboard, designed to gather and transmit data back to Earth for analysis. Another significant aspect of these robotic missions is their longevity. Many spacecraft, like Voyager, launched decades ago, are still sending back information about the outer planets and beyond. This long-term observation allows scientists to gather data over extended periods, tracking changes and understanding planetary dynamics better. The data collected paints a much clearer picture of these celestial bodies, contributing to our knowledge of their geological and atmospheric processes. Ultimately, robotic missions do not just expand our knowledge of distant places, they also ignite our curiosity about the universe. Each discovery encourages further exploration and ignites discussions about life beyond Earth, the formation of our solar system, and even the potential for future human exploration. These missions are not just vehicles of data, they are pathways to understanding our place in the cosmos. As we look towards the future, several innovative technologies stand poised to enhance our exploration of the cosmos. A significant driver of these advancements is the development of much more powerful rockets. For example, the Space Launch System, designed by NASA, represents a leap in capabilities, allowing us to send heavier payloads into deep space. These rockets can pave the way for missions that will take astronauts to Mars and beyond, leading to unprecedented discoveries on other planets. Another promising technology is the use of advanced robotics. Robotic spacecraft have already provided us with a wealth of knowledge about distant worlds, and innovations in artificial intelligence are set to elevate this exploration to new heights. Imagine rovers that can navigate rugged terrains autonomously, or drones that can explore the atmospheres of distant planets. These robotic pioneers can work tirelessly in environments where human explorers cannot, unveiling secrets of places like Titan or the gas giants of our solar system. Additionally, we are on the brink of developing solar sails and ion propulsion systems that could drastically reduce travel times across vast distances. Solar sails harness the energy from sunlight and, when combined with electric propulsion, could allow spacecraft to achieve incredible speeds. This technology is particularly exciting for potential interstellar missions, offering a glimpse into ways we could reach the closest star systems within a human lifetime. Finally, advancements in communication technology are essential for deep space exploration. Enhanced methods of data transmission, perhaps inspired by optical technology, could allow for faster and more reliable communication with spacecraft over vast distances. This progress will not only improve the efficiency of information exchange, but also enable scientists back on Earth to receive rich data from distant worlds almost in real time. With these transformative technologies on the horizon, our quest to understand the universe is set to enter an exhilarating new chapter. Artificial intelligence has transformed the field of cosmology by significantly improving our ability to analyze vast and complex datasets. The universe is teeming with information, from the subtle variations in cosmic microwave background radiation to the intricate patterns found in galaxy formation. Traditional methods of data analysis often fall short when faced with the sheer volume and complexity of this information. Enter artificial intelligence, which uses algorithms and machine learning to identify patterns and correlations in data far more efficiently than ever before. One of the most notable applications of artificial intelligence in cosmology is in the classification of astronomical objects. For instance, in surveys of the night sky, AI systems can quickly and accurately differentiate between various types of celestial bodies, such as stars, galaxies, and quasars. By training on large datasets, these AI models learn to recognize the subtle differences in images that human analysts might overlook. This process not only speeds up research, but also enhances the quality of the findings, allowing scientists to explore deeper questions about the universe's structure. Moreover, artificial intelligence plays a crucial role in data simulation and prediction. It can model cosmic phenomena, such as the formation of galaxies or the behavior of dark matter, based on existing theories and data. These simulations help researchers visualize scenarios that would be impossible to observe directly. For example, using AI, scientists can predict how light from distant galaxies is affected by gravity as it travels through space-time, a process known as gravitational lensing. Such predictions are instrumental in testing theories of relativity and refining our understanding of fundamental astrophysical processes. The integration of artificial intelligence into cosmology extends beyond analysis and prediction. AI tools also help to identify new phenomena, flagging unusual events or anomalies that merit further investigation. As the data collected from telescopes and space missions continues to grow exponentially, the collaboration between artificial intelligence and human researchers will likely deepen, heralding an era of profound discoveries that may reshape our understanding of the cosmos. In this dynamic interplay, artificial intelligence does not merely enhance our existing capabilities. It opens new frontiers for exploration, pushing the boundaries of what we know about the universe. Astrophysics is a vast field filled with mysteries that continue to intrigue scientists and enthusiasts alike. Among the biggest unanswered questions is the nature of dark matter, which is believed to make up about 25% of the universe. While we can infer its existence through its gravitational effects on visible matter, we have yet to detect it directly. What could this elusive substance be? Many theories propose various particles or exotic forms of matter, but none have been conclusively proven. Another significant question revolves around dark energy, which is thought to account for about 70% of the universe. This mysterious force is driving the accelerated expansion of the cosmos. Scientists are puzzled by its origin and nature. What is it that is causing galaxies to move apart at an increasing rate? Some propose that it might be a property of space itself, while others suggest it could be a manifestation of new physics beyond our current understanding. Additionally, the enigma of black holes presents a challenge in modern astrophysics. While we have a solid grasp of their existence and impacts on surrounding matter, many questions remain about what happens beyond their event horizons. Are singularities real, or could they instead point to a breakdown of our current laws of physics? Understanding the true nature of black holes may revolutionize our comprehension of time, space, and the fundamental structure of the universe. Lastly, we can't overlook the search for extraterrestrial life. Have we truly found every potential habitat within our galaxy? Or are there worlds teeming with life beyond our current reach? Even as we send missions to distant planets and moons, like the intriguing subsurface oceans of Europa and Enceladus, the answer remains tantalizingly out of reach. The quest to understand whether we are alone in the universe continues to spur exploration and discussion in astrophysics. Dark matter is one of the most intriguing mysteries in the universe. Although it constitutes about 27% of the cosmos, it remains invisible and undetectable directly with our current technology. Scientists cannot see dark matter with telescopes, nor can they measure it through traditional means. Instead, its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. The first clues about dark matter emerged in the early 20th century when astronomers observed that galaxies were spinning at such speeds that they should have flown apart. There simply wasn't enough visible matter in these galaxies to hold them together through gravity. This led to the idea that there must be some unseen mass, dark matter, providing the necessary gravitational pull. It's like a hidden scaffolding, maintaining the structure of the universe while remaining entirely out of sight. While researchers have proposed various candidates for what dark matter could be, the most popular theory points to a class of particles called weakly interacting massive particles, often shortened to WIMPs. These particles would interact with normal matter very weakly, which explains why they evade detection under most conditions. Scientists are conducting experiments deep underground and in large particle colliders to try to catch a glimpse of these elusive particles, but so far it remains an ongoing quest. The nature of dark matter is critical not only for our understanding of the universe's composition, but also for its evolution. It plays a significant role in galaxy formation and the overall structure of cosmic web. Though we currently cannot see dark matter, we have a wealth of evidence pointing to its existence. Like a silent partner in a vast dance, dark matter shapes the universe while remaining a tantalizing enigma, endlessly sparking curiosity and investigation among scientists and stargazers alike. Time travel has long captivated our imaginations, solidifying its place in science fiction while also raising profound questions within the realm of physics. At its core, the concept challenges our understanding of time itself, which we typically perceive as a continuous flow. In physics, time is often depicted as a dimension similar to space, leading to fascinating theories that suggest movement through time might be possible. One of the foundational theories that touches on time travel is Albert Einstein's theory of relativity. This theory introduces the idea that time can be affected by speed and gravity. For instance, as an object moves closer to the speed of light, time slows down relative to observers who are at rest. This phenomenon, known as time dilation, suggests that traveling at incredibly high speeds could allow a traveler to experience time differently compared to those remaining stationary, essentially granting a form of time travel into the future. Additionally, the idea of closed time-like curves has been proposed, particularly in the context of black holes and wormholes. A closed time-like curve would allow an object to return to its own past, creating a loop in time. This leads to intriguing paradoxes, such as the famous grandfather paradox, which questions what happens if you were to travel back and inadvertently prevent your own grandfather from meeting your grandmother. Such logical conundrums illustrate the complexities and contradictions that time travel introduces. Despite these intriguing possibilities, practical time travel remains purely theoretical. The enormous energies required, coupled with our current understanding of physical laws, make time travel seem more like a dream than a reality. Nonetheless, the mysteries of time travel ignite our curiosity and push the boundaries of what we know, inspiring scientists to explore deeper into the nature of time and our universe, igniting hopes that perhaps one day we might glimpse the possibilities that lie beyond the present. Black holes embody some of the most intriguing paradoxes in the universe, challenging our understanding of physics and our grasp of reality itself. At their core, black holes are regions in space where the gravitational pull is so intense that nothing, not even light, can escape. This characteristic leads to a question that has puzzled scientists. What happens to information that falls into a black hole? This is often referred to as the information paradox. According to the principles of quantum mechanics, information cannot be destroyed. However, if something material falls into a black hole, it seems as though the information about that matter disappears forever when the black hole evaporates or merges. This contradiction raises fundamental questions about the laws of physics. Some physicists suggest that information might be preserved in some way, perhaps encoded on the event horizon, the boundary surrounding a black hole, or even emitted back into the universe as radiation. Another captivating paradox involves the nature of time near a black hole. The intense gravity near a black hole warps time, creating differences in how time is experienced. For someone falling into a black hole, time would slow down dramatically compared to someone watching from a distance. This leads to a surreal scenario where one could witness the universe evolve while being in a timeless bubble. This concept stretches our understanding of reality and pushes the boundaries of what we believe to be true about time and space. The pursuit of understanding these paradoxes has led to numerous theories and hypotheses. Researchers explore ideas such as holographic principles, which suggest that the information on the surface of the black hole can reconstruct what fell inside. These discussions highlight the vibrant, evolving nature of science as we continue to grapple with the complexities of black holes. Each answer seems to unveil new questions, inviting us to look deeper into the cosmos's captivating mysteries. The concept of the multiverse has captivated scientists and cosmologists alike, suggesting that our universe might be just one of many. One prominent theory comes from quantum mechanics, specifically the idea of many worlds. According to this view, every time a decision or measurement is made at a quantum level, the universe splits into different branches. This means that every possible outcome of every event actually occurs in some separate universe, creating an infinite tapestry of realities. Another intriguing perspective on the multiverse arises from cosmic inflation, a rapid expansion of space that occurred just after the Big Bang. According to this theory, inflation happens differently in various locations. As a result, some regions of space may cease inflating while others continue to expand, potentially creating bubble-like universes, each with its own distinct laws of physics. In this vast multiverse, the conditions and constants we observe in our own universe could be just one set among countless others. The implications of the multiverse theory are profound and somewhat bewildering. It challenges the notion of uniqueness. If there are infinite universes, the idea that our universe is special becomes harder to justify. Furthermore, it raises questions about the nature of reality itself and whether we can ever truly understand the universe we inhabit when there might be so many others beyond our reach. Moreover, the multiverse theory pushes the boundaries of science itself. While traditional science relies on empirical evidence and observation, many aspects of the multiverse remain speculative. This discrepancy leads to intriguing philosophical discussions about the nature of scientific inquiry. If we live in a multiverse, how do we confirm the existence of other universes? These questions keep scientists and thinkers modern day tantalizingly engaged in the quest to unravel the mysteries of existence. In grappling with the multiverse theory, we not only face the limits of our understanding but also discover the vast potential of what lies beyond. Light plays a crucial role in our understanding of the universe, serving as both a tool and a medium through which we gather information about celestial bodies and phenomena. When we observe the stars, planets, and galaxies, we are actually looking at the light that traveled vast distances to reach us. This light carries essential information about the temperature, composition, and movement of these celestial objects. By examining different wavelengths of light, from visible colors to infrared and ultraviolet, scientists can uncover a wealth of details about the universe's structure and evolution. The importance of light extends beyond mere observation. It is fundamental to the principles of astronomy. The concept of redshift, for instance, helps us comprehend the expanding nature of the universe. As galaxies move away from us, their light shifts towards the red end of the spectrum. By measuring this redshift, astronomers can determine not only how fast a galaxy is receding, but also glean vital insights into the universe's history and its ultimate fate. This relationship between light and cosmic expansion is a key pillar of the Big Bang theory, revolutionizing our understanding of cosmic beginnings. Moreover, light also informs us about the phenomenon of dark matter and dark energy. While these entities cannot be seen directly, they influence visible matter through their gravitational forces. By studying how light from distant galaxies bends around unseen mass, scientists have been able to map the distribution of dark matter across the universe. This has profound implications for our grasp of the cosmos, particularly as dark matter is thought to make up a significant portion of the universe's mass. Lastly, light is indispensable in the field of astrophysics, where it helps bridge gaps in our knowledge. Telescopes equipped to detect various wavelengths enable us to observe events such as supernova, black hole formations, and the birth of stars. With each discovery made possible by different forms of light, we continue to piece together the intricate puzzle that is our universe, deepening our understanding of both familiar and enigmatic cosmic phenomena. Spectroscopy is a fascinating scientific technique that plays a crucial role in understanding the universe. By studying the light that interacts with various celestial objects, astronomers can identify the chemical composition of distant stars, planets, and galaxies. When light from these objects passes through a prism or a spectrograph, it breaks into its constituent colors, creating a spectrum. This spectrum contains valuable information, as each element in the universe absorbs and emits light at specific wavelengths. As light from a distant celestial body meets our instruments, certain wavelengths may be missing or altered. These differences arise because elements like hydrogen or helium absorb certain colors of light. Scientists meticulously analyze these patterns, comparing them to known wavelengths that correspond to different elements. This allows them to discern which elements are present in faraway celestial entities, even billions of light-years away. Moreover, the way the spectrum shifts can reveal even more information about these objects. If a celestial body is moving towards us, the wavelengths of light appear compressed, resulting in a shift towards the blue end of the spectrum. Conversely, if it is moving away, the wavelengths stretch towards the red side. This phenomenon, known as the Doppler effect, provides insight into the movement and velocity of those galaxies and stars, deepening our understanding of cosmic expansion. Spectroscopy acts like a cosmic fingerprint, offering a unique glimpse into the distant universe. With each spectrum analyzed, astronomers uncover the elemental makeup of stars, understand the dynamics of galaxies, and explore the intricate tapestry of matter that fills the cosmos. This method not only enriches our knowledge, but also fuels curiosity about the universe's past, present, and future. Light, the fundamental form of electromagnetic radiation, is not only essential for our sight, but also plays a critical role in understanding the cosmos. It travels through the vacuum of space at an astonishing speed, about 300,000 kilometers per second. This incredible speed allows us to see distant stars and galaxies as they were millions or even billions of years ago, offering a glimpse into the history of the universe itself. When light encounters matter, its interaction can reveal vital information about the cosmic phenomena we observe. For instance, when light from a star passes through a cloud of gas, certain wavelengths are absorbed by the elements in that gas. This results in a unique pattern of dark lines in the star's spectrum, akin to a fingerprint. By studying these absorption lines, scientists can determine the composition, temperature, and even the movement of celestial bodies. Moreover, light bends when it passes near massive objects due to gravity, a phenomenon known as gravitational lensing. This effect allows astronomers to study objects that are otherwise too faint or distant to observe directly. By analyzing the light that has been bent around a galaxy, researchers can glean insights about its structure and the dark matter surrounding it. Gravitational lensing thus serves as a powerful tool in cosmology, helping to unlock the mysteries of the universe. Lastly, the varying wavelengths of light, from radio waves to visible light and beyond, also offer diverse information about cosmic events. Different wavelengths tell different stories. For example, radio waves can reveal the presence of cosmic background radiation, while X-rays can expose high-energy phenomena like black holes and supernovae. Together, these interactions of light with matter not only illuminate the universe's past, but also guide us toward its future, allowing us to piece together the grand narrative of cosmic evolution. The speed of light is a fundamental constant that serves as a cosmic speed limit. It travels at about 300,000 kilometers per second, or around 186,000 miles per second in a vacuum. This speed is crucial not just for light itself, but for all forms of electromagnetic radiation. It influences how we perceive and understand the universe around us. Due to this limit, the light we see from distant stars and galaxies took time to reach us, which means we are essentially looking back in time. When we observe the night sky, we are witnessing events that may have occurred millions or even billions of years ago. For instance, if a star is located 10 million light-years away, The light from that star takes 10 million years to reach our eyes. This aspect of light travel turns our observations into a history lesson, revealing how the universe has evolved over unimaginable stretches of time. We often think of light as instantaneous, but its finite speed adds a temporal dimension to our observations. Moreover, the speed of light also affects the way we understand distance in the cosmos. The concept of a light year, which is the distance light travels in 1 year, helps scientists define vast cosmic distances in relatable terms. This opens up a way to measure the universe that aligns with our observations, allowing astronomers to map out the structure of galaxies, clusters, and even the large-scale framework of the universe itself. Lastly, the speed of light plays a vital role in the theories of relativity, fundamentally changing our understanding of space and time. According to Einstein's theory, as objects move closer to the speed of light, they experience time differently than those at rest. This aspect deepens our understanding of how the fabric of space-time interacts and shapes the cosmic landscape. So the speed of light is not just about how we observe the universe, it fundamentally influences our very understanding of reality itself. Breakthroughs in optics have profoundly transformed the field of astronomy, enabling scientists to peer deeper into the universe than ever before. The journey began with the invention of the telescope in the early 17th century, which allowed astronomers to observe celestial objects with unprecedented clarity. By bending light through lenses or mirrors, telescopes have revealed details of distant planets, stars, and galaxies, paving the way for major discoveries and advancements in our understanding of the cosmos. Modern optical technology has continued to evolve, leading to the development of larger and more sophisticated telescopes. Reflective telescopes, for instance, utilize mirrors to gather light and eliminate some of the distortions associated with lenses. These advancements enable astronomers to capture light from fainter objects, such as distant galaxies, which were once invisible to early observers. This ability to see more of the universe has significantly expanded our knowledge of cosmic structures, including the vast tapestry of the night sky. The introduction of adaptive optics has further revolutionized astronomy. By compensating for the distortion caused by Earth's atmosphere, this technology allows telescopes to produce much sharper images. As a result, astronomers can observe celestial objects with incredible precision, investigating finer details of planetary surfaces and uncovering new features in the nebulae that were previously indistinguishable. In addition to telescopes, breakthroughs in sensor technology have played a crucial role. The arrival of charge-coupled devices, which capture light more efficiently than traditional photographic plates, has enhanced the ability to gather and analyze data. With these advancements, astronomers can create detailed mappings of celestial regions, study the composition of stars, and even track the movements of exoplanets around distant suns. Collectively, these developments in optics have propelled astronomy into a new era, where the universe seems more accessible and mysterious discoveries await at every turn. Defining the age of the universe is a fascinating journey through the cosmos, combining advanced science with a bit of cosmic detective work. At its core, scientists arrive at the universe's age through several key methodologies, primarily focusing on the expansion of the universe, the cosmic microwave background radiation, and observations of ancient stars. One of the fundamental ways we measure the universe's age is by understanding how fast it is expanding. This concept is encapsulated in Hubble's law, discovered by Edwin Hubble, which states that galaxies are moving away from us at speeds proportional to their distance. By measuring these distances and speeds, scientists can determine the rate of expansion, known as the Hubble constant. The current estimates suggest the universe is approximately 13.8 billion years old, which is the time since the Big Bang, the event that marked the birth of our universe. Another crucial methodology involves studying the cosmic microwave background radiation, which is the afterglow of the Big Bang, filling the entire universe. This radiation provides a snapshot of the universe when it was just about 300,000 years old. By analyzing the tiny fluctuations in temperature within this background radiation, researchers can infer the conditions at that early time, which helps refine our estimate of the universe's age. The observations made by satellites like the European Space Agency's Planck satellite have been instrumental in solidifying our understanding of this cosmic relic. Finally, astronomers also look at the oldest stars in our galaxy, specifically globular clusters. These ancient stellar communities contain stars that have existed for nearly as long as the universe itself. By measuring how quickly these stars are exhausting their nuclear fuel, scientists can estimate their ages, providing a sort of cosmic clock that aligns with the ages derived from other methods. Together, these methodologies paint a coherent picture, allowing us to appreciate not just the age of the universe, but the intricate processes at play that led to the cosmos as we know it. The concept of an expanding universe fundamentally reshapes our understanding of time. As we observe distant galaxies moving away from us, we discover that the universe is constantly stretching, a phenomenon sparked by the Big Bang some 13.8 billion years ago. This expansion signifies that the universe is fraught with change, and it indicates that time itself is not a constant. Instead, it becomes a dynamic element intertwined with the fabric of space. The implications of this expansion lead us to consider how time is not just a backdrop to events, but rather an integral part of the cosmic narrative. For example, the farther we look into space, the deeper we delve into the past. Light from distant galaxies takes billions of years to reach us, so when we observe them, we are seeing them as they were at the time the light was emitted. This connection means that studying these remote celestial bodies allows us to trace the history of the universe, revealing how it has evolved over vast stretches of time. Moreover, the expansion affects how we perceive the sequence of events in the cosmos. Different regions of the universe may experience time at varying rates due to factors like gravity, a concept rooted in Einstein's theory of relativity. In regions of strong gravitational pull like near black holes, time can move more slowly compared to areas with weaker gravitational forces. This nuances our understanding of time as not only relative, but also varied across different environments in the universe. The expanding universe invites us to rethink time as a fluid and ever-evolving entity, rather than a mere clock ticking away. It's a reminder that in the grand scheme of the cosmos, our experience of time is intricately linked to the very fabric of space itself, emphasizing that every moment we experience is part of a much larger tapestry that stretches across the universe's vast history. Timescales in the universe are vast and can seem almost unfathomable compared to our daily experiences. The universe itself is around 13.8 billion years old, shaped by events like the Big Bang and the formation of galaxies, stars, and planets. When we consider such immense time periods, our lives, which span only a few decades, can feel fleeting. This difference in time perception invites us to reflect on our place in the cosmos and the legacy we leave behind. In our daily lives, we tend to measure time in much shorter increments, seconds, minutes, days, and years. Yet understanding the long time scales of the universe can influence how we think about change and progress. For instance, evolutionary processes that created the diversity of life on Earth unfold over millions of years, reminding us that noteworthy change often takes time beyond our immediate experience. This perspective can foster patience and appreciation for gradual growth, both in nature and in our personal endeavors. Moreover, our understanding of cosmic time impacts technologies that guide our lives. For example, satellites rely on precise timing systems to communicate and navigate. Engineers take into account various factors, including the time dilation predicted by Einstein's theory of relativity, which states that time moves differently under various gravitational forces. Such scientific insights, based on cosmic understanding, become the backbone of everyday technologies, although we may not always realize it. Finally, by connecting the small moments of our lives to the grand timeline of the universe, we cultivate a sense of awe and wonder. This larger context can inspire how we view events like our birthdays or anniversaries, not merely milestones of years lived, but also markers within an ongoing story that stretches across the cosmos. Embracing this cosmic viewpoint can enhance our appreciation for life, reminding us that even the smallest moments are part of a much bigger narrative. The temporal nature of the universe is intricately intertwined with cosmic events, shaping not just how we measure time, but also how we perceive its passage. One of the most significant ways cosmic events influence time is through the phenomenon of gravitational time dilation. According to Einstein's theory of relativity, time passes differently depending on the strength of gravitational fields. Near massive objects like black holes or neutron stars, time moves more slowly compared to regions of weaker gravity, like our own planet. This means that a clock near a black hole would tick at a different rate than one far away. This mesmerizing interplay shows us that time is not a fixed backdrop, but rather a dynamic fabric influenced by the cosmos. Another profound influence comes from the expansion of the universe itself. As galaxies drift apart, the very fabric of space-time stretches, leading to phenomena such as the redshift, which is the change in light from distant galaxies as they move away from us. This expansion not only illustrates the universe's ongoing evolution, but also points to how events like supernova explosions can alter the timing of light reaching us from these celestial bodies. The further away an object is, the longer its light takes to reach Earth, and the history we observe is stretched over vast periods. Knowing this allows us to glimpse the universe's past, granting us insights into its age and story. Cosmic events also play a role in marking the vast epochs that define the universe. For instance, the formation of stars and galaxies, or the collisions between them, ripple through time, impacting everything in their vicinity. Such events can result in the creation of new elements, influencing not only the physical structure of the universe, but also the evolution of solar systems, including our own. These moments can signify when certain cosmic milestones occur, helping us grasp the timeline of the universe from its explosive beginnings in the Big Bang to the ongoing processes of star formation and galaxy evolution. Lastly, the alignment of cosmic events can have intriguing effects on our perceptions and measurements of time. Events like eclipses or the regular cycles of pulsars, which are rapidly rotating neutron stars emitting beams of radiation, allow us to clock time with extraordinary precision. Pulsars, for instance, can serve as cosmic clocks, helping astronomers test the fabric of space-time itself. By studying these phenomena, we uncover layers of complexity in our understanding of time, revealing that it is not merely a human construct, but something that dances in concert with the universe's grand narrative. Each cosmic event adds depth to our understanding, reminding us that the universe is ever active and timelessly unfolding. Measuring cosmic time across vast distances presents unique challenges that stem from the very nature of our universe. One significant issue is the vastness of space itself. The distances between celestial objects can span billions of light years, meaning the light we observe from them has taken an immense amount of time to reach us. This creates a sort of time delay where we see these objects not as they are now, but how they appeared long ago. This issue complicates our understanding of cosmic events, as we must constantly account for the light travel time when interpreting what we observe. Furthermore, our measurements can be influenced by the expansion of the universe. Since the time of the Big Bang, the cosmos has been stretching, which affects how we perceive distances and time intervals. Objects that are receding from us can appear to move more quickly due to this expansion. In fact, the rate at which this expansion occurs is still being studied, leading to discussions among scientists about the accuracy of our measurements of cosmic time. This introduces a level of uncertainty when trying to establish a timeline of the universe's history. Another challenge lies in the nature of cosmic events themselves. Many significant events in our universe, such as supernovae or gamma-ray bursts, can occur over varying timescales. These events might be brief from our perspective, but they release vast amounts of energy and can carry intelligence about the state of the universe back to us. Determining their exact age and pinning down how long ago they occurred requires precise measurements and an understanding of their inherent variability. Lastly, the concept of cosmic time is further complicated by gravitational effects. According to Einstein's theory of general relativity, gravity can influence the passage of time. The stronger the gravitational field, the slower time runs. This means that time is not an absolute constant across the universe. Instead, it's a variable dependent on location and the influence of mass. All these factors combine to make measuring cosmic time a deeply intricate challenge, showcasing the complexities of our universe and our quest to understand it. Humanity's relationship with the night sky has undergone a fascinating transformation throughout history. In ancient times, our ancestors relied on the stars for navigation and agricultural practices. They looked up with wonder as celestial bodies marked the changing of seasons, guiding them in their daily lives and rituals. These early cultures often attributed deities and myths to constellations, creating rich stories that connected them to the cosmos. As civilizations advanced, so did our understanding of the night sky. The Greeks, for instance, began to document their observations methodically, laying the groundwork for astronomy. They recognized patterns in the movements of stars and planets, leading to the development of models that tried to explain their behaviors. This intellectual curiosity sparked profound questions about the universe, fueling explorations of philosophy and science that would influence generations. With the advent of the telescope in the 17th century, humanity's view of the cosmos dramatically changed. Astronomers like Galileo revealed worlds beyond our own, challenging long-held beliefs about the place of Earth in the universe. The vastness of space became more apparent, and new discoveries such as moons orbiting Jupiter and the phases of Venus ignited excitement and a deeper sense of connection to the universe. The night sky transformed from a series of myths into a realm of scientific inquiry. In recent times, technological advancements have expanded our exploration even further. Satellites and spacecraft allow us to peer deeper into the cosmos than ever before. We have captured images of distant galaxies and detected exoplanets beyond our own solar system. Today, our relationship with the night sky evokes feelings of curiosity, awe, and humility. With the growing recognition of our universe's vastness, we are reminded of our small yet significant place within it, fostering a collective sense of responsibility for our planet and its future. The stars and the vast cosmos have long captured the imagination of artists, musicians, and writers. From ancient civilizations to modern times, the celestial sphere has influenced countless creative expressions. Stars, with their shimmering brilliance, represent beauty and mystery, offering an endless source of inspiration for those who view them. The night sky itself has served as a canvas for artists, a backdrop for tales of adventure, and a muse for musicians who seek to capture its essence in melody. In literature, celestial bodies often symbolize deeper themes such as hope, the unknown, and the search for meaning. Think of the romantic poets who gazed at the stars and penned verses that echoed their feelings of longing and existential reflection. These writings evoke a sense of connection to something greater than ourselves, with stars serving as a reminder of our place in the universe and our aspirations to reach beyond earthly limitations. Books featuring space exploration and fantastical worlds encourage readers to dream of possibilities beyond our own experiences. Music, too, finds its foundation in the cosmos. Many composers have used the imagery of stars and galaxies to craft symphonies that evoke the grandeur and beauty of the universe. The haunting soundscapes capture the essence of cosmic wonder, inviting listeners to lose themselves in the melodies that seem to speak directly to the mysteries of space. Popular songs referencing the night sky or celestial themes resonate deeply, often touching on feelings of love, loss, or yearning for something unattainable. Visual artists, from painters to sculptors, have depicted celestial scenes that inspire awe. The work of artists like Vincent van Gogh, whose swirling skies seem alive with energy, captures this ethereal beauty. Starry nights become more than mere representations. They become meditations on the nature of reality. These artistic interpretations not only showcase the grandeur of the universe, but also reflect our inner thoughts, emotions, and the age-old human quest to understand our surroundings. In this interplay between art and the cosmos, we find a profound connection that transcends time, reminding us of our shared curiosity about the universe beyond our planet. Mythology and folklore offer fascinating insights into how different cultures interpret the universe and their place within it. Throughout history, people have looked to the skies, observing the stars, the moon, and the sun, which inspired stories that explained celestial phenomena in relatable human terms. These narratives often provided frameworks for understanding complex ideas such as creation, existence, and the natural world around them. Consider ancient cultures like those of the Greeks and the Egyptians, who devised intricate myths to explain the movements of celestial bodies. The Greek god Helios drove the sun across the sky in his chariot, while the Egyptians revered Ra, the sun god, as a powerful deity who battled darkness each night. These stories not only personified natural forces, but also illustrated humanity's deep curiosity about the cosmos, transforming the night sky into a canvas of storytelling. Moreover, these tales often reflected the values and beliefs of their societies. For instance, creation myths frequently depicted the emergence of the cosmos from chaos or darkness, mirroring notions of order, balance, and harmony. Such narratives served as more than mere entertainment. They were vehicles for teaching moral lessons and understanding life's mysteries. They provided a shared identity and a sense of connection among those who heard them, binding generations together through the shared experience of exploring the unknown. In modern times, while our scientific understanding has dramatically evolved, the essence of these stories remains significant. They act as a bridge between our ancient past and contemporary thought. Many scientists and philosophers still draw on these age-old narratives to communicate complex ideas about the universe, reminding us that while we seek facts and figures, the human experience of wonder is universal. Mythology and folklore are not just relics of cultural history. They are reflections of our ongoing quest to understand the vast, enigmatic universe we inhabit. Contemplating the cosmos can evoke a wide range of psychological effects in individuals, often leading to profound changes in perspective and emotional responses. For many, gazing up at the night sky or pondering the vastness of the universe instills a sense of awe and wonder. This feeling often transcends simple curiosity. It can spark a deep appreciation for the beauty of existence and the intricate complexities of the universe. Such moments can expand our sense of self, reminding us that we are part of something far larger than our individual lives. Additionally, contemplating the cosmos can induce feelings of humility. When faced with the scale of the universe, with its billions of galaxies and countless stars, individual troubles can seem smaller in comparison. This humbling effect can lead to a greater sense of connectedness with humanity, as people recognize that we share this world and the universe with others. Such realizations can foster a nurturing perspective, encouraging compassion and a desire to care not only for ourselves, but also for each other and our planet. Exploring cosmic themes can also serve as a catalyst for reflection and existential questioning. Many individuals find themselves considering their place in the universe and the significance of life itself. These reflections can lead to a renewed appreciation for everyday moments or a search for purpose and meaning. Sometimes, this journey can bring about anxiety or discomfort as people grapple with existential questions, but it can also foster personal growth by encouraging deeper self-understanding and exploration of one's beliefs and values. Finally, the psychological impact of contemplating the cosmos can be therapeutic. Engaging with the mysteries of the universe offers a form of escape from daily stresses, providing a comforting reminder of the beauty and complexity of life. Many find solace in stargazing or studying astronomy, as these activities allow for quiet reflection and a break from the fast-paced world. In this way, the cosmos becomes not just an object of study, but also a source of inspiration and peace that enhances our emotional well-being. The exploration of the universe has a unique power to inspire unity among humanity. Throughout history, space exploration has brought together individuals from various countries, cultures, and backgrounds, all working toward a common goal: understanding the cosmos. This shared endeavor breaks down barriers, allowing us to realize that, despite our differences, we share the same planet and face similar challenges in our quest for knowledge. When we look up into the night sky, we are reminded of our place in the vast universe. The pursuit of exploration calls for collaboration and cooperation, as seen in monumental projects such as the International Space Station. Scientists, engineers, and astronauts from around the world contribute their expertise to push the boundaries of our understanding. This cooperation fosters a sense of collective identity, uniting us as citizens of Earth committed to discovering more about the universe we inhabit. Moreover, the discoveries made through space exploration often highlight the interconnectedness of our existence. For instance, studying other planets enhances our understanding of Earth's climate and ecosystems. Learning how various celestial phenomena affect each other invites us to consider our own actions and their impact on our planet. This perspective promotes responsibility not just for ourselves, but for future generations as well, as we together navigate the challenges posed by climate change and resource management. Lastly, as we venture further into the cosmos and imagine the possibilities that lie beyond, we cultivate a shared sense of wonder and curiosity that transcends cultural divides. Whether it's the hope of finding life on other planets or unraveling the mysteries of dark matter, these aspirations can inspire people across the globe to come together. Our exploration of the universe serves as a reminder that while we may be different, we are all part of this incredible journey through space and time, united in our search for understanding. Astronomers today face a multitude of challenges as they strive to unravel the mysteries of the universe. One of the most pressing issues is the sheer vastness of space itself. The universe is mind-bogglingly large, containing billions of galaxies, each with billions of stars. This immense scale means that even with the most powerful telescopes, catching a glimpse of distant objects can be like trying to spot a single grain of sand on a sprawling beach. Another significant hurdle is the speed of light, which limits our observations to the very distant past. Light takes time to travel from celestial bodies to Earth, meaning that when we view distant galaxies, we see them not as they are now, but as they were when the light first left them. This time delay can lead to misconceptions about the current state of the universe and complicates our understanding of its evolution over billions of years. Additionally, astronomical observations can be heavily affected by the Earth's atmosphere. Factors such as light pollution and atmospheric turbulence distort images from ground-based telescopes, making it difficult to capture clear data. To counter this, astronomers have turned to space-based telescopes like the Hubble Space Telescope and the recently launched James Webb Space Telescope. But launching and maintaining these instruments requires significant resources and technological advancement. Lastly, the cosmos holds many secrets that challenge our existing theories. Phenomena such as dark matter and dark energy remain largely mysterious, comprising most of the universe's content, yet difficult to detect and study. As our tools and theories evolve, so too do the challenges, pushing astronomers to continuously adapt and innovate in their pursuit of understanding our vast universe. Funding and resources are pivotal in shaping the landscape of astrophysics research. They determine not only what projects scientists can embark on, but also the scope and scale of those investigations. With limited budgets, research teams must prioritize their questions, often gravitating towards pursuits that promise immediate results or align with funding sources' objectives. Public institutions and private organizations frequently provide grants and financial support, guiding researchers toward areas that may not only advance science, but also capture public interest or address societal challenges. For instance, studies on climate change and its cosmic connections enjoy robust funding due to their relevance. In contrast, certain fundamental inquiries, like the nature of dark matter, might struggle to secure resources despite their theoretical importance. The availability of cutting-edge technology further influences research directions. Facilities equipped with advanced telescopes or particle accelerators can unlock new frontiers. A well-funded laboratory can explore high-energy astrophysics, delving into phenomena like black holes or supernova, while others may focus on more niche investigations due to financial constraints. Consequently, disparities in funding can lead to uneven advancements across different areas of astrophysics. While the pursuit of knowledge drives scientists, the reality of funding acts as both a guiding star and a limiting factor. The intricate dance between available resources and research ambitions ultimately shapes the progress and evolution of our understanding of the universe, revealing just how intertwined economics and exploration truly are. Political factors play a crucial role in shaping international space exploration collaborations. One significant aspect is national priorities. Countries often view space exploration as a reflection of their technological prowess and leadership on the global stage. This competition can foster partnerships, but it can also create barriers if nations perceive each other as rivals. For instance, when significant achievements in space are tied closely to national identity or prestige, nations may be reluctant to share resources or knowledge, fearing they might lose their competitive edge. Additionally, political stability or instability can impact collaborations. In times of turmoil, countries might prioritize domestic issues over international partnerships. This can lead to abrupt shifts in funding or support for space missions. Conversely, nations with stable governments are more likely to sustain long-term commitments to international projects, building trust and cooperation over time. Take the International Space Station as an example. It has persisted through various political climates because participating countries recognize the mutual benefits of collaboration in exploration. Furthermore, diplomatic relationships are integral to these collaborations. Countries that maintain strong diplomatic ties are more inclined to work together on ambitious space missions. In contrast, strained relations can result in reduced collaboration or entire projects being shelved. The partnerships formed under organizations like the United Nations Office for Outer Space Affairs illustrate how international dialogue can pave the way for joint missions that benefit a broader community rather than just individual nations. Finally, the expansion of commercial space activities introduces a new dynamic. Private companies are now key players in space exploration, which can complicate the political landscape. Governments must navigate their relationships with private entities and ensure that national interests align with commercial goals. Ultimately, while science thrives on collaboration, it is equally influenced by the political will and relationships that govern how nations interact on the final frontier. As scientists delve into the mysteries of the universe, they often stumble upon certain paradoxes that provoke deep thought and debate. One of the most famous is known as the Fermi paradox, which ponders the question, if the universe is so vast with billions of stars and potentially habitable planets, why have we not yet encountered evidence of extraterrestrial life? This paradox captures the juxtaposition between the high probability of other civilizations existing and the stark absence of clear signs that they are out there. It suggests that either intelligent life is exceedingly rare or that we are missing something significant in our search. Another compelling paradox is the Olbers paradox, which questions why the night sky is dark if the universe is infinite, eternal, and filled with stars. The reasoning is that if the universe had existed forever, there would be enough stars to light up every corner of the sky. The resolution lies in understanding the finite age of the universe, as well as the expansion that causes distant light to redshift beyond the visible spectrum. This begs the question about the nature of light and how we perceive the universe around us. The information paradox related to black holes presents another intriguing puzzle. When objects fall into a black hole, it seems that all information about those objects is lost forever, contradicting the fundamentals of quantum mechanics, which state that information cannot be destroyed. How can something vanish completely when the laws of physics suggest it must persist in some form? This paradox has led to heated debates about the nature of reality and the foundations of our understanding of the universe. Lastly, there exists the dark energy paradox. We can observe that the universe is expanding, and it's doing so at an accelerating rate, yet our understanding of cosmic forces is still incomplete. Dark energy is the mysterious force driving this acceleration. While scientists can measure its effects, they are still grappling with its origins and how it fits into the larger picture of cosmology. Each of these paradoxes not only showcases the limits of our current knowledge, but also highlights the relentless quest for understanding that defines the field of cosmology. Public perception of science plays a significant role in shaping the landscape of scientific research. When people value and trust scientific inquiry, they often support funding and policies that promote advancements in technology and medicine. This positive perception can lead to increased investment from both government and private sources, paving the way for groundbreaking discoveries. Conversely, skepticism or distrust in scientific findings can hinder the progress of research by diminishing support and resources. One critical aspect of public perception is the role of communication. How scientists convey their findings and engage with the public can determine whether people view science as a trustworthy endeavor. Effective communication fosters understanding, bridging the gap between complex research and everyday life. When scientists are able to explain their work in clear terms, it resonates more with the audience, often resulting in greater public interest and engagement. This connection can inspire future generations to pursue careers in scientific fields, ensuring a pipeline of talent and innovation. Moreover, the media also influences public perception significantly. When scientific research makes headlines, it has the potential to shape conversations and even government policy. However, sensationalized reporting or the oversimplification of findings can lead to misunderstandings. This means scientists must not only conduct rigorous research, but also actively participate in discussions about its implications. Engaging with communities and being responsive to public concerns ensures that science remains relevant and respected. Ultimately, the relationship between science and society is symbiotic. As the public engages with scientific topics, they contribute to setting research agendas and priorities. Scientists, in turn, benefit from a supportive society that values knowledge and fosters inquiry. As we move forward, nurturing this relationship will be crucial for addressing global challenges and advancing our understanding of the universe. As humanity gazes beyond our home planet, long-term goals for establishing a lasting presence in space take shape. These ambitions are fueled by an innate desire to explore, understand, and eventually inhabit worlds beyond Earth. Pioneering these efforts are organizations like NASA, the European Space Agency, and private enterprises such as SpaceX. The dream is not just to visit other celestial bodies, but to create sustainable communities in places like the Moon and Mars. One of the primary milestones is the Artemis program, which seeks to return humans to the Moon and establish a long-term lunar presence by the end of this decade. The Moon serves as a proving ground where we can develop and test technologies while learning to live off the land. This concept, often referred to as in situ resource utilization, would involve using lunar materials to support human activities. This approach is vital for future missions that aim to extend further into the solar system. Mars is often seen as the next frontier. Plans are being laid for crewed missions to the Red Planet in the 2030s, with visions of building base habitats where humans can safely live and work. Scientists believe that with the right technology, we could harness Martian resources to support these colonies. These endeavors also open up the fascinating possibility of terraforming, the notion of transforming Mars to make it more Earth-like, a bold challenge that captivates our imaginations. Ultimately, these efforts reflect a broader goal: to ensure the survival of humanity in case of global catastrophes on Earth. By becoming a multiplanetary species, we can spread our wings beyond the confines of our atmosphere, explore new worlds, and safeguard our legacy. This dream inspires not just scientists and explorers, but every person who looks up at the stars and wonders what lies beyond. Space colonization holds the potential to fundamentally reshape our understanding of the universe in several profound ways. First, by expanding human presence beyond Earth, we could establish new observation points. Each new location in space provides an opportunity to view celestial phenomena from different perspectives. For instance, a colony on Mars could allow us to directly study the interactions between solar radiation and the Martian atmosphere, offering insights that cannot be gained from telescopes situated only on Earth. Moreover, through colonization, we can engage in long-term scientific experiments that are impossible on our home planet. For example, colonies in the harsh environments of Mars or the Moon could allow us to explore the effects of reduced gravity on biological systems over generations. Such studies might not only reveal how life adapts in extraterrestrial environments, but could also inform us about human physiology and the possibility of long-term space travel, which is crucial for further exploration of the cosmos. Additionally, establishing human settlements in space could spark technological advancements that revolutionize our capabilities across the universe. Developing life support systems, sustainable agriculture in alien soils, and advanced energy sources will require innovation. These technologies could have applications back on Earth, potentially solving current problems, such as climate change or food scarcity, while also preparing us for deeper space exploration. Finally, colonization challenges our philosophical and ethical perspectives on humanity's place in the universe. As we venture into the cosmos, we must confront questions about stewardship of other worlds, our responsibility to potential alien ecosystems, and the nature of life itself. Engaging with these questions could deepen our understanding not only of the universe, but also of ourselves, reshaping our beliefs and aspirations as we reach out into the vast unknown. The potential colonization of other planets raises profound ethical questions that spark lively discussions among scientists, ethicists, and the public alike. At the heart of these inquiries lies an essential consideration: the moral implications of altering an extraterrestrial environment. If we were to colonize another planet, would we have the right to change its landscape, disrupt potential ecosystems, or even connect with any form of extraterrestrial life? These questions challenge our understanding of exploration and stewardship of worlds beyond our own. Furthermore, think about the concept of ownership. Just as land on Earth has a complex history of ownership disputes, The same dilemma extends to our celestial neighbors. Who has the right to claim territory on Mars, for instance? Nations, corporations, or perhaps humanity as a whole? This question is compounded by the absence of established legal frameworks governing these potential new homes. The Outer Space Treaty of 1967 limits the claim of ownership over celestial bodies, yet as we stand on the brink of exploration, the need for a more refined moral and legal understanding grows urgent. Moreover, we must consider the ethical implications of transferring our social, political, and economic structures to another world. Would a colony reflect the best of human society, or would it recreate the inequalities and issues we struggle with on Earth? As we expand into the cosmos, there's a distinct responsibility to not repeat past mistakes, ensuring that new societies promote equity and sustainability rather than privilege and exploitation. Finally, the idea of colonization also stirs questions about our intentions and the broader impacts of our actions. Are we colonizing other planets to escape our problems, or to genuinely expand our understanding of life and the universe? As we ponder these ethical dilemmas, it becomes clear that any steps we take beyond our home planet must be approached with a deep sense of responsibility, respect, and an awareness of the potential consequences for both ourselves and any worlds we might inhabit. Each decision carries weighty implications for the future of humanity and our role as caretakers in the universe. Advancements in propulsion technology present exciting possibilities for interstellar travel, the dream of reaching other star systems beyond our own. Traditional chemical rockets, while effective for space travel within our solar system, are insufficient for journeys that could last decades or even centuries. To explore the stars, researchers and engineers are looking into innovative propulsion methods that could drastically reduce travel times and make such missions feasible. One of the most promising avenues is nuclear propulsion, particularly nuclear thermal and nuclear electric systems. Nuclear thermal propulsion uses heat from a nuclear reactor to propel a spacecraft, offering a much greater efficiency than conventional rockets. This technology could enable faster trips to Mars and even pave the way for deeper space exploration. Meanwhile, nuclear electric propulsion harnesses electricity generated by a reactor to power ion thrusters, which produce thrust by expelling ions at high speeds. This method, while offering lower thrust, would permit continuous acceleration over long durations, making it ideal for interstellar missions. Another exciting prospect is the concept of solar sails, which utilize the pressure of sunlight to push large, lightweight craft across the vastness of space. These sails could theoretically reach substantial fractions of the speed of light over time, allowing for travel to nearby stars in a matter of decades. Coupled with advancements in materials science, developing durable and efficient sails becomes increasingly plausible. As these technologies progress, the blueprint for reaching other stars transforms from the theoretical to the attainable. Moreover, researchers are investigating concepts like antimatter propulsion and fusion drives. Antimatter, the most efficient fuel known, offers potential for immense thrust, but poses significant technical and safety challenges. On the other hand, fusion drives aim to replicate the processes that power the Sun, providing a potentially sustainable and powerful source of energy for Starship engines. Although many of these ideas are still in the experimental phase, each step forward in propulsion technology brings us closer to the reality of interstellar travel, igniting the imagination and curiosity of generations to come. Space tourism represents an exciting bridge between everyday life and the vast expanse of the cosmos. This burgeoning industry allows ordinary people, not just seasoned astronauts, to experience the thrill of space travel. As more individuals embark on these journeys, they bring back stories, images, and newfound enthusiasm about the universe. This first-hand experience can ignite a collective curiosity, making the mysteries of space more relatable and accessible. With the spectacle of rocket launches and the awe of viewing Earth from above, space tourism can spark a broader public interest in astronomy and space science. It has the potential to captivate new audiences, especially younger generations, who might see their future in exploring the stars. Through social media and personal narratives, travelers can share what it's like to float in weightlessness or witness the curvature of our planet, painting a vivid picture of life beyond Earth. This immediate connection can inspire many to delve deeper into the wonders of the universe. Moreover, space tourism can enhance educational initiatives around space exploration. As interest grows, more resources may be allocated to science education and research. Programs that involve schools, community groups, and educational institutions could emerge, aiming to deepen understanding and appreciation for space. This grassroots enthusiasm can lead to a broader cultural shift, where space is seen not only as a scientific frontier, but also as a realm of adventure and possibility. Ultimately, space tourism could reshape our relationship with the cosmos. By making the experience of space travel more commonplace, it democratizes access to the final frontier. It encourages more people to wonder about what lies beyond our atmosphere, fueling many conversations about the future of humanity in space and reinvigorating our collective imagination as we ponder our place in the universe. Our understanding of the universe profoundly influences our perspective on environmental challenges here on Earth. By studying the cosmos, we gain insights into the delicate balance that sustains life on our planet. This knowledge drives home the idea that Earth's resources are finite, reminding us that we are a small part of a vast, interconnected system. The realization that Earth is a unique oasis in the fabric of the universe encourages a sense of responsibility for its preservation. Moreover, exploring celestial phenomena helps us grasp the fragility of ecosystems. For instance, by examining the climate of other planets, scientists can draw comparisons with Earth's own climate dynamics. Understanding how atmospheric changes occur, as seen with Venus and Mars, offers valuable clues about the impacts of pollution and greenhouse gases on our own planet. The lessons learned from the universe serve as stark reminders of what can happen if we ignore the warning signs at home. Additionally, advancements in technology developed for space exploration often find applications in environmental monitoring and conservation efforts. Satellite imagery, for instance, allows us to track deforestation, monitor ocean health, and study changes in wildlife habitats. These tools provide critical data that help us address pressing environmental issues in real time, guiding our efforts to combat climate change, resource depletion, and habitat destruction. In contemplating our place in the universe, we also come to appreciate the shared fate of life on Earth. Just as celestial bodies dance in harmony, so too must we learn to coexist with our environment and one another. Understanding the universe not only fosters a sense of wonder, but also a collective call to action, inspiring us to work toward a sustainable future for generations to come. Cosmic disasters like asteroid impacts may seem like scenarios from a science fiction story, but they are real threats to humanity. Throughout Earth's history, sizable asteroids have struck our planet, leading to significant and often catastrophic changes. One of the most famous examples is the asteroid impact that is widely believed to have contributed to the extinction of the dinosaurs approximately 66 million years ago, marking the end of the Cretaceous period. When a massive object collides with Earth, it can release immense energy, equivalent to millions of atomic bombs, generating scorching heat and shockwaves that can cause widespread devastation. The immediate effects of an asteroid impact include intense heat, fiery explosions, and tsunamis if it strikes an ocean. Following the collision, debris can be thrown into the atmosphere, blocking sunlight for extended periods. This phenomenon, known as an impact winter, could lead to drastic temperature drops and severely disrupt weather patterns. Such changes can jeopardize global food supplies, leading to famine and societal collapse. The loss of sunlight can also halt photosynthesis, devastating plant life and fundamentally altering ecosystems. In addition to these environmental threats, the psychological and societal impacts of a cosmic disaster can be profound. If a significant asteroid were on a collision course with Earth, it would trigger a global response. Governments would likely mobilize resources and attempt to devise ways to either mitigate the impact or evacuate populations. The uncertainty and fear surrounding such an event could lead to panic quickly. The failure to address the threat adequately could leave humanity vulnerable, creating chaos even before the asteroid strikes. Despite these daunting prospects, it is essential to note that scientists engage in monitoring near-Earth objects. These efforts aim to identify and track asteroids that could pose a risk. Missions dedicated to studying asteroids and devising potential deflection strategies are currently underway. As we deepen our understanding of these cosmic phenomena, we can better prepare for, and perhaps even prevent, the potential devastation they may bring. securing a safer future for humanity amidst the cosmic ballet of our universe. As inhabitants of Earth, we carry a profound responsibility to protect our planet, not only for ourselves but for future generations and the delicate balance of life that exists here. Earth is the only known refuge for life in the vast cosmos, and it harbors an incredible diversity of ecosystems and creatures, many of which are still undiscovered. Every species, no matter how small, plays a role in the intricate web of life, and the loss of even one could have ripple effects throughout our environment. Our actions have far-reaching consequences, from the emissions that contribute to climate change to the pollution of our oceans and the depletion of natural resources. Every decision we make impacts the planet's health. The ongoing changes to the Earth's climate are not merely localized, they affect weather patterns, sea levels, and biodiversity all over the globe. As stewards of this unique world, we must strive to minimize our ecological footprint and promote sustainability. In the grand scheme of the universe, Earth is rare. While we've discovered thousands of exoplanets, none are quite like our home. The combination of water, atmosphere, and life-supporting conditions makes Earth an exceptional place. Protecting our planet safeguards not only our immediate environment, but also our place in the universe. It sparks curiosity about the possibility of life beyond our solar system and compels us to consider our role as guardians of this fragile oasis in space. Engagement in conservation efforts, advocating for renewable energy, and supporting policies that prioritize ecological wellness are all critical steps we can take. By fostering a culture of awareness and action regarding environmental issues, we help ensure that Earth continues to thrive. Ultimately, our responsibility extends beyond Earth itself. It's about preserving the legacy of this planet for countless future explorers and scientists, inspiring them with a world that pulses with life and possibility long into the future. As we turn our eyes to the vastness of space, the study of other planets offers profound insights that can significantly inform our approach to environmental preservation here on Earth. Take, for instance, the Martian landscape, which tells a story of a planet that once boasted a vibrant atmosphere and liquid water. Researchers have uncovered evidence suggesting that catastrophic climate changes led to Mars losing its atmosphere and becoming the arid desert we see today. This serves as a powerful reminder of how sensitive planetary climates really are, pushing us to consider our own planet's fragile balance. On Venus, conditions are extraordinarily harsh, marked by thick clouds of sulfuric acid and surface temperatures hot enough to melt lead. The runaway greenhouse effect seen on Venus acts as a chilling forecast for Earth if we continue down our current path of unchecked carbon emissions. Learning from Venus highlights the dire consequences of ignoring early warning signs, urging us to take more seriously the challenges posed by climate change. By examining such extreme examples, we gain a clearer perspective on the potential outcomes of environmental neglect. In addition, the moons of Jupiter and Saturn, like Europa and Enceladus, present fascinating case studies in a different way. These icy moons harbor hidden oceans beneath their frozen surfaces, teeming with potential for life. Their environments remind us of the importance of biodiversity and untouched ecosystems. They encourage us to reflect on the irreplaceable value of natural habitats on Earth, reinforcing the idea that by protecting our ecosystems, we might safeguard our future and possibly even life beyond our planet. Ultimately, the lessons gleaned from our celestial neighbors compel us to act responsibly. They inspire a commitment to preserving the delicate balance of our environment, urging us to become better stewards of the Earth. By understanding the dynamics of other planets, we can harness that knowledge to guide our efforts in tackling climate challenges, protecting biodiversity, and ensuring that our blue planet remains a vibrant home for generations to come. Cosmic events offer a profound perspective on the fragility of life here on Earth. When we look up at the night sky, we're actually peering into a vast universe filled with powerful phenomena, such as supernovae, gamma-ray bursts, and asteroid impacts. These events, often occurring light years away, remind us of the overwhelmingly chaotic nature of the cosmos, a reminder that celestial forces can unleash energy that dwarfs human existence in scale and magnitude. For instance, consider a supernova, which occurs when a massive star exhausts its nuclear fuel and collapses under its own gravity. This dramatic explosion not only obliterates the star, but can also significantly affect nearby planets and systems. If such a stellar event were to occur close enough to Earth, it could potentially alter our atmosphere and disrupt life as we know it. This highlights the delicate balance in which life thrives, underscoring how external cosmic events can influence our existence in ways we cannot fully control. Furthermore, the study of past cosmic events, such as the asteroid that contributed to the extinction of the dinosaurs, serves as a historical reminder of life's vulnerability. A single colossal object impact could create widespread destruction, leading to collapsing ecosystems and mass extinctions. Such events remind us that, while life is resilient and capable of remarkable adaptation over time, it remains susceptible to sudden, unforeseen disruptions from the universe. In reflecting on these cosmic occurrences, we gain a deeper appreciation for our own planet's fragile atmosphere and its delicate ecosystems. They teach us not only about the hazards we face, but also the importance of protecting our environment. By understanding our place in the cosmos and the potential threats that loom, we become more aware of the intricate threads that connect all life on Earth and the universe's boundless mysteries. Cosmology, the study of the universe's origins, evolution, and eventual fate, has seen some incredible discoveries that have reshaped our understanding of reality. One of the most groundbreaking was the observation that the universe is expanding. In the early 20th century, astronomer Edwin Hubble revealed that distant galaxies were moving away from us, implying that the universe was not static but ever expanding. This discovery led to the formulation of the Big Bang theory, which proposes that the universe began with a monumental explosion around 13.8 billion years ago from a singular, immensely hot and dense point. Another transformative discovery was the identification of cosmic microwave background radiation. In the late 1960s, scientists Arno Penzias and Robert Wilson stumbled upon this faint glow permeating the universe. This radiation is a remnant from the early days of the universe, acting as a snapshot of its infancy just a few 100,000 years post-Big Bang. Its presence provided strong evidence supporting the Big Bang theory and revealed the universe's hot and dense origins, drastically altering our perspective on cosmic history. The advent of dark matter and dark energy has further revolutionized our understanding of the cosmos. Although dark matter cannot be seen directly, its existence is inferred from its gravitational effects on visible matter, such as stars and galaxies. This elusive substance makes up about 27% of the universe, while dark energy, which accounts for about 70%, drives the accelerated expansion of the universe. Together, these enigmatic components of the cosmos have raised fundamental questions about the nature of reality and the future of our universe. Finally, advancements in observational technology have opened new frontiers in cosmology. Telescopes like the Hubble Space Telescope and more recently the James Webb Space Telescope allow us to observe distant galaxies and study their formation and evolution. This has revealed a rich tapestry of cosmic history and created a deeper understanding of how structures in the universe develop over billions of years. Each of these discoveries has not only deepened our knowledge of the universe's mechanics, but has also sparked an enduring curiosity about the cosmos that continues to inspire scientists and enthusiasts alike. The advent of quantum physics has profoundly shifted our understanding of the universe, transforming how we perceive reality itself. Before the advent of quantum theory, classical physics dominated our explanations of the physical world, describing particles as solid objects moving through space like tiny balls. However, quantum physics introduced a radically different perspective, revealing a universe that is more complex and nuanced than we ever imagined. In the quantum realm, particles can simultaneously exist in multiple states, a concept known as superposition. This means that an electron, for instance, doesn't occupy one specific location, but rather exists in a cloud of probabilities until it is measured. This challenges traditional notions of determinism, suggesting that at the fundamental level, the universe operates on principles of uncertainty. The implications of these ideas extend far beyond just particles. They influence our understanding of light, energy, and even the fabric of space and time. Quantum entanglement is another fascinating concept that has altered our perspective. Particles can become entangled in such a way that the state of one immediately influences the state of another, no matter how far apart they are. This phenomenon prompted scientists to rethink their ideas about locality and separateness in the universe. It raises profound questions about the interconnectedness of everything and encourages us to think of the universe as a more unified whole than previously recognized. Moreover, the principles of quantum physics have paved the way for technological advancements that touch our daily lives. From the development of semiconductors to the innovations in quantum computing, these scientific breakthroughs expand our understanding of reality while also providing practical benefits. As we continue to explore the quantum world, we are likely to uncover even more mysteries and insights that will further reshape our understanding of the cosmos. Citizen scientists have become indispensable players in the field of cosmic research, contributing significantly to our understanding of the universe. These enthusiastic individuals, often without formal training in science, participate in a wide variety of projects that help expand our knowledge about celestial phenomena. From analyzing data collected by powerful telescopes to tracking the movements of asteroids, citizen scientists harness the power of community collaboration to delve into the mysteries of the cosmos. One remarkable example of citizen science is the Galaxy Zoo project, where volunteers classify hundreds of thousands of galaxies based on their shapes. This initiative has led to discoveries that even professional astronomers may not have made alone. By engaging the general public in tasks that require human intuition, such as distinguishing between different galaxy types, researchers have discovered new patterns and anomalies in the data that enhance our understanding of galaxy formation and evolution. Another captivating contribution comes from varied platforms like Planet Hunters, where citizen scientists analyze light curves from stars to identify potential exoplanets. These dedicated volunteers sift through huge amounts of data, looking for small dips in brightness that indicate a planet might be crossing in front of its host star. Their observations have led to the discovery of numerous exoplanets, expanding our knowledge of potentially habitable worlds outside of our solar system. Engaging the public in scientific inquiry not only accelerates research, but also fosters a deeper appreciation for science among participants. Each contribution from citizen scientists enriches the collective understanding of the universe while igniting curiosity and excitement about the cosmos. Their role is a reminder that scientific exploration knows no boundaries, and everyone has something valuable to offer in the quest for knowledge about our vast and mysterious universe. Collaboration between disciplines like physics, astronomy, and philosophy can significantly enrich our understanding of the universe. Each field brings its unique perspective and methodologies, creating a more comprehensive approach to exploring cosmic questions. For instance, while physics provides the fundamental laws governing matter and energy, astronomy uses observations from telescopes to see the universe in all its grandeur. Philosophy then steps in to ponder the implications of these findings and to question the very nature of existence and reality itself. When scientists from different disciplines work together, they can address questions that no single field could answer alone. For example, astrophysicists may use complex theories to explain phenomena like black holes, but it takes a philosophical lens to explore the implications of what these phenomena mean for the concepts of time and space. Likewise, philosophers can frame questions about the universe that inspire physicists to develop new theories and experimental designs. This synergy can lead to groundbreaking discoveries and new ways of thinking about the universe. Moreover, interdisciplinary collaboration encourages the development of new tools and technologies. Techniques developed in physics for experiments can advance astronomical observations, while philosophical inquiry can guide ethical considerations in scientific research. Together, these disciplines can tackle the most profound questions about the universe, such as the origins of time, the possibility of parallel universes, or the nature of consciousness itself. Ultimately, this collaboration sparks a richer dialogue about existence, pushing the boundaries of human knowledge. It helps us not only uncover the mechanics of the universe, but also understand our place within it. By bridging the gap between empirical evidence and philosophical reasoning, we can venture deeper into the mysteries of the cosmos, fostering a profound curiosity that drives scientific exploration forward. The discovery of extraterrestrial technology would undoubtedly reshape our understanding of the universe and our place within it. Imagine realizing that advanced civilizations exist beyond our planet. This revelation could challenge our fundamental beliefs about life and intelligence, suggesting that we are not alone in the cosmos. It would evoke questions about the nature of these civilizations, their histories, and their technological advancements. Such an event would also provoke intense scientific curiosity and research efforts. Scientists would scramble to study and decipher any technology that might be found. This could lead to groundbreaking innovations on Earth, as we might learn new methods of energy production, propulsion, or communication that far exceed our current capabilities. The field of technology and engineering could be revolutionized overnight, opening doors to inventions we cannot yet even imagine. However, there would be significant philosophical, ethical, and political implications to consider as well. The knowledge that we share the universe with other intelligent beings could lead to discussions about cooperation and communication strategies. How do we reach out? What protocols should we establish for engagement? The potential for conflict could also arise, forcing governments and organizations to rethink their approaches to international relations and security in an expanded cosmic context. Ultimately, the discovery of extraterrestrial technology could be both an exhilarating and daunting prospect. It would compel us to grapple with questions about existence, evolution, and our responsibilities as stewards of our planet and potential galactic neighbors. In this new paradigm, humanity would be called to unite in exploring not only what lies beyond Earth, but also what this means for our future and identity as a species. International collaborations play a crucial role in the exploration of our universe, enabling scientists and researchers from various countries to come together, share resources, and pool their expertise. This collective approach allows different nations to contribute unique strengths, be it in technology, funding, or scientific knowledge. By collaborating, they can work on complex questions that might be too challenging for any single organization or country to tackle alone. One emblematic example of such collaboration is the International Space Station, a remarkable achievement of humanity that involves multiple countries contributing to its research and upkeep. Scientists aboard the station conduct experiments that explore the effects of microgravity on various biological systems, contributing to our understanding of life itself and advancing applications in medicine and technology. Such insights benefit all partner nations and humanity at large. Moreover, large astronomical projects like the Large Hadron Collider in Switzerland or the upcoming James Webb Space Telescope illustrate how global teamwork enables the sharing of knowledge and resources. These projects rely on scientists from around the world working on connecting data, interpreting findings, and fostering advancements that would be impossible without diverse perspectives and expertise. Finally, international collaborations foster a culture of unity and shared purpose in scientific exploration. In a world where the cosmos can seem vast and isolating, scientists rallying together across borders emphasizes that the quest for knowledge is a universal endeavor. By sharing both achievements and challenges, they inspire future generations to explore and wonder about the universe, nurturing a spirit of curiosity that transcends geographical boundaries. The scientific community actively engages in addressing misconceptions about space through education, outreach, and public engagement programs. One of the primary ways they do this is by producing educational materials such as books, documentaries, podcasts, and interactive websites. These resources are designed to provide accurate information and clarify common misunderstandings about astronomical phenomena, such as the nature of black holes, the vacuum of space, and the false notion that humans can directly see stars from the Earth without any atmospheric interference. Moreover, scientists often participate in public lectures and community events where they share their knowledge and answer questions. This face-to-face interaction helps create a dialogue, allowing scientists to correct myths and provide insight from their expert perspectives. Such events foster a sense of curiosity and can ignite a passion for science in attendees who may otherwise hold on to misconceptions about the cosmos. These interactions shine a light on the importance of critical thinking, inviting listeners to ask questions and explore the universe more deeply. Social media platforms also serve as valuable tools for outreach. Many scientists and institutions utilize these channels to disseminate information quickly and engage with a larger audience. They often address trending myths or popular misconceptions surrounding space and astronomy. debunking inaccuracies with well-researched facts. This not only counters misinformation, but also amplifies the voices of scientists, making their work more accessible and relatable to the general public. Finally, collaborative efforts among scientists, educators, and communicators ensure the continuation and expansion of these initiatives. Programs in schools, partnerships with science museums, and involvement in global campaigns promote accurate scientific literacy. By combining various approaches, the scientific community is working towards creating a more informed public, one that appreciates the wonders of space with accurate knowledge. This ongoing endeavor showcases both the importance of science communication and the intrinsic beauty of our universe. Public engagement initiatives play a crucial role in fostering interest in astrophysics by making the complex and often distant concepts of the universe accessible and relatable. These initiatives can take various forms, such as interactive exhibitions, public lectures, stargazing events, and community science projects. By presenting astrophysics in a hands-on manner, audiences can directly experience the wonders of the cosmos, which fuels their curiosity and deepens their understanding. One effective approach is through storytelling. Engaging narratives that weave together the latest discoveries with human experiences can capture imaginations. For instance, highlighting the journey of a scientist from a small town who contributed to a major discovery can inspire young minds and show that anyone can pursue a career in science. Additionally, when scientists share their personal motivations and challenges, it humanizes the field and resonates with the audience on a more personal level. Furthermore, utilizing digital platforms and social media can amplify these outreach efforts. Online webinars, interactive social media campaigns, and educational videos allow for a broader reach, especially among younger audiences. By leveraging these technologies, astrophysics can enter living rooms and classrooms, sparking interest in ways that traditional forms alone may not achieve. These initiatives also create a community around science, where people can discuss, ask questions, and share ideas. Engaging local schools and communities fosters collaboration and helps cultivate a new generation of science enthusiasts. When the public feels involved in the exploration of astrophysics, it encourages lifelong learning and a greater appreciation for the universe, ensuring that the quest for knowledge continues to thrive across all age groups. Throughout the history of space exploration, many missions have faced setbacks, each leaving behind important lessons for future endeavors. One of the most significant lessons is the critical importance of thorough testing and validation. In earlier missions, many spacecraft were launched without sufficient trials. For instance, the failure of the Mars Climate Orbiter in 1999 was attributed to a simple metric conversion error, exacerbating the need for rigorous checking processes. By examining these past mistakes, engineers have learned that establishing strict protocols and conducting extensive simulations can prevent avoidable mishaps. Additionally, communication and collaboration have emerged as key factors in the success of cosmic missions. Past failures have shown that when teams work in silos, critical information can be overlooked. The loss of the Columbia Space Shuttle in 2003 underscored just how vital it is for engineers, scientists, and mission control to share insights and concerns openly. Thus, modern missions emphasize interdepartmental teamwork, creating a culture where every voice is heard and valued, ultimately enabling better decision-making. Furthermore, these setbacks have illuminated the necessity for adaptable missions. The journey to understanding and exploring space is unpredictable, often filled with unforeseen challenges. The Spirit and Opportunity rovers, for instance, were initially designed for a 90-day mission. However, their remarkable resilience allowed them to exceed expectations, operating for years. This experience taught mission designers to build flexibility into their plans, allowing for adjustments that can extend a mission's lifespan and enhance discoveries. Lastly, there's been an increased focus on public engagement and transparency following past failures. When missions do not succeed, it's important to communicate those lessons to the public openly. This approach fosters a more informed society while nurturing a sense of shared adventure in space exploration. By learning from the past and applying these insights, the field continues to advance, paving the way for future successes that inspire generations to look up and dream. The sharing of data across international borders plays a crucial role in accelerating scientific advancements. When researchers collaborate globally, They can pool their resources, expertise, and findings, creating a more comprehensive understanding of complex problems. For instance, data related to climate change, disease outbreaks, or astronomical discoveries benefits greatly from the diverse perspectives and analytical methods that various countries bring to the table. Consider the ongoing fight against diseases like COVID-19. The rapid exchange of genomic data allowed scientists from multiple nations to identify and track variants, develop vaccines, and set public health strategies effectively. Without this collaboration, progress would have been slower, with researchers potentially duplicating efforts instead of building upon each other's work. Instant access to shared data not only enhances speed, but also improves the quality of research. Moreover, sharing data fosters inclusivity in science. Researchers from less wealthy nations gain access to valuable information, enabling them to contribute meaningfully to global scientific dialogues. This democratization of knowledge enhances innovation, as ideas from diverse cultures and scientific traditions can lead to breakthroughs that might not have emerged in isolation. In conclusion, international data sharing establishes a thriving collaborative environment that propels scientific progress. By allowing scientists to work together, regardless of location, we foster a richer, more effective search for solutions to some of the world's most pressing challenges. The interconnectedness of modern science exemplifies how collaboration can lead to discoveries that benefit all of humanity. Art serves as a powerful bridge between complex scientific ideas and the general public, particularly when it comes to the vast and intricate universe we inhabit. While science often relies on data and equations to convey its findings, art transcends language and can evoke emotions, making difficult concepts more approachable. Through various forms of creative expression, artists illuminate scientific principles, inviting viewers to engage with these ideas on a personal level. For instance, visual art like paintings, sculptures, and installations can portray abstract theories of cosmology, such as the nature of black holes or the expanse of galaxies. These artworks transform often dry mathematical ideas into visually stimulating representations. When an audience views a vivid cosmic scene, they not only appreciate the aesthetic but also gain insights into the scale and complexity of the universe. This visual representation aids in demystifying scientific content, allowing a deeper understanding without the intimidation of technical jargon. Additionally, performance art and multimedia experiences can further enrich this communication. Imagine theatrical performances that interpret the life cycle of stars or dance that visually narrates the movement of celestial bodies. These forms create memorable experiences that resonate emotionally, making the underlying science more relatable. By transforming complex ideas into stories or movements, art captivates attention and fosters a lasting memory of the scientific concepts being presented. Lastly, collaborative projects between scientists and artists often yield enlightening results that push the boundaries of both fields. As artists explore scientific themes, they can ask questions that scientists might overlook, leading to new perspectives. In this symbiotic relationship, art not only communicates science but inspires curiosity, encouraging audiences to seek further understanding of the universe we share. In the end, art becomes a vital tool, ensuring that the wonders of the cosmos are accessible to all, no matter their background or prior knowledge of science. Film and literature serve as powerful mirrors reflecting our understanding of the cosmos, often interpreting complex scientific ideas through the lens of human experience. These art forms have the unique ability to weave together storytelling and science, inviting audiences to ponder the vastness of space, the nature of existence, and our place in the universe. For instance, the dramatic elements found in works like Arthur C. Clarke's 2001: A Space Odyssey illustrate how humanity's journey through space introduces profound philosophical questions about evolution, intelligence, and the future of our species. Moreover, thematic explorations in films like Interstellar address concepts such as time dilation, black holes, and the fabric of space-time, making high-level physics accessible to general audiences. They manage to bridge the gap between scientific theories and emotional narratives, allowing viewers to connect with abstract concepts on a personal level. This blend of science and storytelling encourages viewers not just to think about the cosmos, but to feel something about it, its beauty, its danger, and its mystery. Literature has similarly played a crucial role in shaping our understanding of the universe. Works like Carl Sagan's Cosmos and Neil deGrasse Tyson's Astrophysics for People in a Hurry popularize complex ideas, making them digestible and relatable. These narratives explore themes of awe and curiosity, often drawing attention to the remarkable interconnectedness of all things and inspiring a sense of wonder about what lies beyond our blue planet. Through imaginative language and vivid descriptions, authors ignite the spark of curiosity about the universe within their readers. As a result, both film and literature do more than present scientific facts. They encourage introspection and foster a deeper appreciation for the cosmos. They compel us to question not merely what we know, but what we do with that knowledge. The stories we tell through these mediums help define our understanding of the universe and our role within it, posing fundamental questions that resonate across time and space, reminding us that we are part of a larger narrative unfolding in the cosmos. Visual representations of the universe have a profound impact on public perception, shaping how we see our place in the cosmos. Images from powerful telescopes and space missions present the universe in stunning colors and intricate details. These visuals make abstract ideas like distant galaxies and the vastness of space tangible. They invite curiosity and wonder, which is essential for understanding our universe. Additionally, these representations often serve as a bridge between scientific research and public engagement. Stunning images can make complex concepts like black holes or the expansion of the universe more relatable. They capture attention and can even inspire interest in scientific inquiry, encouraging people to learn more about astrophysics and cosmology. This spark of curiosity might lead someone from simply admiring a photograph to exploring courses in science or even pursuing a career in that field. Moreover, visuals can sometimes mislead public perception. For instance, images can create an overwhelming sense of grandeur which can overshadow the harsh realities of space, such as its inhospitable nature. This romanticized view can lead to misconceptions about our universe and how accessible it is to humanity. Balancing awe with scientific reality becomes crucial as we convey complex ideas through stunning imagery. Visual representations of the universe serve as both a guide and a gateway. They not only captivate our imagination, encouraging us to ponder our origins and the mysteries of existence, but they also drive a deeper interest in the scientific disciplines that seek to unravel these mysteries. Through powerful imagery, we begin to understand that we are part of a much larger story, filled with unknowns and endless possibilities. Creativity is often viewed as the spark that ignites scientific discovery and innovation. It allows scientists to look beyond the established norms and question the status quo. This imaginative thinking leads to new hypotheses, fresh approaches, and inventive methods for solving complex problems. For instance, many breakthroughs in various fields, from medicine to technology, stem from the ability to envision possibilities that others may not yet see. One of the key aspects of creativity in science is the ability to connect seemingly unrelated concepts. When researchers can draw parallels between different disciplines, they often discover innovative solutions that transform their fields. A mechanical engineer might find inspiration in nature, leading to biomimicry, where designs in technology mimic systems found in living organisms. This interdisciplinary bridge not only fosters creativity, but also accelerates technological advancements by integrating diverse perspectives. Moreover, creativity is fundamental in the way theories are developed and tested. Scientists must often navigate through uncertainty and ambiguity. Encouraging creative thinking allows them to embrace failure as a stepping stone toward success, rather than seeing it as a setback. When experiments do not go as planned, it is creative thinking that helps researchers reframe their methods, adjust their research questions, and ultimately refine their focus on what truly matters. Creativity serves as a crucial engine driving scientific inquiry and innovation. By blending imaginative thinking with rigorous experimentation, scientists can inspire breakthroughs that enhance our understanding of the universe and improve our everyday lives. The interplay of creativity and science is not just about coming up with new ideas. It's about fostering a culture that values curiosity, exploration, and the relentless pursuit of knowledge. The intersection of science and art opens a vibrant dialogue about our understanding of the universe, revealing deeper layers of meaning and inspiration. Art has the power to communicate complex scientific ideas in ways that resonate emotionally with people. For instance, the breathtaking visuals of galaxies and cosmic landscapes can spark the imagination, inviting us to explore concepts like the vastness of space, the complexity of time, and the beauty of natural laws. In this way, art becomes a bridge that helps us engage with ideas that might otherwise feel abstract or distant. Science and art together challenge us to think critically and creatively. Artists draw on scientific discoveries to inform their work, leading to innovative interpretations of the universe. Consider how artists like Ansel Adams used photography to capture the majesty of Earth's landscapes, igniting respect for nature and a greater understanding of ecological systems. Similarly, contemporary artists may use concepts from quantum physics or genetics to inspire their creations, sparking conversations about the implications of these discoveries on our lives. This blend not only enhances public interest in scientific progress, but also underscores the role that creativity plays in scientific inquiry. Furthermore, this relationship enriches our cultural narrative by making science more accessible. When artists illustrate scientific phenomena or involve themselves in scientific projects, they translate complex information into something tangible. This can inspire curiosity and passion, attracting individuals who might not otherwise engage with science. Imagine an art installation that depicts the life cycle of stars, or an exhibit that brings the human genome to life through visual media. These experiences can shape our collective appreciation for the universe while grounding scientific principles in personal interpretation. Ultimately, the fusion of science and art expands our cultural narrative, encouraging a holistic view of knowledge. It reminds us that the quest for understanding the universe is not solely a pursuit of empirical knowledge, but an enriching journey that encompasses intuition, emotion, and creativity. Through this rich tapestry, we gain a more profound insight into our place in the cosmos and the stories that connect us all. The origins of the universe have long fascinated scientists and thinkers alike, leading to several theories that provide different perspectives on this profound mystery. The most widely accepted explanation is the Big Bang theory, which posits that the universe began as an incredibly hot, dense point roughly 13 billion years ago. Over time, this point expanded rapidly, leading to the cosmos we observe today, filled with galaxies, stars, and planets. Key evidence supporting this theory includes the cosmic microwave background radiation, which serves as a relic of that early hot state, and the observed redshift of distant galaxies, consistent with an expanding universe. In contrast to the Big Bang theory, the steady-state theory offers an entirely different view. This concept suggests that the universe has no beginning or end, but is eternally expanding while maintaining a constant average density. In this model, as galaxies move apart, new matter is continuously created to fill the gaps. However, as observational evidence, particularly the discovery of the cosmic microwave background radiation, grew stronger, the steady-state theory waned in popularity and is now largely considered outdated. Another intriguing explanation is the concept of cosmic inflation. This theory builds upon the Big Bang model by proposing that the universe underwent an exponential expansion in the very first moments after the Big Bang, smoothing out the irregularities and providing a framework for the uniformity we observe today. Inflation theory accounts for the uniform temperature of the cosmic microwave background and helps explain the large-scale structure of the universe, including the distribution of galaxies. Lastly, we have the multiverse theory, which posits that our universe might be just one of many existing parallel universes. Each of these universes could have different physical laws and constants, potentially offering a diverse array of realities. While this theory stretches our understanding of reality and is still speculative, it invites questions about what might lie beyond the boundaries of our observable universe, adding further intrigue to the quest to understand our origins. The Big Bang theory emerged as the leading explanation for the origins of the universe through a series of groundbreaking discoveries in the early 20th century. Initially in the 1920s, astronomer Edwin Hubble observed that galaxies are moving away from us, suggesting that the universe is expanding. This observation contradicted the then popular static universe model and hinted at a dynamic, evolving cosmos. Hubble's findings provided crucial evidence that something extraordinary must have occurred to shape the universe as we know it. One of the key components of the Big Bang theory is the cosmic microwave background radiation. In the mid-20th century, scientists Arno Penzias and Robert Wilson accidentally discovered this faint glow permeating the universe. This uniform radiation is seen as the afterglow of the hot, dense state of the universe shortly after the initial explosion, corroborating the Big Bang model. The existence of this background radiation supports the idea that the universe began in an extremely hot and compact state, which has since been cooling as it expands. Moreover, the abundance of light elements in the universe, such as hydrogen and helium, further solidifies the Big Bang theory. According to the theory, these elements were formed during the first moments after the explosion, a process known as nucleosynthesis. Observations of elemental abundances across the cosmos align remarkably well with predictions from the Big Bang model, reinforcing its credibility. Finally, the combination of observational evidence and theoretical developments led to the widespread acceptance of the Big Bang theory. It effectively explained how the universe has evolved over billions of years, providing a cohesive narrative of its beginnings and ongoing expansion. While alternative theories have surfaced, none have matched the Big Bang model's ability to consistently explain and predict the universe's features, making it the cornerstone of modern cosmology. In the very first moments after the Big Bang, the universe was an incredibly hot and dense place. Imagine a space teeming with energy, where particles were in constant collision, forming and annihilating in an instant. This primordial soup consisted mainly of fundamental particles like quarks, electrons, and neutrinos, all racing around at nearly the speed of light. Temperatures soared to unimaginable levels, exceeding trillions of degrees Celsius. These extreme conditions were not just vibrant, they laid the groundwork for everything that would subsequently evolve in our cosmos. As time unfolded, the universe began to expand rapidly in a process known as inflation. This expansion was extraordinarily swift, stretching the fabric of space itself. In the first few microseconds, something remarkable occurred. Quarks coalesced to form protons and neutrons. These particles, the building blocks of atomic nuclei, began to emerge from the chaotic energy. As the universe continued to cool, it fostered an environment conducive to these particles combining, paving the way for the formation of simple nuclei. A few minutes into this expansion, the universe had cooled sufficiently for protons and neutrons to unite and form light elements such as hydrogen and helium. This era, known as Big Bang nucleosynthesis, was short-lived but crucial. Around 20 minutes after the Big Bang, most of the helium and a small amount of lithium were born. Interestingly, this early composition of the universe has remained largely unchanged, making these light elements the foundations upon which later stars and galaxies would form. Finally, after several 100,000 years of expansion and cooling, the universe entered a stage called recombination. During this period, electrons combined with protons to create neutral hydrogen atoms. This process allowed photons, or light particles, to travel freely for the first time. The release of these photons created what we now observe as the cosmic microwave background radiation, a faint glow that permeates our universe, echoing the very origins of all we see today. This radiation provides a snapshot of the universe at about 380,000 years old and serves as a cornerstone for our understanding of cosmic history. Scientists study the conditions of the early universe by piecing together evidence from several key areas, including cosmic observations, theoretical models, and experimental physics. One of the most significant tools in this investigation is the cosmic microwave background, or CMB. This is the faint glow of radiation that fills the universe, a remnant of light from when the universe was just 380,000 years old. Observing the CMB allows scientists to glimpse the conditions shortly after the Big Bang, providing vital clues about its temperature, density, and fluctuations that eventually led to the formation of galaxies. In addition to cosmic radiation, scientists use advanced telescopes to observe the light from distant galaxies. The light from these galaxies has taken billions of years to reach us, offering a window into the distant past of the universe. As astronomers look deeper into space, they are essentially looking further back in time, allowing them to study the evolution of different structures in the universe and compare them to theoretical predictions about the early universe's conditions. High-energy particle physics also plays a crucial role in understanding the universe's early moments. Large particle colliders like the Large Hadron Collider are instrumental in recreating the extreme conditions that were present just after the Big Bang. By colliding particles at unprecedented speeds, scientists can produce temperatures and energies similar to those found in the early universe. This helps them study fundamental forces and particles, providing insights into how the universe evolved from a hot, dense state to the cosmos we see today. Moreover, theoretical physics engages in complex modeling, using equations and simulations to predict how the universe should behave under different conditions. These models are continually tested against observational data, allowing scientists to refine their understanding. The synergy between observation and theory paints a clearer picture of the universe's infancy, revealing a vibrant tapestry that continues to intrigue and inspire. By embracing multiple disciplines, scientists unlock the mysteries of our universe's beginnings, illuminating the grand narrative of cosmic evolution. The cosmic microwave background radiation, often referred to as CMB, serves as a vivid echo of the universe's infancy, revealing insights that have fundamentally shaped our understanding of its origins. This faint glow, omnipresent in all directions of the sky, is the afterglow of the Big Bang, a brief moment when the universe was a hot, dense soup of particles. As the universe expanded and cooled, it reached a point approximately 370,000 years after that explosive beginning, allowing light to shine freely for the first time. What we now see as the CMB is this light, stretched into the microwave range due to the ongoing expansion of the universe. Discoveries surrounding the CMB have unveiled critical information about the age, composition, and evolution of the universe. Particularly significant is the fact that the CMB is remarkably uniform, but it also contains slight fluctuations. These fluctuations represent variations in density that eventually led to the formation of galaxies and large-scale structures we observe today. Detailed measurements, particularly those from the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have honed our understanding of these irregularities, allowing scientists to derive the universe's rate of expansion and its overall geometry. The CMB also confirmed key elements of the Big Bang theory. For instance, the precise ratio of hydrogen to helium in the early universe, inferred from CMB observations, aligns with predictions made by nuclear physics about the conditions following the Big Bang. This consistency not only reinforces our theoretical models, but also illustrates the universe's remarkable and intricate balance. Moreover, the CMB has helped identify mysterious components of the universe, such as dark matter and dark energy. By studying how matter was distributed in the early universe, researchers learned that ordinary matter accounts for only a fraction of the universe's total energy density. The remaining portions are attributed to these enigmatic forces, integral to understanding how our universe has evolved and how it may continue to unfold. The revelations prompted by the cosmic microwave background radiation have not only forged a clearer picture of our universe's past, but also laid a foundation for future exploration in cosmology. Galaxies are remarkable structures that emerge from the vast cosmic web, a tapestry of dark matter and gas that permeates the universe. This web consists of vast filaments and sheets of dark matter, which act as gravitational scaffolding. Over time, small fluctuations in density within this web attract gas and matter. As this material begins to clump together, the gravitational forces grow stronger, leading to the formation of galaxies. It's a breathtaking process stretching across billions of years, where the universe transitions from a hot, dense state to the rich variety of galaxies we see today. The shape of a galaxy is influenced by several dynamic processes. Initially, as gas and stars come together, they conserve angular momentum, spinning faster as they collapse under gravity. This can lead to the formation of spiral galaxies, which are characterized by their distinct arms and a flat disk shape. On the other hand, galaxies that undergo significant mergers with other galaxies tend to be more irregular or elliptical. These collisions can trigger intense bursts of star formation, radically altering the structure and appearance of both galaxies involved. Interactions between galaxies are a key factor in their evolution and shape. When two galaxies collide, their gravitational forces disrupt each other's structures, often resulting in a new galaxy shape altogether. This can create features such as tidal tails, which are streams of stars and gas pulled out of the galaxies. Over time, these interactions can transform the galaxies, merging them into larger, more massive structures, ultimately resulting in galaxies that may appear smooth and rounded or display unusual shapes. Additionally, the environment plays an essential role in shaping galaxies. Those nestled within dense clusters experience different gravitational influences than isolated galaxies. The competition for space and resources can stifle star formation in clustered galaxies, leading to older, redder stars dominating their populations. In contrast, galaxies in less crowded areas may continue to create new stars for much longer, resulting in a vibrant array of colors and shapes. This intricate dance of formation and interaction highlights the complexity and beauty of galaxies within our universe. To understand the formation of galaxies, we must first grasp the crucial roles of dark matter and dark energy. Dark matter, which makes up about 23% of the universe, is invisible and does not emit light, but it has significant gravitational effects. As the universe expanded after the Big Bang, dark matter began to clump together under the influence of gravity. These clumps formed the scaffolding around which ordinary matter, made up of atoms, accumulated. This gravitational attraction was essential in creating the large-scale structure of galaxies we observe today. Dark energy presents a different yet equally important aspect of cosmic evolution. Comprising approximately 73% of the universe, dark energy is thought to be responsible for its accelerated expansion. This means that while dark matter pulls together the matter to form galaxies, dark energy pushes galaxies apart, influencing their movement and the overall shape of the cosmos. If not for dark energy, dark matter's clumping behavior would dominate the dynamics of the universe. If not for dark energy, dark matter's clumping behavior would dominate the dynamics of the universe, leading to a very different outcome. Together, dark matter and dark energy set the stage for galaxy formation and evolution. Initially, as dark matter formed dense regions in the early universe, ordinary matter began to coalesce in these areas, eventually leading to the birth of stars and galaxies. Over billions of years, these galaxies continued to evolve, influenced by interactions with other galaxies and the vast expanding fabric of dark energy driving them apart. In this complex cosmic dance, dark matter provides the necessary structure for galaxy formation, while dark energy acts as the unseen force shaping their future. As researchers delve deeper into these enigmatic components of the universe, we come closer to unraveling the mysteries of how galaxies form and how they will continue to evolve into the distant future. Galaxies, the majestic collections of stars, gas, dust, and dark matter, undergo a fascinating evolutionary journey throughout the vast expanse of the universe. The process of galaxy formation and evolution begins with small fluctuations in the density of matter shortly after the Big Bang. These deviations led to the gradual accumulation of mass, eventually forming primordial clouds of gas and dust that collapsed under their own gravity, birthing the very first stars. As galaxies begin to take shape around the young stars, they enter a stage known as the protogalactic phase. During this time, they can experience significant interactions with nearby matter. Galaxies are not static. They engage in processes like merging with other galaxies or absorbing smaller ones. These interactions can trigger bursts of star formation, leading to growth and the diversification of galaxy types. For instance, while spiral galaxies retain a flat disk structure, elliptical galaxies result from prolonged interactions that smoothed out their star distribution. As galaxies mature, they enter a phase characterized by the slowing of star formation. This is commonly seen in older galaxies, where their available gas diminishes due to star formation activity, leading to a gradual transformation into what we recognize as elliptical shapes. Interestingly, some galaxies, especially those in dense clusters, can undergo processes like strangulation, where they lose their gas supply, stifling new star formation and exhibiting subtle shifts in their characteristics. The final stages of a galaxy's evolution can take millions to billions of years, marked by subtle changes over long durations. Galaxies can become more evolved. They shift from vibrant star-making machines to more subdued bodies, shifting into a brighter but less active state. Even in their twilight, galaxies may find themselves interacting with others, drawing them into a cosmic ballet lasting eons, further complicating and enriching their backstory in the grand tapestry of the universe. As the universe itself continues to expand and evolve, so too do galaxies, forever spinning through the intricate dance of cosmic history. The study of distant galaxies offers us a unique window into the origins of our universe. Light from these galaxies takes billions of years to reach us, meaning we are essentially looking back in time. When astronomers observe these faraway celestial bodies, they are seeing them as they were in their infancy, often hundreds of millions or even billions of years after the Big Bang. This perspective allows scientists to piece together a timeline of cosmic evolution and gain insights into the conditions that shaped the universe we inhabit today. One of the key aspects scientists examine is the formation and evolution of galaxies. By studying the light emitted by these distant galaxies, researchers can determine their age, composition, and structure. Early galaxies formed when the universe was still quite young, and by analyzing their characteristics, we can learn how matter was distributed and how the first stars ignited. This understanding helps to paint a picture of the formative processes that led to large-scale structures in the universe. In addition, distant galaxies can reveal the chemical makeup of the early universe. As stars form and die, they produce heavier elements, which are then dispersed into space, contributing to the birth of new stars and planets. By examining the light spectra from these galaxies, scientists can identify the elements present and their abundance. This information sheds light on the processes of stellar evolution and provides clues about the history and evolution of the cosmos. Finally, the evolution of distant galaxies also informs our understanding of dark matter and dark energy, two of the universe's most mysterious components. The behavior and distribution of galaxies across vast distances can reveal the influence of these unseen forces on cosmic structure. By studying how galaxies interact and cluster, astronomers can trace the effects of dark matter on visible matter, offering deeper insights into the fundamental nature of our universe. Through the lens of these ancient galaxies, we continue to unravel the mysteries of the cosmos. Galactic mergers are fascinating cosmic events that significantly change the structure and future of galaxies involved. When two galaxies collide, their tremendous gravitational forces interact, leading to a dynamic dance of stars, gas, and dark matter. Over time, this interaction can dramatically alter the distribution and morphology of stars within both galaxies. For example, spiral galaxies can become elliptical galaxies, characterized by a smoother, more rounded appearance due to the chaotic gravitational effects. The most immediate consequence of a galaxy merger is the reshuffling of stars. This can lead to new star formation as clouds of gas and dust implode under gravitational pressure, igniting bursts of starbirth. The merging process can create spectacular regions of star formation, sometimes referred to as starburst galaxies, where the rate of stellar creation can increase dramatically. Yet this vibrant phase is temporary. As the galaxies settle into their new structure, the rate of star formation eventually slows. These mergers don't just shape the stars themselves, they also have profound effects on the galaxy's supermassive black holes at their centers. When galaxies collide, their black holes can draw closer together, sometimes resulting in a spectacular merger of these enigmatic entities. This process can generate intense energy release, often seen in the form of gravitational waves, offering a glimpse into the nature of these cosmic powerhouses. Finally, the ultimate fate of the merged galaxies is heavily influenced by their initial conditions and the angle of their collision. Some merged galaxies will evolve into a stable, larger galaxy, while others could become the seeds for new galactic structures or even trigger further mergers. As we observe the expansive universe, every merging galaxy tells a story of cosmic evolution, revealing our universe as an ever-changing tapestry of creation and destruction. A black hole is one of the universe's most fascinating and perplexing phenomena. At its core, a black hole is a region in space where the gravitational pull is so intense that nothing, not even light, can escape from it. This is why black holes appear black against the backdrop of the cosmos. The boundary surrounding a black hole is called the event horizon, and it marks the point of no return. Once something crosses this boundary, it is doomed to be pulled inexorably into the black hole. The formation of a black hole typically begins with a massive star. Stars are born from clouds of gas and dust through the process of nuclear fusion. During their lifetime, these stars burn enough helium to become supergiants, leading to an explosive finale known as a supernova. When a massive star exhausts its nuclear fuel, it can no longer support itself against the force of gravity. This collapse can result in a supernova, leaving behind a core that may collapse further into a black hole if it is heavy enough. Black holes can also form through different processes, including the merger of two neutron stars or the merging of smaller black holes. When such massive objects collide, they can create a more massive black hole, further amplifying the gravitational pull. This process significantly contributes to the population of black holes in the universe. Some experts theorize that there may even be supermassive black holes at the centers of almost all large galaxies, including our own Milky Way, containing millions to billions of solar masses. The study of black holes challenges our understanding of fundamental physics and the very nature of space and time. While they might seem like alien entities, they play a crucial role in the dynamics of our universe and continue to be a source of awe and deep scientific inquiry. As we explore the mysteries of black holes, we uncover more about the universe's evolution, the behavior of matter under extreme conditions, and even the potential for new physics beyond our current understanding. Detecting and studying black holes may seem like a daunting task, given that these cosmic entities do not emit light and are therefore invisible to traditional telescopes. Scientists have developed sophisticated techniques to infer their presence and study their behavior by observing the effects they have on their surroundings. The key lies in their gravitational influence and the light produced by material falling into them. One of the primary methods for detecting black holes involves observing the motion of nearby stars. When a star orbits an invisible object, its path reveals crucial information about that object's mass. For instance, if a star is seen moving rapidly around a seemingly empty space, scientists can deduce that a black hole may be present. Notable examples include black holes in binary systems, where a visible companion star gives off light that can be analyzed to understand the properties of its hidden partner. Another intriguing approach involves studying the radiation emitted by accretion disks. When matter falls into a black hole, it spirals around and forms a disk, heating up to incredibly high temperatures due to friction and gravitational forces. This process produces X-rays, which can be detected by specialized space telescopes. Observing these high-energy emissions allows scientists to gather data about the black hole's mass and spin, providing insights into its behavior and the fundamental physics at play. In recent years, groundbreaking advancements have been made, such as the Event Horizon Telescope capturing the first image of a black hole. This extraordinary achievement provided a visual confirmation of their presence and opened a new window into the study of these fascinating objects. Through these methods, scientists continue to unravel the mysteries of black holes, pushing the boundaries of our understanding of the universe. Black holes captivate our imaginations, but they come in different forms, primarily categorized into stellar black holes and supermassive black holes. Stellar black holes are formed when massive stars exhaust their nuclear fuel and undergo a supernova explosion. This catastrophic event allows the core to collapse under its own gravity, producing a black hole that can range in size from about 3 to 25 solar masses. These black holes are scattered throughout galaxies, often found in binary systems where they interact with companion stars, drawing in matter and emitting energy. On the other hand, supermassive black holes are of a different magnitude entirely. They dwell at the centers of galaxies and possess masses ranging from millions to billions of solar masses. The formation of these colossal entities is still a topic of research, but scientists believe they may have formed from the merger of numerous smaller black holes or the collapse of massive clouds of gas in the early universe. Their immense gravitational pull influences the orbits of stars in their vicinity and plays a crucial role in the dynamics of galaxies. What's particularly fascinating is how these two types of black holes influence their surroundings. Stellar black holes, while powerful, primarily interact on a smaller scale, usually affecting their immediate stellar neighbors. Meanwhile, supermassive black holes can dictate the structure and evolution of entire galaxies. As matter spirals into a supermassive black hole, it forms an accretion disk, heating up and emitting high-energy radiation, often observed as quasars, one of the bright wonders of the universe. In recent years, Advances in observational technology have allowed us to witness the effects of both types of black holes. We have seen stellar black holes through their interactions with visible stars, while supermassive black holes have been confirmed through the motion of stars orbiting around them. The mystery of how these different types of black holes form and evolve continues to drive our quest for knowledge in astrophysics, showing us just how complex and awe-inspiring our universe really is. Black holes are among the most fascinating objects in the universe, and their influence extends far beyond their immediate vicinity. At their core, they possess an incredible gravitational pull that can affect everything around them, drawing in gas, dust, and even stars. This gravitational force can lead to the creation of what is known as an accretion disk, a swirling mass of material that gradually spirals into the black hole. As this material accelerates and heats up, it emits radiation, sometimes outshining entire galaxies. The energy released by accretion disks can have profound implications for their surroundings. For instance, this intense radiation can affect the formation of new stars in nearby regions. The heat and energy emitted may either trigger the collapse of nearby clouds of gas into new stars, or conversely, prevent star formation by dispersing the gas and dust. This interplay demonstrates a delicate balance between creation and destruction in cosmic environments. Additionally, black holes are not static entities. They often interact with their environment through processes such as stellar winds and galactic jets. When a black hole pulls in matter, it can launch powerful jets of particles at nearly the speed of light, extending out from the poles of the black hole. These jets can influence the interstellar medium and contribute to the dynamics of galaxies, playing a role in their evolution. Furthermore, in densely populated areas in the universe, like the centers of galaxies, supermassive black holes can exert an influence that extends across vast distances. They can affect the orbits of stars and the overall structure of their host galaxy. This highlights a vital relationship between black holes and their environments, showcasing their role as dynamic players in the cosmic ballet that shapes the universe. Here, gravity is thought to become infinitely strong, and the laws of physics as we know them break down. This enigmatic center challenges both our understanding of quantum mechanics and general relativity, leaving scientists grappling for a unified theory that can encompass both realms. Another unresolved puzzle is the nature of black hole entropy and information. When matter falls into a black hole, it seems to vanish, seemingly obliterated from existence. However, this raises the so-called information paradox. How can information be destroyed if the laws of quantum mechanics assert that it cannot? Researchers are exploring various theories, including the idea that information may be stored on the black hole's event horizon, but a comprehensive solution remains out of reach. Additionally, black holes may hold clues to the very fabric of our universe. The presence of dark matter and dark energy plays a significant role in cosmic evolution, yet their true nature is not well understood. Some theorists speculate that black holes could provide insights into these mysterious components by studying their formation and evolution. However, the relationship between black holes and these cosmic enigmas continues to be an area of active research and speculation. Lastly, the ultimate fate of black holes poses yet another unsolved mystery. They are known to emit Hawking radiation, a theoretical prediction suggesting that black holes can slowly evaporate over time. But the timescales for this process are extraordinarily long, meaning it is currently outside our observational reach. Will black holes eventually vanish completely, or will they leave remnants behind? The answers to these questions could reshape our comprehension of the universe itself, intertwining the fates of black holes with the broader narrative of cosmic evolution. Dark matter is one of the most enigmatic components of our universe, making up roughly 27% of its total mass energy content. Despite its name, dark matter is not something you can see or directly measure. It does not emit, absorb, or reflect light, making it invisible to our current observational techniques. Scientists were led to postulate its existence due to how galaxies behave and how they interact gravitationally. When astronomers observed galaxies, they noticed that the stars at the outer edges were spinning around their centers much faster than expected. The visible mass within these galaxies, mainly comprised of stars and gas, could not account for this rapid rotation. If the galaxies only contained the mass we could see, the outer stars should be flying off into space. To explain this discrepancy, scientists concluded that there must be a significant amount of unseen mass, which we now refer to as dark matter, exerting gravitational influence. Further evidence of dark matter comes from observations of galaxy clusters. When measuring the mass of these clusters through gravitational lensing, scientists found that the total mass considerably exceeded what could be accounted for with visible matter alone. The effect of gravity bending light from distant galaxies indicates that there is far more mass present that remains hidden from direct observation. The quest to understand dark matter continues, and while it remains elusive, it is integral to our understanding of cosmic structure and evolution. Researchers are exploring a variety of possibilities about the nature of dark matter, including weakly interacting massive particles, or WIMPs, and other theoretical particles. With ongoing advancements in technology and exploratory missions, the mysteries of dark matter may one day be unveiled, providing unprecedented insights into the fabric of our universe. Dark energy and dark matter are two of the most enigmatic components of our universe, yet they serve very different roles. Dark matter is a substance that interacts with regular matter and exerts gravitational influence. It does not emit or absorb light, making it invisible and detectable only through its gravitational effects. Scientists estimate that dark matter constitutes about 27% of the universe's total mass and energy. It acts as a cosmic glue, helping to hold galaxies and galaxy clusters together. In contrast, dark energy accounts for an astonishing 73% of the cosmos. Unlike dark matter, which binds things together, dark energy drives the universe apart. This mysterious force is responsible for the accelerated expansion of the universe, a phenomenon discovered in the late 20th century. As galaxies move away from each other, dark energy works to push them further apart, defying the gravitational attraction of dark matter and other celestial bodies. The existence of dark energy leads to perplexing questions. Why does it dominate the universe when ordinary matter and dark matter are necessary for forming structures like stars and galaxies? While scientists have proposed various theories to explain dark energy, none have garnered widespread acceptance. Some think it could be a property of space itself, while others speculate it might involve a new field or particle, hinting at the limits of our current understanding. It's worth noting that while both dark matter and dark energy are invisible, their effects are crucial to the universe's structure and behavior. Together, they shape the cosmos at the largest scales and influence the evolution of the universe over billions of years. As research continues, unlocking the secrets of these mysterious entities may one day illuminate our grasp of the fundamental workings of the cosmos. Dark matter and dark energy represent some of the most intriguing mysteries in cosmology. Despite being key components of our universe, they remain largely elusive. To unravel their secrets, scientists employ a variety of innovative methods and technologies that tap into the fabric of the cosmos. One of the primary ways researchers study dark matter is through its gravitational effects. Although dark matter cannot be seen directly, its presence is inferred by observing the motion of galaxies and galaxy clusters. When astronomers measure the speed at which galaxies rotate, they find that the visible matter alone doesn't provide enough gravitational pull to hold them together. This discrepancy hints at an unseen mass, dark matter. By looking at phenomena like gravitational lensing, where the gravity of massive objects bends the light from more distant galaxies, they can map the distribution of dark matter in large structures across the universe. Dark energy, on the other hand, is studied primarily through its influence on the expansion of the universe. The discovery that the universe is not just expanding but doing so at an accelerating rate led to the concept of dark energy. Observations of distant supernovae, which explode in a consistent brightness, reveal how fast they travel away from us, providing clues about the rate of expansion. Satellite missions like the European Space Agency's Euclid and NASA's Wide Field Infrared Survey Telescope are being designed to gather data on cosmic structures, helping to illuminate the nature of dark energy. Additionally, both dark matter and dark energy are investigated through simulations and large-scale surveys of the cosmos. Projects such as the Sloan Digital Sky Survey map large sections of the universe, capturing a wealth of information about galaxy distributions and cosmic microwave background radiation. This data helps scientists paint a broader picture of how these mysterious components influence the universe. By combining observational data with theoretical models, researchers continue to peel back the layers of complexity surrounding dark matter and dark energy, inching closer to understanding one of the universe's most profound enigmas. The universe's expansion is a fascinating topic that intertwines the realms of observation and theory. Two mysterious components play pivotal roles in this expansive tale: dark energy and dark matter. To start, let's focus on dark energy. This enigmatic force is believed to account for about 70% of the universe's total energy content. Its most compelling feature is the way it drives the accelerated expansion of the cosmos. Imagine it as a kind of invisible pressure, pushing galaxies apart at an ever-increasing rate. Observations of distant supernovae and the cosmic microwave background radiation have provided strong evidence for this acceleration, suggesting that the universe is not just expanding, but is doing so with increasing speed. On the other hand, dark matter, which constitutes around 25% of the universe, dances in a different way. Though it cannot be seen directly, its presence is inferred from gravitational effects on visible matter, radiation, and the large-scale structure of the universe. It affects the expansion by contributing to the overall gravitational pull within galaxies and clusters of galaxies. This interplay slows down the expansion at smaller scales like galaxies, while dark energy's influence dominates at the larger cosmic scales. Dark matter acts as a stabilizing force, holding galaxies together even as dark energy pushes the universe apart on a grand scale. The interaction between these two forces creates a dynamic tension within the universe. As dark energy continues to cause accelerated expansion, dark matter remains crucial in forming the very structure of the cosmos, helping to create the webs of galaxies we observe today. This cosmic balance influences how the universe evolves, determining the fates of galaxies and the overall destiny of cosmic structures over immense timescales. In a broader sense, the ongoing investigation into dark energy and dark matter leads us to fundamental questions about the nature of the universe itself. What are these components truly made of? How do they interact? And what will their roles be as the universe continues to expand? As researchers delve deeper into these mysteries, they uncover not just the mechanics of cosmic expansion, but also profound implications for our understanding of reality itself. Each discovery ignites curiosity about the universe, reminding us of the many layers yet to be explored. As we gaze into the vastness of the cosmos, we find that the visible universe around us accounts for only a small fraction of what actually exists. Current hypotheses suggest that dark matter, an invisible substance that does not emit, absorb, or reflect light, makes up about 25% of the universe. This mysterious material interacts with regular matter through gravity, providing crucial structure to galaxies. Observations of spiral galaxies have revealed that they spin at such rates that without this unseen mass, they would fly apart. Dark matter acts as a gravitational glue, holding these cosmic structures together. But what exactly is dark matter? Various candidates have emerged in the scientific community, with one of the leading hypotheses being that it consists of weakly interacting massive particles, or WIMPs. These theoretical particles would interact very weakly with normal matter, making them elusive to direct detection. Other candidates include axions and sterile neutrinos, all of which are yet to be confirmed. Regardless of its true nature, the search for dark matter continues, engaging scientists across the globe in a quest to unlock its secrets. Alongside dark matter, dark energy constitutes about 70% of the universe and is equally mysterious. It is thought to be responsible for the accelerated expansion of the universe observed since the late 20th century. This expansion defies intuitive understanding, as one might expect gravity to pull galaxies together rather than push them apart. Current hypotheses suggest that dark energy is a property of space itself, perhaps linked to a cosmological constant, a concept proposed by Albert Einstein. Another captivating idea is that dark energy could be related to a field permeating the universe, often called quintessence. This field might evolve over time, behaving differently at various stages of cosmic history. Regardless of its true nature, dark energy remains one of the most profound enigmas of modern astrophysics, pushing the boundaries of our understanding of the universe. As research progresses and new technologies are developed, The hope is that we will one day untangle the mysteries of both dark matter and dark energy, revealing the true fabric of our universe. Stars, those dazzling celestial bodies that light up our night sky, are born from vast clouds of gas and dust known as nebulae. These immense structures, often appearing as beautiful, colorful formations in images captured by telescopes, serve as the raw material for star formation. When regions within a nebula become dense enough, small gravitational forces can begin to pull matter together, creating clumps where the density increases over time. As these clumps of gas and dust coalesce, they undergo a process called gravitational collapse. This is where the material begins to clump together more tightly, and as it does, the gravitational pull becomes stronger. The temperature and pressure at the center of these clumps rise significantly. Eventually, when temperatures soar high enough, nuclear fusion ignites in the core, marking the birth of a new star. This process can take millions of years, as the nebula slowly transforms into a new celestial entity. Surprisingly, not every part of a nebula leads to the formation of a star. Some regions may form a protostar, a pre-star stage, but might not gain enough mass to ignite nuclear fusion. Interestingly, the birth of stars in a nebula often occurs in clusters, meaning many stars can form simultaneously from the same cloud of gas and dust. This cluster formation is vital in understanding the dynamics of star evolution and their eventual life cycles. As these new stars shine brightly, they also influence their surroundings. The energy produced by newly formed stars heats the remaining gas within the nebula, which can trigger further star formation. This ongoing cycle illustrates the life-giving nature of nebulae and their crucial role in the universe's continual dance of creation and destruction. In this way, nebulae serve not just as stellar nurseries, but also as windows into the life cycle of galaxies and the very cosmos itself. The lifespan and fate of a star are primarily determined by its mass. Stars begin their lives in a nebula, where clouds of gas and dust clump together under gravity, eventually igniting nuclear fusion at their cores. This fusion process allows stars to shine, converting hydrogen into helium and releasing immense amounts of energy. However, not all stars are created equal. The mass of a star defines its temperature, luminosity, and how quickly it will exhaust its nuclear fuel. A star's mass significantly influences its life cycle. For massive stars, often over 8 times the mass of our Sun, the burning process is rapid and intense. These stars can live for only a few million years, but they go out with a spectacular explosion known as a supernova, seeding the surrounding universe with elements that will form new stars, planets, and even life itself. The remnants of such a violent end can lead to the formation of neutron stars or black holes, exotic objects with incredibly dense cores. In contrast, smaller stars like our Sun have a more leisurely pace. They can burn for billions of years, going through various stages of their life cycle. After eventually exhausting their hydrogen fuel, these stars will expand into red giants, possibly engulfing nearby planets. Ultimately, they shed their outer layers gently, creating beautiful planetary nebulae, while the core that remains cools and becomes a white dwarf, a dim but stable remnant of its former self. Thus, the fate of a star is a story written in its mass. From brief but brilliant supernova to the slow and steady glow of white dwarfs, each path reflects the underlying physics that has governed its life from the moment it formed. The narrative of a star does not conclude with its death. Rather, it contributes to the grand cosmic cycle, providing the fundamental building blocks for future generations of stars and planets. Stars, much like humans, go through life cycles that differ based on their initial mass and composition. At the beginning of a star's life, it originates from a giant cloud of gas and dust in space, often referred to as a stellar nursery. In this environment, gravity causes parts of the cloud to collapse in on themselves, creating clumps that eventually heat up and ignite nuclear fusion in their cores. But from here, the path forward varies significantly for different types of stars. For instance, smaller stars such as our Sun will evolve into red giants as they exhaust the hydrogen fuel in their cores. When this happens, the core contracts and heats up, allowing the outer layers to expand dramatically. This transformation can lead a star to swell to sizes hundreds of times larger than its original state. During this red giant phase, the star begins to fuse helium into heavier elements. Eventually, the outer layers of the star shed, creating beautiful planetary nebulae, while the core remains and becomes a white dwarf. On the other hand, larger stars have a more dramatic life cycle. When they exhaust their nuclear fuel, they undergo a supernova explosion, scattering their outer layers into space and leaving behind an incredibly dense core. Depending on the mass of this core, it can become a neutron star, or, if massive enough, collapse further into a black hole. Before this explosive finale, these stars also experience a red giant phase, similar to their smaller counterparts, but the end result could not be more different. The formation of different types of stars like red giants and white dwarfs is deeply connected to their mass and life cycle. While smaller stars evolve gently into red giants and eventually white dwarfs, larger stars face catastrophic endings that speak to the power of the cosmos. Each transformation reveals the intricate processes that govern our universe, and the beautiful, often violent stages of star life highlight the dynamic nature of stellar evolution. The death of a star is a dramatic finale in the life cycle of these celestial bodies, marked by various spectacular astronomical events. The fate of a star largely depends on its mass, shaping the way it will end its life. For smaller stars like our Sun, the process leads to the creation of a planetary nebula, while larger stars might culminate in a supernova explosion. For stars similar in mass to our Sun, the journey begins after they exhaust their nuclear fuel. At this stage, they expand into red giants, shedding their outer layers into space. This ejection of material forms what is known as a planetary nebula. The remaining core, now left behind, becomes a white dwarf, which will cool and fade over billions of years. This gentle yet poignant transition adds to the cosmic material pool, enriching the universe with elements forged in stellar interiors. In stark contrast, the demise of massive stars brings a more violent and dramatic end through a supernova explosion. When these massive stars reach the end of their life cycle, they experience a core collapse. The core succumbs under the force of gravity, causing a cataclysmic explosion that can outshine entire galaxies for a brief moment in time. This immense release of energy blasts out the star's outer layers, scattering matter across the universe and creating shock waves that can trigger the formation of new stars in surrounding gas clouds. The remnants of these supernova explosions may evolve into neutron stars, or if the original star was incredibly massive, they can collapse into black holes. Each of these endings, from the quiet fading of a white dwarf to the colossal burst of a supernova, illustrates the diverse and intricate processes that govern the life and death of stars. Through these events, the very fabric of the universe is shaped and transformed, illustrating the deep interconnectedness of cosmic evolution. Supernovae are one of the universe's most spectacular phenomena, marking the explosive death of massive stars. When such a star exhausts its nuclear fuel, its core collapses under gravity. This collapse leads to a rebound effect, resulting in an enormous explosion that releases an immense amount of energy. During this cataclysmic event, elements created in the star's life cycle, as well as new elements formed in the intense heat of the explosion, are scattered across the cosmos. This distribution of materials is essential for the cosmic cycle of matter. The elements expelled in a supernova are the building blocks for new stars, planets, and even life. Most of the heavier elements we find on Earth today, such as carbon, oxygen, and iron, were forged in the cores of stars and released into space during supernova explosions. Without these explosive events, the universe would be a less diverse and less complex place, lacking the rich variety of elements essential for the formation of planets and the emergence of life. Moreover, the shock waves generated by a supernova can trigger the formation of new stars. As these shock waves travel through the interstellar medium, they compress gas and dust clouds, leading to dense areas that can collapse under their own gravity. This process ignites new star formation, effectively recycling the materials from old stars into new celestial bodies. In this way, supernovae play a crucial role in the life cycle of matter in the universe. They facilitate the transformation of elements from one generation of stars to the next, ensuring both the continuity and evolution of the cosmic landscape. The cycle of birth, death, and rebirth initiated by these explosive events illustrates the interconnectedness of all matter in the universe, a grand dance that echoes through the vastness of space and time. A neutron star is one of the most fascinating astronomical objects in our universe. These incredibly dense stars are the remnants of massive stars that have ended their lives in spectacular supernova explosions. Once the core of a massive star exhausts its nuclear fuel, gravity causes it to collapse. This implosion happens so rapidly that it compresses the core matter into an incomprehensibly small volume where the normal atomic structure breaks down. During the collapse, electrons and protons merge to form neutrons, resulting in a star composed almost entirely of these subatomic particles. What remains is an object so dense that a sugar cube-sized amount of neutron star material would weigh about as much as an entire mountain. This astonishing density is what gives neutron stars their name, highlighting their unique composition and the extreme environments in which they exist. Neutron stars also exhibit intense magnetic fields, often millions of times stronger than that of the Earth. This powerful magnetism can cause them to emit beams of radiation that sweep across space. When these beams point toward Earth, they can be detected as pulsing signals, making neutron stars popular candidates for the title of pulsars. These pulsating stars give scientists incredible insights into the fundamental laws of physics, particularly in extreme conditions. The life cycle of a neutron star can also lead to fascinating outcomes. If it is part of a binary system, it might accumulate additional material from its companion star. This process can trigger further intense phenomena, such as bursts of X-rays, or even lead to the formation of a black hole, depending on the mass of the star and the dynamics of the system. Neutron stars challenge our understanding of matter and continue to be a subject of deep scientific research, revealing secrets about the universe and the forces that govern it. Pulsars are fascinating astronomical objects, often described as cosmic lighthouses. They are rapidly rotating neutron stars, remnants of massive stars that have exploded in supernova events. As they spin, they emit beams of electromagnetic radiation. This emission occurs primarily from their magnetic poles, which are not aligned with their rotation axes. As the pulsar rotates, these beams sweep across space like the light from a lighthouse. The process begins deep within the pulsar, where extreme magnetic fields play a crucial role. When the neutron star forms, it compresses its core so tightly that protons and electrons combine to create neutrons. This immense density leads to incredibly strong magnetic fields, sometimes trillions of times stronger than that of Earth. Charged particles, such as electrons, become trapped in these magnetic fields and are accelerated to nearly the speed of light. As these particles move along the magnetic field lines, they emit radiation in the form of pulses. The characteristic pulses are observed when the beams of radiation point towards Earth. Because of the pulsar's rapid rotation, these beams sweep across the planet at regular intervals, which creates the effect of a pulsing signal. Depending on the rotation speed of the pulsar, these emissions can occur every few milliseconds to several seconds. When scientists observe these beats, they can determine the rotational period of the pulsar and learn more about its properties. One of the striking aspects of pulsars is their precision. Many of them can keep time more accurately than atomic clocks. These regular pulses have made pulsars invaluable tools for understanding the universe, from testing theories of gravity to exploring the behavior of matter under extreme conditions. With each discovery, pulsars continue to intrigue scientists and enlighten us about the fundamental workings of the cosmos. Quasars, short for quasi-stellar objects, are astonishingly bright celestial phenomena found in the universe. They are powered by supermassive black holes that reside at the centers of distant galaxies. When matter spirals into these black holes, it forms an accretion disk, where the intense gravitational forces generate immense heat and energy. This process emits radiation across the entire electromagnetic spectrum, making quasars detectable across vast cosmic distances. One of the fascinating aspects of quasars is their extraordinary brightness. In fact, some of them can outshine entire galaxies, emitting as much light as hundreds of billions of stars combined. This incredible luminosity allows astronomers to observe quasars from billions of light-years away, providing valuable insights into the early universe. As light travels through space, it brings with it information about the conditions and characteristics of the universe when the quasars were formed, often just a few billion years after the Big Bang. Quasars serve as beacons, helping scientists understand the formation and evolution of galaxies. Their light carries clues about the gas and dust in the early cosmos, as well as the interplay between black holes and their surroundings. With the help of modern telescopes, researchers can analyze this light to gather data about the temperature and composition of the material being consumed by the black hole, as well as the distance and movement of the quasar itself. Quasars are not only among the brightest objects in the universe, but also fascinating tools for astronomers. They illuminate the distant past, revealing the dynamic events that shaped the cosmos and providing a glimpse into the behaviors of matter under the extreme conditions found near supermassive black holes. Each quasar serves as a reminder of the vastness of space and the mysteries that continue to unfold within it. Gamma-ray bursts, often referred to as GRBs, are among the most energetic and luminous events in the universe. These explosive phenomena can release as much energy in just a few minutes as the sun will emit over its entire lifetime. Typically, they manifest as flashes of gamma-ray radiation, which is the highest energy form of light. These bursts can be detected from billions of light-years away, making them a vital tool for scientists studying the deep cosmos. So, what exactly causes these astonishing bursts? There are two primary types of gamma-ray bursts. The first category is long-duration bursts, which last more than 2 seconds. These are generally associated with the death of massive stars. When such a star exhausts its nuclear fuel, it undergoes a catastrophic collapse, leading to a supernova explosion and potentially forming a black hole. As the material spirals into the black hole, it emits powerful jets of gamma rays. The other category consists of short-duration bursts, lasting less than 2 seconds. These are thought to result from the merger of neutron stars or the collision of a neutron star with a black hole. In these cases, when the two dense celestial bodies collide, the immense gravitational forces create shock waves that produce intense bursts of gamma radiation. The study of gamma-ray bursts has opened a window into many areas of astrophysics, including the formation of black holes, the behavior of neutron stars, and the evolution of galaxies. These bursts not only highlight the violence and complexity of the universe, but also remind us that even the most extreme phenomena are rooted in the fundamental forces of nature. Each discovery related to gamma-ray bursts deepens our understanding of the cosmos and our place within it. Throughout the history of science, phenomena that defy our current understanding of physics often serve as catalysts for major breakthroughs. One of the most striking examples of this is the behavior of black holes. When matter is compressed into an incredibly small space, it creates a region in space where gravity is so strong that not even light can escape. This challenges our perception of time and space, suggesting that these familiar concepts behave differently under extreme conditions. Theories of general relativity, conceived by Albert Einstein, grapple with this phenomenon, but they leave us with many unanswered questions. Then there's the mystery of dark matter and dark energy, which together account for approximately 95% of the universe. Despite this significant presence, dark matter remains invisible to our current instruments, and dark energy is even more elusive, causing the universe to expand at an accelerating rate. Our grasp of fundamental forces and particles is shaken as these phenomena challenge the completeness of the standard model of physics. These enigmatic aspects of the cosmos force scientists to reconsider existing theories and look for new particles or forces that could account for what we cannot see. Moreover, quantum mechanics introduces another layer of complexity. The strange behaviors exhibited at the quantum level, such as particles existing in multiple states at once, pose profound questions for classical physics. Observations like quantum entanglement, where particles are instantaneously connected regardless of distance, defy our intuitive understanding of cause and effect. This inconsistency between quantum mechanics and general relativity is a major puzzle, leading many physicists to seek a unified theory that can encompass both realms. Lastly, the phenomenon of time itself remains a perplexing subject. As scientists study black holes and the fabric of space-time, they encounter the idea that time may not be a one-way street. This has significant implications for our understanding of causality and the universe's structure. By engaging with these challenging phenomena, scientists are not just seeking answers, they are expanding the very framework of physics. reshaping our view of reality in ways that were once deemed unimaginable. The journey toward understanding these elusive parts of our universe continues to excite the curiosity and creativity of thinkers across the globe. Gravity plays a pivotal role in shaping the universe's large-scale structure, acting as the unseen force that pulls matter together. From the very earliest moments after the Big Bang, tiny fluctuations in density began to set the stage for the grand cosmic architecture we observe today. Regions with slightly more mass exert greater gravitational attraction, drawing in surrounding matter and leading to the formation of cosmic structures over billions of years. As matter clumped together under gravity's influence, it gave rise to galaxies, clusters of galaxies, and vast cosmic filaments. These filaments form a web-like structure, often referred to as the cosmic web, comprising great voids and denser areas where galaxies congregate. The gravitational pull of dark matter, an invisible substance that does not emit light, enhances this structure by providing the scaffolding that keeps these filaments intact. On a larger scale, gravitational interactions continue to affect the motion of galaxies. They pull them closer together, causing them to interact and sometimes merge. This continuous process shapes the arrangement and evolution of galaxies across the universe, resulting in formations like superclusters, massive groups of galaxies that are gravitationally bound to each other. In contrast, vast areas of the universe remain almost empty, illustrating the influence of gravity in carving out cosmic voids. Intriguingly, gravity not only shapes how galaxies are organized, but also influences the expansion of the universe itself. While the universe is constantly expanding, gravity works to slow this expansion down. Understanding gravity's role in these processes not only offers insights into the present structure of the universe, but also the history and future evolution of cosmic formations. Gravitational waves are ripples in the fabric of space-time, produced by some of the most violent and energetic processes in the universe. These waves move at the speed of light and can stretch and compress space itself as they pass through it. You can think of them as the echoes of cataclysmic events, such as the collision of black holes or neutron stars, traveling vast distances across the cosmos, carrying with them information about their origins and the fundamental nature of gravity. The first direct detection of these elusive waves occurred in September of 2015, a monumental breakthrough for scientists and astronomers alike. The Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, was responsible for this historic achievement. LIGO employs long L-shaped detectors, measuring tiny changes in distance caused by passing gravitational waves. As waves travel through Earth, they cause the lengths of the arms of this detector to oscillate by a fraction of the diameter of a proton, an incredibly subtle measurement. This groundbreaking moment was sparked by the merger of two black holes about 1 billion light-years away. The collision generated gravitational waves that reached Earth and were detected by LIGO. The significance of this detection cannot be overstated. It confirmed a major prediction of Albert Einstein's theory of general relativity, established a new way to observe the universe, and opened the door to the field of gravitational wave astronomy. Since that first detection, LIGO and its partner instruments around the world have observed numerous events, giving us new insights into the workings of the universe. These discoveries have illuminated the lives of black holes, neutron star mergers, and even the formation of the universe itself. As we continue to track these cosmic ripples, they promise to transform our understanding of the universe and our place within it. The study of gravity has profoundly shaped our understanding of the universe and its vast expanse. Gravity, the fundamental force that governs the attraction between masses, plays a pivotal role in the formation and evolution of celestial bodies and structures. Since ancient times, thinkers contemplated the nature of gravity, but it was not until the work of Sir Isaac Newton in the 17th century that a cohesive theory emerged. Newton articulated the law of universal gravitation, which provided a framework for understanding how objects in space interact with one another. As cosmologists delved deeper into the cosmos, they uncovered that gravity is not merely a benign force, but a powerful architect of the universe's structure. The discovery of how gravity influences the motion of planets, stars, and galaxies laid the groundwork for modern astrophysics. For example, Einstein's theory of general relativity expanded upon Newton's ideas. It proposed that gravity is not just a force between masses, but a curvature of space-time caused by those masses. This breakthrough altered our perception of the universe, suggesting that massive objects like stars and black holes warp the very fabric of space, affecting everything around them. Gravity's effects are not limited to just interacting celestial bodies. They have also led to some of the most intriguing phenomena in cosmology. For instance, the study of gravitational waves, ripples in space-time caused by cataclysmic events such as merging black holes, has allowed scientists to witness cosmic events that were once only theoretical. This has opened a new window into understanding the universe, providing insights into its birth and evolution. Moreover, gravity plays a crucial role in the fate of the universe itself. It influences the expansion of space, which has been observed to be accelerating. This finding raised profound questions about dark energy, a mysterious force counteracting gravity on cosmic scales. Through the lens of gravity, we gain a deeper appreciation for the intricate dance of celestial mechanics, and this continues to drive our quest for knowledge about the cosmos. As we peer deeper into the universe, gravity remains a constant companion guiding our exploration and understanding of everything we know about the heavens above. The world of physics underwent a remarkable transformation with the introduction of Albert Einstein's theory of general relativity. Prior to this groundbreaking theory, Sir Isaac Newton's laws of gravity reigned supreme for more than 2 centuries. Newton depicted gravity as a force that acts at a distance, explaining how objects are attracted to each other in a straight line. His laws demonstrated that the gravitational pull between 2 bodies is proportional to their masses, which painted a clear picture of how celestial bodies interacted. Einstein, however, expanded our understanding by rethinking gravity itself. He proposed that gravity is not simply a force, but rather a curvature of space and time caused by mass. Imagine placing a heavy object like a bowling ball on a trampoline. That heavy object creates a dip, causing lighter objects, such as tennis balls, placed nearby to roll towards it. In this analogy, the trampoline represents the fabric of space-time, and the heavier mass symbolizes a planet or a star distorting this fabric. This conceptual leap not only explained the motion of planets in a fundamentally different way, but it also led to predictions that Newton's laws could not account for. For instance, general relativity predicted phenomena such as the bending of light around massive objects, a concept known as gravitational lensing. This has been observed and confirmed by numerous astronomical observations, revealing how light from distant galaxies is altered when it passes near massive objects, like clusters of galaxies. The differences extend to the scale of influence as well. Newton's laws work remarkably well for everyday situations, and even during most celestial events. However, when we venture into the realm of extreme gravitational fields, such as those near black holes or neutron stars, general relativity emerges as the more accurate theory. It guides our understanding of cosmic phenomena, shifting our perspective and broadening our comprehension of the universe's intricate ballet, forever changing the way we perceive gravity and space itself. Gravity has long been a source of intrigue for scientists, particularly because it behaves so differently from the other fundamental forces of nature. To understand how we might unify gravity with electromagnetism, the weak nuclear force and the strong nuclear force, we must first consider what unification means. It is the idea that all these forces could be manifestations of a single underlying force or theory. One prominent theoretical framework aiming at this unity is string theory. This fascinating concept suggests that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. According to string theory, different vibrational modes of these strings give rise to various particles, and, consequently, the different forces. Gravity emerges naturally in this framework, which has led many physicists to consider string theory a leading candidate for a theory of everything. Another avenue of exploration is loop quantum gravity. Unlike string theory, which unifies all forces in a higher dimensional space, loop quantum gravity focuses primarily on the fabric of space-time itself. It posits that space-time is made up of tiny, discrete loops woven together like a fabric. This approach aims to reconcile general relativity, which describes gravity, with quantum mechanics. Although this theory is still in development, It offers a promising avenue toward understanding how gravity fits into the quantum realm. Additionally, some researchers are exploring grand unified theories. These theories propose that at extremely high energies, the electromagnetic, weak, and strong forces merge into a single force. Gravity, however, has remained more elusive. The hope is that at the energy scales close to those present during the Big Bang, a unified description of all four forces could be achieved. This quest continues to shape modern physics and cosmology, inviting both theoretical innovation and experimental explorations that seek to uncover the deeper laws of the universe. Telescopes have fundamentally transformed our understanding of the universe, acting as powerful instruments that have opened our eyes to the vast cosmos beyond our planet. Before the invention of telescopes, early astronomers relied solely on their naked eye observations, which limited their ability to discern celestial phenomena. With the advent of the telescope in the early 17th century, humanity first glimpsed a much broader universe. Galileo Galilei, utilizing a simple telescope, famously discovered the moons of Jupiter and the phases of Venus, allowing him to challenge established views about our solar system. As telescopes evolved, so too did their impact on astronomical research. The development of larger and more complex optical telescopes allowed scientists to observe fainter and more distant objects in the night sky. Throughout the 19th and 20th centuries, public institutions began to invest in larger observatories, such as Mount Wilson and Mauna Kea. These facilities produced groundbreaking observations, enabling astronomers to map our galaxy and identify nebulae and other distant galaxies. Telescopes essentially acted as time machines, allowing us to see light that had traveled billions of years to reach us, thus offering glimpses into the early universe. The introduction of radio telescopes in the mid-20th century opened a whole new chapter in astronomy. These instruments revealed phenomena that optical telescopes could not detect, including cosmic microwave background radiation and pulsars, rotating neutron stars emitting beams of radio waves. This advancement in technology broadened our perspective on the universe's structure, composition, and even the conditions present after the Big Bang, enriching our scientific narratives with fresh insights. Today, space-based telescopes like the Hubble Space Telescope have taken our understanding to even greater heights. By orbiting above Earth's atmosphere, Hubble provides clearer images of celestial objects, free from atmospheric distortion. Its contributions have led to breakthroughs in many areas, including the calculation of the expansion rate of the universe and the identification of exoplanets. Telescopes in all their forms serve as vital links in our quest to decipher the secrets of the universe, continuously expanding our knowledge and igniting our awe for the cosmos. Space missions have been instrumental in expanding our understanding of the universe beyond our planet. Through a series of carefully planned expeditions, scientists have been able to gather data that challenges, enhances, and sometimes completely changes what we know about the cosmos. From the early days of human space exploration to the sophisticated robotic missions of today, each endeavor has contributed to a greater comprehension of astronomical phenomena. One of the most significant advancements has come from missions that have ventured beyond Earth's atmosphere. For instance, the Hubble Space Telescope, launched in 1990, has provided us with breathtaking images of distant galaxies, revealing processes that range from star formation to black holes. Its observations have helped astronomers calculate the expansion of the universe and delve into the mysterious nature of dark energy. Each image captured by Hubble serves as a window into the past, showcasing objects that may be billions of light-years away. Robotic missions to other planets have also played a crucial role. The Mars rovers, for example, have not only explored the Martian surface, but have also analyzed soil samples, searched for signs of water, and investigated the planet's climate and geology. These findings are helping scientists assess whether Mars could have supported life in the past. The knowledge gleaned from these missions compels us to rethink our definitions of habitable environments and broaden the scope of life in the universe. Perhaps one of the most ambitious missions in recent history is the Voyager spacecraft, launched in the late 1970s. Carrying golden records filled with sounds and images of life on Earth, Voyager 1 and 2 have traveled beyond our solar system, providing unprecedented information about the outer planets and the vast emptiness that exists beyond. The data from these missions continues to inform our understanding of interstellar space, shedding light on the conditions and materials found there. As our technology advances and new missions are planned, the journey to uncover the secrets of outer space remains a vital quest for humanity. The Hubble Space Telescope, launched in 1990, has significantly expanded our understanding of the universe. One of its most profound contributions is the measurement of the rate of expansion of the universe, which led to the realization that this expansion is accelerating. This discovery prompted scientists to investigate the mysterious force known as dark energy, a now fundamental concept in cosmology. By observing distant supernovae, Hubble helped astronomers refine their estimates of the universe's age, placing it at roughly 13.8 billion years. Another remarkable achievement of Hubble's observations is the detailed imagery of the cosmos. For instance, Hubble provided stunning photographs of the pillars of creation in the Eagle Nebula. This awe-inspiring image shows towering clouds of gas and dust, acting as stellar nurseries where new stars are born. Such captivating visuals not only enthrall the public, but also offer vital insights into the processes of star formation and the life cycle of cosmic structures. Hubble also played a critical role in understanding the characteristics of distant galaxies. The telescope helped classify galaxies and determine their composition, shedding light on how galaxies evolve over time. By observing them in various stages of development, astronomers gained a clearer picture of galactic interactions, mergers, and the formation of supermassive black holes at their centers. Lastly, Hubble's exploration of exoplanets has sparked immense interest in the search for extraterrestrial life. Through techniques such as transit photometry, it has detected the faint signatures of exoplanet atmospheres, identifying elements like water vapor and carbon dioxide. These findings not only invigorate the field of astrobiology, but also encourage deeper inquiries into the potential habitability of these distant worlds, further igniting the quest to understand our place in the cosmos. The James Webb Space Telescope represents a monumental leap in our ability to explore the cosmos. Launched in December 2021, it is designed to observe the universe in a way that its predecessors, like the Hubble Space Telescope, could never achieve. With its large mirror and advanced instruments, Webb focuses on infrared light, allowing it to peer through cosmic dust and gas clouds that obscure our view of the universe. This capability opens exciting new avenues for understanding both the birth of stars and the formation of galaxies. One of the most intriguing aspects of Webb is its potential to detect the light from some of the first stars and galaxies that formed after the Big Bang. These ancient celestial bodies, known as Population 3 stars, are believed to have played a critical role in evolving the universe. By capturing their light, Webb could help pinpoint when and how the first galaxies emerged and evolved over time, deepening our knowledge of cosmic history. This is akin to peeling back layers of a cosmic onion, revealing insights that have eluded astronomers for decades. Moreover, Webb's technology enables it to study exoplanets, those planets outside our solar system, in unprecedented detail. Scientists can analyze the atmospheres of these distant worlds to identify chemical signatures that might indicate the presence of life. With the capability to detect water vapor, carbon dioxide, and other key molecules, Webb is set to answer profound questions about our place in the universe and whether we are alone. The James Webb Space Telescope is not just a new tool for astronomers, it is a gateway to uncovering the mysteries of the universe. By observing in infrared light, it allows us to see through obstacles and discover what lies beyond our current understanding. As we unlock the secrets of the cosmos with the help of Webb, we find ourselves on the brink of exciting discoveries that could reshape our view of reality itself. As we look to the future of space exploration, scientists are brimming with excitement about several transformative technologies that could open new frontiers beyond our current reach. One of the most promising advancements is the development of next-generation propulsion systems. Traditional chemical rockets have served us well, but they are limited in speed and efficiency. Scientists are exploring alternatives like nuclear thermal propulsion, which could drastically reduce travel time to distant destinations such as Mars or even the icy moons of Jupiter and Saturn. With such technology, missions that once took months or years could be completed in weeks, sparking incredible possibilities for human exploration. Another area garnering attention is in-space resource utilization. As we venture further into the cosmos, the ability to harness local resources becomes critical for sustainability. This technology involves extracting water, minerals, and other materials from celestial bodies. For instance, the Moon is believed to host deposits of ice in permanently shadowed craters. This ice could be converted into water for drinking and oxygen for breathing, or even serve as a source of rocket fuel, enabling astronauts to explore deeper into the solar system without the need to send all supplies from Earth. Artificial intelligence is also poised to play a pivotal role in future missions. Machines equipped with advanced AI can assist astronauts in navigating complex environments and making real-time decisions when communication with Earth is delayed due to vast distances. Imagine robots that can explore the surface of Mars or even asteroids independently, sending back vital data and conducting experiments while humans remain safely in orbit or on another celestial body. This could enhance our understanding of these locations and allow for more ambitious missions with reduced human risk. Moreover, the concept of space habitats has evolved significantly with advancements in materials science. Scientists are investigating ways to build living environments that can protect astronauts from radiation and other harsh conditions beyond Earth's atmosphere. Concepts like inflatable habitats or structures made from materials found on other planets could allow for longer stays in space, while maintaining safety and comfort for the crew. As these technologies develop, they will transform our ability to explore the universe, making the dream of becoming an interplanetary species ever closer to reality. The quest for evidence of life beyond our planet is one of humanity's most intriguing pursuits. Scientists have unearthed an array of compelling indicators that suggest life could exist elsewhere in the universe. One of the primary pieces of evidence comes from the discovery of extremophiles, organisms that thrive in harsh environments on Earth. These resilient forms of life endure extreme temperatures, pressures, and radiation, demonstrating that the building blocks of life can survive in conditions once thought too hostile. Furthermore, the detection of exoplanets, planets outside our solar system, has significantly bolstered the argument for extraterrestrial life. As of now, thousands of these worlds have been identified, many of which reside in the so-called Goldilocks zone. This is the region around a star where conditions may be just right for liquid water to exist. The presence of water is a crucial factor, as it is considered an essential ingredient for life as we know it. Observations from telescopes like Kepler and the Transiting Exoplanet Survey satellite have revealed numerous planets that may have the potential to support life. Mars, our neighboring planet, also provides substantial evidence in favor of this possibility. NASA missions have detected seasonal dark streaks, known as recurring slope lineae, which suggest the flow of briny water on the surface. Additionally, the presence of ancient riverbeds and minerals that form in water hints that Mars once had a much wetter climate, possibly hosting microbial life in its past. As we explore Mars, the curiosity surrounding its potential for current life continues to grow. Lastly, the search for extraterrestrial intelligence, or SETI, scans the cosmos for signals that could indicate intelligent life beyond Earth. While no definitive evidence has yet been found, the sheer vastness of the universe, containing billions of galaxies, each with billions of stars, fuels the hope that we are not alone. The combination of diverse environments on other planets, the historical presence of water on Mars, and the ongoing search for communication leads us to remain optimistic about uncovering the mysteries of life beyond our home planet. Searching for exoplanets or planets outside our solar system has become one of the most exciting frontiers in astrophysics. Scientists employ several innovative techniques to identify these distant worlds, especially those that might support life. One of the most influential methods is the transit method. This involves monitoring a star's brightness over time. When an exoplanet passes in front of its host star, it temporarily blocks a portion of the star's light. By measuring this dip in brightness, scientists can infer the planet's size and its distance from the star, which are crucial for determining if it lies in the so-called Goldilocks zone. This is the region where conditions could be just right for liquid water to exist, a key ingredient for life as we know it. Another prominent technique is radial velocity, or the Doppler effect method. As planets orbit their host stars, they exert a gravitational pull that causes the star to wobble slightly. This wobble affects the star's light spectrum, shifting it towards the red or blue end of the spectrum, depending on whether the star is moving away from or towards us. By tracking these shifts, scientists can deduce the presence of an exoplanet, along with its mass and orbit. This method has led to the discovery of many exoplanets, some of which lie in potentially habitable zones. In addition to these techniques, scientists use direct imaging to capture images of exoplanets themselves. This method is particularly challenging due to the overwhelming brightness of stars compared to their planets. However, advancements in telescope technology, such as adaptive optics, have made it possible to block out the starlight, revealing the planets around them. Observing the atmosphere of these planets is crucial, as it can reveal vital information about their composition and potential habitability. Together, these methods give scientists a broader understanding of the range of exoplanets in our galaxy, especially those that might share characteristics with Earth. As technology continues to improve, the search for potentially habitable worlds is gaining momentum, encouraging hope that we might someday discover life beyond our planet. Each new discovery adds to our extraordinary understanding of the universe and our place within it. The search for extraterrestrial life has captivated scientists and enthusiasts alike, leading to the discovery of many intriguing exoplanets beyond our own solar system. Among these, several stand out due to their unique characteristics and their potential to harbor life. One of the most notable is Proxima Centauri b, an exoplanet orbiting the star Proxima Centauri, which is the closest star system to Earth. This planet lies within the so-called habitable zone, where liquid water could exist, a crucial ingredient for life as we know it. Another exciting candidate is Kepler 186f, which is part of a system that was discovered by NASA's Kepler mission. It is approximately 158 light-years away from us and is about 1.1 times the size of Earth. What makes Kepler 186f particularly promising is its position in the habitable zone of its star, a red dwarf, which allows for conditions potentially suitable for life. This planet's rockiness suggests it could have terrain and atmospheres similar to our own. Then there's TRAPPIST-1 system, containing 7 Earth-sized planets, 3 of which are firmly located in the habitable zone. This group, situated around 40 light-years away, has garnered much attention. Researchers are excited by the possibility that these planets could possess environments that support liquid water and ultimately life. The diverse atmospheres of these worlds raise tantalizing questions about chemistry and potential biology, inviting us to wonder if life might arise under varying conditions. Finally, LHS 1140b is another standout exoplanet that has been labeled a super-Earth, sitting just 41 light-years from our solar system. Its robust gravity and atmosphere offer intriguing possibilities for sustaining life. Scientists are particularly interested in studying the atmospheric composition of this planet because it may reveal important clues about habitability. As technology advances and our exploration of the cosmos deepens, we inch closer to understanding which of these elusive worlds might be our cosmic neighbors in the search for life beyond Earth. The discovery of extremophiles on Earth has significantly shaped our approach to searching for life beyond our planet. Extremophiles are organisms that thrive in environments once thought to be too hostile for life. These resilient life forms have been found in volcanic hot springs, deep-sea hydrothermal vents, and even in the icy realms of Antarctica. Their ability to survive under extreme conditions, such as intense heat, high pressure, or extreme acidity, raises fascinating questions about where life might exist elsewhere in the universe. Understanding extremophiles broadens our definition of habitable environments. For decades, scientists primarily focused on planets and moons that resemble Earth. However, the existence of life in such extreme conditions suggests that alien life could thrive in places we previously dismissed, such as the thick clouds of Venus or the icy crusts of moons like Europa and Enceladus. Extremophiles have taught us that life can adapt and survive in ways we might not have imagined, opening the door to the possibility of finding life in the most unexpected and seemingly inhospitable places. This insight has ignited a new wave of exploration in astrobiology, leading to missions designed specifically to search for life in these uncharted territories. For instance, upcoming missions to Mars aim to investigate ancient water sources and potential subsurface habitats where extremophiles could exist. Similarly, Landing on Europa is driven by the hope that beneath its icy surface lies a subsurface ocean, potentially harboring life. Moreover, the study of extremophiles informs our understanding of the biochemical processes that may support life elsewhere. By examining how these organisms metabolize and reproduce in extreme conditions, scientists can formulate hypotheses about alien biochemistry that differ from our own. Thus, the influence of extremophiles extends beyond Earth's boundaries, prompting a re-evaluation of life's potential in the cosmos and challenging our understanding of where we might find our extraterrestrial neighbors. The quest for extraterrestrial life has long fascinated humanity, leading to the idea of sending interstellar messages into the vast expanse of space. The role of these messages is profound, offering a potential bridge between our world and civilizations that might exist light years away. Interstellar messages represent a form of communication strategy designed to reveal our existence and seek out those who might be listening in the cosmos. These messages are not just simple signals, they are carefully crafted packages of information. Scientists and researchers aim to encode significant aspects of human civilization, including our mathematical understanding, scientific achievements, and the essence of our cultures. The hope is to create a universal language that transcends the barriers of speech and context. For instance, symbols representing mathematical concepts might serve as the first impression, showcasing intelligence before any more complex information is shared. One of the most ambitious projects in this regard is the Arecibo message, sent in 1974 from Puerto Rico. This binary-coded radio message contained basic information about humanity, such as our DNA structure, the numbers 1 through 10, and the solar system's structure. Its intent was to reach the globular star cluster M13, approximately 25,000 light-years away. This act of sending forth a message symbolized our desire to connect and share knowledge with potential extraterrestrial civilizations, no matter how far they may be. Interestingly, the practice of sending interstellar messages is rooted not only in hope, but also in the possibility of initiating a dialogue. The act of proclaiming our presence could invite responses, leading to a deeper understanding of the cosmos. Conversely, there is also the consideration of potential risks involved in revealing our location and existence. Nevertheless, the exploration continues, driven by humanity's innate curiosity about the universe and our place within it. This quest underscores the belief that perhaps one day our signals will reach a listening ear among the stars. Theories like spacetime and the multiverse offer profound insights into the nature of our universe, fundamentally altering how we perceive reality. Spacetime, a concept first formalized by Albert Einstein, merges the fabric of space with time into a single continuum. This shift in perspective means that events in the universe are not just located in space, but also intimately linked to the progression of time. It suggests that what we experience is a four-dimensional stage where time plays an active role, influencing the movement of celestial bodies and the very flow of the cosmos. On the other hand, the multiverse theory posits that our universe is only one of many, potentially infinite universes that exist simultaneously. This concept emerges from various interpretations of quantum mechanics, suggesting that every decision or occurrence can create branching realities. Each universe in this multiverse might have different physical laws or constants, leading to diverse forms of matter and life. This idea challenges the notion of a singular reality, inviting us to question the boundaries of our knowledge and the uniqueness of our own universe. Exploring both space-time and the multiverse opens doors to understanding phenomena we cannot yet fully grasp. For example, black holes challenge our notions of space-time, showcasing how time can behave differently under extreme conditions. Similarly, if the multiverse holds true, it could explain why our universe has certain fundamental constants that allow for life, as there could be countless other configurations that simply do not support such conditions. These theories not only expand our comprehension of the universe, but also ignite our imagination. They compel scientists and thinkers to envision a grander picture of existence and to consider questions about our place in the cosmos. In a way, they serve as a reminder that the universe is richer and more complex than we can fully comprehend, encouraging a spirit of curiosity and discovery that drives scientific exploration forward. Wormholes and time dilation are fascinating concepts that stretch our understanding of the universe and its laws. At the core of these ideas lies Albert Einstein's theory of relativity, which revolutionized how we perceive space and time. Time dilation is a phenomenon where time moves at different rates depending on the relative speed of objects or their proximity to massive bodies. Simply put, if you were traveling near the speed of light or were located near a black hole, time for you would slow down compared to someone far away from such influences. Wormholes, on the other hand, are theoretical passages through space-time that could create shortcuts between two distant points. Imagine a tunnel that connects two separate locations in the universe. Conceptually, if such wormholes exist, they could allow for quicker travel across vast distances, potentially even enabling time travel. However, the existence of wormholes is still purely hypothetical. They arise from the equations of general relativity, but have not been observed in reality. Integrating these concepts into our current theories of physics creates a rich tapestry of potential. For instance, researchers are investigating whether wormholes could be stabilized through exotic matter, which is still a mystery in its own right. If such stabilization were possible, it could offer profound implications, not just for travel, but for our understanding of causality and the nature of time itself. While these ideas may sound like science fiction, they form crucial inquiries in theoretical physics, pushing the boundaries of what we know about the cosmos. Scientists continue to explore and debate these concepts, hoping to unravel their complexities, potentially leading to new insights about the universe and our place within it. The interplay between wormholes, time dilation, and the fundamental fabric of space-time remains one of the most exciting frontiers in modern science. The twin paradox is a fascinating scenario in the realm of relativity that highlights the counterintuitive nature of time. It begins with twins, often referred to as Twin A and Twin B. Twin A remains on Earth while Twin B travels to a distant star at a speed close to that of light. According to the theory of relativity, as Twin B speeds off into space, time for them slows down compared to Twin A, who remains on Earth, experiencing time as usual. When Twin B eventually returns home, a surprising outcome awaits them. Due to the effects of time dilation, a phenomenon predicted by Einstein's theory of relativity, Twin B will have aged less than Twin A. This difference in aging occurs not because of an intrinsic property of the twins, but rather as a result of the incredible speeds involved and the relative motion between the two. Twin B's journey through space has altered their perception of time, demonstrating that time is not an absolute uniform experience for everyone. This paradox effectively illustrates one of the core tenets of relativity, that time is relative and can be affected by speed and gravity. Einstein's equations show that as objects move closer to the speed of light, the fabric of time itself stretches. In this way, the experience of time can vary significantly for observers in different states of motion. The twin paradox challenges our intuitive understanding of time, suggesting that what we take for granted may not apply in extreme conditions. Furthermore, the twin paradox also raises interesting discussions about the nature of reality and the relativity of simultaneity. When Twin B is moving at such remarkable speeds, their understanding of time and events differs fundamentally from that of Twin A, even if they are observing the same universe. This paradox does not just remain a thought experiment. It has been tested in real-world scenarios, such as with atomic clocks on high-speed jets, solidifying the understanding that time exists as a flexible entity, beautifully interwoven with the fabric of space itself. A greater understanding of time and space can profoundly reshape our perception of the cosmos. Historically, humanity has viewed time as a simple, linear progression, much like a straight line connecting the past to the future. However, developments in physics, particularly those stemming from Einstein's theories, reveal that time is not an absolute measure. Instead, it is intertwined with space, forming a dynamic fabric known as spacetime. This recognition elevates our understanding of the universe, allowing us to see that time can bend and stretch depending on the strength of gravity and the speed at which an object moves. This newfound perspective also enhances how we experience the vastness of the cosmos. By acknowledging the curvature of space-time, we can appreciate phenomena like black holes, where time slows immensely as one approaches the event horizon. This suggests that for someone near a black hole, time flows differently compared to someone far away. Such revelations lead to fascinating implications about the nature of reality itself, inviting us to ponder whether our experience of time is universally shared or deeply personal. Moreover, with advancements in astrophysics, we now comprehend that the universe is expanding, meaning that the distances between galaxies are growing over time. This realization challenges our previous notions of a static cosmos, allowing us to perceive space not merely as an empty void, but as an ever-changing and dynamic environment. This ongoing expansion touches on fundamental questions about the fate of the universe, compelling us to consider concepts like the Big Freeze or Big Crunch, scenarios that unfold over unimaginable periods. As we delve deeper into the mysteries of time and space, we find ourselves contemplating our place in this immense universe. This can provoke a sense of awe as we recognize that we inhabit a tiny speck in a vast expanse, shaped by forces and events beyond our comprehension. Each new discovery in the realm of cosmology only deepens this connection, urging us to reconsider not just how we see the cosmos, but how we understand our existence within it. The concept of a potentially infinite universe raises profound philosophical questions that have sparked debates among thinkers for centuries. If the universe is indeed infinite in extent and possibly in time, it challenges our traditional understanding of existence, reality, and our place within it. One major implication is the idea of the multiverse, where countless universes exist alongside our own, each with different laws of physics, histories, and potentialities. This notion prompts us to reconsider the uniqueness of our existence, suggesting that everything that can happen or exist may already be realized in some form across this vast cosmic tapestry. Moreover, an infinite universe can influence our understanding of fate and free will. If every possibility is enacted somewhere, it leads to intriguing discussions about determinism. Are our choices truly free, or are they merely reflections of a multitude of trajectories already set within the infinite fabric of reality? In this light, the philosophical inquiry becomes one of reconciling our experiences of choice and consequence with a universe that allows every outcome to occur, where every possible version of ourselves plays out in parallel realms. Then there's the issue of meaning and significance. In a universe that stretches infinitely in all directions and time, our lives can seem minute and fleeting. Yet this infinitude can also inspire a sense of awe and connection, illustrating that even the tiniest events, thoughts, and actions resonate through the cosmos in ways we might not fully grasp. This duality moves us to ponder what it means to be significant in a possibly boundless context and encourages a search for meaning amidst the vastness. In grappling with these implications, we find ourselves at the intersection of science and philosophy. A potentially infinite universe invites us to explore not just the mechanics of cosmic phenomena, but also our attitudes and beliefs about existence itself. While science provides us with data and models of how the universe operates, philosophy enriches our understanding by examining the deeper meanings and implications of those truths, reminding us that the journey of discovery is as infinite as the universe we seek to comprehend. Throughout the vastness of the cosmos, astronomers have unearthed a number of intriguing anomalies that challenge our understanding of the universe. One such discovery is the mysterious fast radio bursts, or FRBs. These are brief, intense bursts of radio waves from distant galaxies lasting mere milliseconds. The precise origins of these bursts remain elusive. While some scientists theorize they could be the results of neutron-star collisions or black hole mergers, others suggest they might even be signals from extraterrestrial civilizations. The uncertainty surrounding their source adds to their allure. Another captivating anomaly in our universe is the Great Attractor. Located nearly 200 million light-years away, this region of space appears to be exerting a gravitational pull on our galaxy and several others. The Great Attractor is not easily visible, as it is hidden behind the dense plane of our Milky Way. This gravitational anomaly has led astronomers to question the distribution of mass in the universe and hints at the presence of large-scale structures that we have yet to fully comprehend. Then there's the phenomenon known as dark matter, an enigmatic substance making up about 27% of the universe. Despite its abundance, dark matter cannot be seen directly. Instead, researchers infer its existence through the gravitational effects it has on visible matter. This invisible matter causes galaxies to rotate in ways that cannot be explained by the mass we can observe. The search for dark matter particles is akin to detective work, piecing together clues from the cosmos. Lastly, consider the oddly placed galaxies, like the Antlia II. This galaxy has been described as an extreme example of a dark matter-dominated galaxy. Its structure is vast yet faint, making it incredibly challenging to study. These anomalies not only spark our curiosity, but also remind us that the universe is full of surprises, often forcing us to rethink what we know about the nature of reality itself. Each discovery enriches our understanding while igniting a desire to know even more. The Great Attractor is a massive gravitational anomaly located towards the center of our own Milky Way galaxy, hidden behind the dense star fields and gas of the galactic plane. It is a region that exerts a detectable force on our galaxy, as well as several others nearby. This phenomenon has proven to be a conundrum for astronomers and physicists alike, challenging our understanding of the structure and behavior of the universe. One of the most profound challenges posed by the Great Attractor is its unpredicted influence on the motion of galaxies. Observations indicate that our galaxy is being drawn towards this immense region of mass at significant speeds. This pulling force suggests a concentration of matter that doesn't align with previous models of the universe, which often assumed a more homogeneous distribution of mass across vast distances. Instead, the presence of such a concentrated anomaly hints at the existence of vast structures that we are only beginning to comprehend. Additionally, studies of the Great Attractor have proved that dark matter, a mysterious form of matter that does not emit light or energy, plays a significant role in cosmic dynamics. The gravitational forces at play in this region challenge the traditional theories that rely heavily on visible matter for explanations. Instead, researchers are compelled to consider the unseen elements of the universe that impact the movement and interaction of galaxies, adding layers of complexity to our models of cosmic evolution. As scientists continue to explore the Great Attractor, they are encouraged to refine their theories about the universe's large-scale structure. This object serves as a reminder that the cosmos is filled with mysteries that expand our understanding and challenge our assumptions. The interplay of visible and dark matter, the dynamics of cosmic structures, and the gravitational pulls of these massive anomalies open new doors to research, illustrating how much we still have to learn about the universe that surrounds us. The Oort cloud is a vast, spherical shell of icy objects that lies on the outer fringes of our solar system. It is named after the Dutch astronomer Jan Oort, who first proposed its existence in the 1950s. This cloud is thought to be a reservoir for comets, consisting of billions of icy bodies that formed in the early solar system. It lies roughly 1 to 2 light-years from the Sun, which means it is far beyond the orbit of Pluto and the other known planets. Cometary activity arises when these icy bodies are disturbed, often by the gravitational influence of nearby stars or interactions with other celestial objects. When a comet from the Oort cloud is nudged toward the inner solar system, it begins to approach the Sun. The heat from the Sun causes the icy nucleus of the comet to sublimate, turning solid ice directly into gas. This creates the beautiful glowing coma and tail that we associate with comets as they travel through space. Interestingly, the Oort cloud is believed to be the source of long-period comets, which have orbits that can take them hundreds or even thousands of years to complete. These comets often come from the far reaches of the Oort cloud and can appear unexpectedly, captivating skywatchers with their bright tails and spectacular displays. In contrast, short-period comets typically originate from a different region known as the Kuiper Belt, which is located closer to the Sun. The study of the Oort cloud and its comets offers valuable insight into the early solar system's formation and evolution. Comets are considered time capsules, preserving the original materials that formed the planets. As scientists continue to learn more about these objects, they deepen our understanding of not just our solar system's history, but also the dynamics of celestial mechanics in the vast universe. The mystery of the Oort cloud remains a tantalizing frontier in the exploration of our cosmic neighborhood. Cosmic rays are high-energy particles that originate from outer space and constantly bombard Earth's atmosphere. These particles are mainly protons, along with heavier nuclei and electrons, and they travel at nearly the speed of light. While our planet's atmosphere and magnetic field offer substantial protection, cosmic rays can still have significant implications for both space exploration and technology on Earth. In the realm of space exploration, cosmic rays pose a serious risk to astronauts. When humans venture beyond the protective layers of Earth, they become exposed to these high-energy particles. The impact of cosmic rays can lead to increased radiation dose, which raises the risk of cancer over time and can negatively affect the central nervous system. Agencies like NASA consider radiation exposure a major challenge for long-duration missions, such as trips to Mars. As a result, research is ongoing to develop effective shielding methods and countermeasures to protect astronauts in deep space. Back on Earth, cosmic rays can interfere with technological systems, especially those relying on sensitive electronics. For instance, they can cause single-event upsets, where a cosmic ray particle strikes the microelectronic circuitry of satellites or computers, leading to errors in data or even system failures. Some satellites are specifically designed with radiation-hardened components and redundancy to maintain functionality despite this interference. This vigilance accounts for the persistent threat posed by cosmic rays to our technology and communication systems. Interestingly, cosmic rays also contribute to scientific research in other ways. They aid in the understanding of the universe's origins and the fundamental processes of particle physics. High-energy cosmic rays help determine the interplay between cosmic forces and the behavior of matter under extreme conditions. While they may pose challenges to astronauts and technology on Earth, the study of cosmic rays fosters advances in both our understanding of the universe and the development of protective measures in our increasingly technology-dependent lives. The universe is a vast and mysterious expanse filled with wonders that often go unnoticed. One of these intriguing marvels is the phenomenon known as pulsars, which are rapidly spinning neutron stars that emit beams of radiation. Imagine a lighthouse in space, where the lighthouse is a compact star that rotates several times a second, sending out beams of energy in a precise pattern. For astronomers, observing pulsars can be like a cosmic clock, providing remarkable insights into the fabric of space and time. Another lesser-known wonder resides in the realm of black holes, particularly in the form of supermassive black holes, which can be found at the centers of most galaxies. While many are familiar with the idea that black holes are points of no return, the size of these cosmic giants is astounding. Some supermassive black holes can have masses equivalent to millions or even billions of suns, warping the very space-time around them. Their strong gravitational pull influences everything in their vicinity, drawing in stars and gas, creating stunning accretion disks that shine brightly as matter spirals inward. Yet another cosmic phenomenon is the immense cosmic web that connects galaxies across the universe. This web is formed by dark matter, which does not emit light and is thus invisible to us. However, its gravitational effects shape the universe's structure. The strands of this web guide galaxies, forming clusters and filaments that stretch across vast distances. It's a beautiful yet eerie sight, one that illustrates the intricate ballet of cosmic forces at work. Lastly, let's not overlook the enchanting orbs of ice and rock known as comets. Though we often think of them as fleeting visitors from the outer reaches of our solar system, their journeys tell tales of the solar system's formation. As they approach the sun, the heat causes their icy cores to sublimate, creating breathtaking tales that can stretch for millions of kilometers. These ancient travelers not only captivate us with their beauty, but also hold clues to the origins of water and organic materials on Earth, hinting at a deeper connection between our planet and the cosmos. As we gaze into the vastness of the cosmos, we are met with the profound question of the universe's ultimate fate. Current scientific theories suggest a range of possibilities for what may happen to our universe in the distant future. The most widely accepted idea is known as the Big Freeze. According to this theory, the universe continues to expand at an accelerating rate due to a mysterious force called dark energy. Over billions of years, galaxies will drift further apart, and the universe will cool down as stars burn out, leading to a dark and cold cosmos. Alternatively, some scientists propose the Big Crunch scenario. In this vision, if the density of the universe were to be high enough to counteract its expansion, gravitational forces might eventually pull everything back together. This could culminate in a cataclysmic collapse where all matter and energy converge to a single point. However, current observations indicate that this outcome is less likely given the accelerated expansion of the universe we are witnessing today. Another fascinating idea is the Big Rip hypothesis. This theory suggests that dark energy might become increasingly potent, ultimately causing galaxies, stars, planets, and even atoms to tear apart in a dramatic conclusion. In this scenario, the universe reaches a state where it can no longer sustain itself, leading to a chaotic dissolution of structures on a cosmic scale. All of these theories illuminate how our understanding of the universe is shaped by the physical laws that govern it. While we may not know for certain what lies ahead, the ongoing exploration of cosmic phenomena and the pursuit of knowledge continue to expand our comprehension of the universe's fate. Each new discovery adds a piece to an incredibly complex puzzle that connects us to the very fabric of existence. The concept of the Big Freeze presents a fascinating maximum expansion scenario for the universe. The Big Freeze predicts that the universe continues to expand indefinitely. Over time, galaxies would drift further apart, and as this expansion accelerates, the universe would ultimately become increasingly cold and dark. Stars would burn out, and new stars would cease to form, leading to a cosmic landscape dominated by black holes, neutron stars, and the remnants of stars long extinguished. Eventually, the universe would reach a state of maximum entropy, where no thermodynamic activity could occur, resulting in a vast, lifeless expanse. In contrast, the Big Crunch posits a dramatically different fate. This scenario suggests that if the density of matter in the universe were high enough, gravitational forces could eventually stop the expansion and pull everything back together. The universe would contract over billions of years, leading to a collapse where galaxies, stars, and cosmic structures would merge, ultimately creating a singularity, a point of infinite density. The Big Crunch evokes the image of an inverse Big Bang, possibly leading to conditions that are remarkably similar to those at the universe's inception. Then, we have the Big Rip, which presents yet another perspective on cosmic evolution. This theory hinges on the behavior of dark energy, the mysterious force believed to be driving the acceleration of the universe's expansion. In the Big Rip scenario, dark energy increases in intensity over time, leading to a situation where the expansion accelerates to such an extent that it tears apart galaxies, stars, and even atoms. The universe would experience a literal disintegration, culminating in a dramatic endpoint where everything is stretched apart beyond recognition. The Big Freeze, Big Crunch, and Big Rip each represent distinct trajectories for the fate of our universe, framed by the interplay of cosmic forces. While the Big Freeze suggests a serene oblivion reached over an eon, the Big Crunch hints at a catastrophic return to singularity, and the Big Rip implies a violent end driven by dark energy. Together, these theories paint a mesmerizing picture of cosmic destiny, each equally captivating in its potential implications for our ultimate fate among the stars. Entropy plays a crucial role in understanding the fate of the universe. In simple terms, entropy is a measure of disorder or randomness in a system. In thermodynamics, it reflects how energy is distributed among the particles in that system. As the universe expands and evolves, entropy tends to increase, leading to a state where energy becomes more evenly spread out and less available for doing work. This tendency toward disorder has profound implications for the long-term future of our universe. At the cosmic level, the second law of thermodynamics states that in an isolated system, entropy will never decrease. As stars burn through their fuel, they produce energy and light, but they also generate waste heat, increasing the overall entropy in the universe. Over billions of years, the stars will exhaust their fuel, and galaxies will drift apart. This gradual decline in organized structures will lead to a more chaotic and less usable energy state, a scenario often referred to as the heat death of the universe. In this end state, energy will be so evenly distributed that stars will have burned out and galaxies will no longer form. The universe would become a dark, cold expanse, with the remnants of stars and black holes peppered throughout. While the universe will persist, it will be in a state of maximum entropy, devoid of the complex structures that sustain life as we know it. This concept of increasing entropy prompts profound philosophical questions about existence and time. As we contemplate the universe's ultimate fate, we are drawn into a deeper appreciation for the transient nature of stars, galaxies, and life itself, reminding us that everything is bound by the laws of thermodynamics. Thus, Entropy not only shapes the physical evolution of the universe, but also our understanding of how life and the cosmos coexist in a delicate balance. Black holes, those enigmatic regions of space with gravitational pulls so strong that nothing can escape from them, play a critical role in shaping theories about the future of our universe. As scientists and astronomers study these fascinating objects, they uncover insights that inform predictions about the eventual fate of all cosmic matter. Black holes are not just endpoints for massive stars, they also provide a unique link between the present state of the universe and its distant future. One significant aspect of black holes is their potential to contribute to a phenomenon known as the Big Freeze. In this scenario, the universe continues expanding indefinitely, causing galaxies to drift further apart. As stars burn out and galaxies fade into darkness, black holes will remain. Over an unimaginably long timescale, they could collide and merge, forming even larger black holes. This process not only alters the distribution of matter in the universe, but also influences the very fabric of space and time. Another theory, called the Big Crunch, suggests that the universe might eventually stop expanding and start contracting, leading back to a singularity similar to the one that sparked the Big Bang. Black holes are crucial in this model, as their gravitational influence could theoretically pull galaxies back together. In this scenario, the gravitational pull of accumulating black holes could escalate, resulting in a dramatic end to cosmic expansion. However, current observations favor the idea of continued expansion, raising essential questions about the role of dark energy, a mysterious force driving this acceleration. Finally, we cannot ignore the future role of black holes in the context of information theory and the fate of information itself. When matter falls into a black hole, the question arises about what happens to the information contained within that matter. Some scientists propose that black holes might eventually evaporate through a process known as Hawking radiation, potentially releasing information back into the universe. This theory could have profound implications for our understanding of time, space, and the continuity of information in an ever-evolving universe. Black holes represent a crossroads of cosmological theories, impacting the trajectory of the universe itself. Their role in the cosmic narrative captivates scientists and fosters curiosity among those eager to understand the mysteries of existence. As we continue to explore and learn about these fascinating phenomena, the questions surrounding their contributions to the universe's future will only deepen, reminding us of the ever-unfolding story of time and space. The universe, with its vastness and complexity, remains a subject shrouded in mystery, especially concerning its ultimate fate. While scientists have proposed various theories about how the universe could end, many unknowns still linger, leaving room for speculation and ongoing research. One of the primary questions concerns the role of dark energy, a force that seems to be driving the accelerated expansion of the universe. Although we know it exists, its nature and how it will influence the universe's destiny are still not fully understood. Several scenarios have been theorized based on our current knowledge. The Big Freeze predicts that as the universe expands indefinitely, galaxies will drift apart and stars will eventually burn out, leaving a cold, dark, and lifeless cosmos. Conversely, the Big Crunch suggests that the gravitational pull of all matter could eventually halt this expansion and reverse it, leading the universe to collapse back into a singular point. However, the likelihood of these outcomes greatly depends on the behaviors and properties of dark energy, which still elude our scientific grasp. Another theory, known as the Big Rip, presents an equally fascinating yet unsettling scenario. In this model, the accelerated expansion driven by dark energy might intensify over time, tearing apart galaxies, stars, planets, and even atoms. This prospect raises profound questions about the fundamental forces of the universe, pushing scientists to delve deeper into the nature of dark energy and the structure of space-time. The interactions between these forces remain largely theoretical and demand much more investigation. In addition to these scenarios, the possibility that our universe could be just one of many, part of a multiverse, introduces further uncertainties. Each universe within this hypothetical framework could follow its own distinct laws of physics, leading to an array of possible endings. As researchers continue to unveil the cosmos's secrets, the unknowns surrounding the universe's final fate remind us that we are merely scratching the surface of understanding the vastness of space and time. The answers may reside in areas of physics we have yet to explore, enticing us to keep looking to the stars. Our understanding of the universe has undergone a profound evolution that reflects the progress of human thought and discovery over centuries. In ancient times, civilizations such as the Babylonians and Greeks gazed at the stars and created mythologies that explained their observations. Early astronomers like Ptolemy proposed geocentric models, suggesting that the Earth was at the center of the universe, encircled by the celestial bodies. This view dominated for nearly 1,000 years, shaping not only our understanding of the cosmos, but also our place within it. The Copernican revolution was a pivotal moment in our quest for knowledge. In the 16th century, Nicholas Copernicus challenged the long-held geocentric view, proposing that the Sun, not the Earth, was at the center of our solar system. This radical idea laid the groundwork for future astronomers. Galileo Galilei, with his powerful telescope, confirmed Copernicus's theory by observing the moons of Jupiter and the phases of Venus, providing crucial evidence that supported a heliocentric model of the universe. As we moved into the Age of Enlightenment and beyond, our grasp of the universe expanded. Sir Isaac Newton synthesized earlier discoveries and introduced the laws of motion and universal gravitation, which offered a framework for understanding celestial mechanics. His work enabled predictions of planetary movements and began to unveil the systematic nature of the universe, leading to the acceptance of a more dynamic and complex cosmic landscape. In the 20th century, we entered a new era with the development of modern physics and cosmology. The observation of the redshift of light from distant galaxies led to the revolutionary realization that the universe is expanding. This discovery, along with the formulation of the Big Bang theory, transformed our understanding of how the universe evolved from a hot, dense state into the vast cosmic expanse we observe today. Today, with advancements in technology and methods, such as the Hubble Space Telescope and the study of cosmic microwave background radiation, we continue to unravel the mysteries of the universe, discovering more about dark matter, dark energy, and the fundamental laws governing the cosmos. Each step forward in knowledge reminds us just how dynamic our comprehension of the universe truly is. Space exploration has profound cultural and philosophical implications that reach far beyond the mere act of sending spacecraft into the cosmos. As we look up at the stars, we are confronted with the questions of our own existence, our place in the universe, and our responsibilities as stewards of Earth. Different cultures have long viewed the heavens as a canvas of mystery and inspiration. The ancient civilizations, from the Egyptians to the Mayans, crafted myths and stories that intertwine with the movement of celestial bodies. These stories not only shaped their understanding of time and life, but also influenced their rituals and spirituality. In contemporary times, space exploration challenges us to reconsider what it means to be human. As we send robots and astronauts beyond our planet, we encounter new ethical dilemmas and responsibilities toward life forms we may discover, whether on Mars or moons like Europa. The prospect of encountering extraterrestrial intelligence raises critical questions. What rights do these beings have? How should we interact with them, if we ever find them? These considerations compel us to redefine our relationships, not only with other potential life, but also with our planet, urging us to reflect on the urgency of sustainability and compassion in our choices. One important cultural shift brought about by space exploration is the increasingly shared perspective on our planet. Observing Earth from space, astronauts often report a profound sense of connection to humanity and nature. This phenomenon, known as the overview effect, has inspired a growing movement for global cooperation, unity, and environmental stewardship. As we see the delicate blue planet suspended in the void, it becomes a vivid reminder that we must protect our home for future generations. This broader perspective fosters an appreciation for our planet's fragility, influencing movements for conservation and the responsible use of resources. Philosophically, space exploration invites us to expand our understanding of the cosmos and ourselves. It deepens the inquiry into fundamental questions about existence, prompting us to ponder the significance of life beyond Earth. Are we the only intelligent beings, or is the universe teeming with life? Each mission into space serves as a step toward answering these timeless questions, compelling us to contemplate the very fabric of reality itself. Through this lens, the journey into space is not just a scientific endeavor. It becomes a profound quest for knowledge, meaning, and connection that spans cultures and centuries, inviting everyone to ponder the great mysteries that lie beyond our home planet. The study of the universe has profoundly influenced human creativity, inspiring artists, musicians, and writers for centuries. Artists have often turned to the cosmos for inspiration, creating works that reflect our understanding of space and our place within it. The vastness and beauty of celestial bodies can evoke wonder, resulting in artworks that capture the shimmering stars, swirling galaxies, and the intricate dance of planetary systems. From the night skies depicted in Vincent van Gogh's famous painting Starry Night, to the intricate designs in ancient cultures' representations of the heavens, the universe has provided a limitless canvas for expression. In music, the cosmos has equally played a significant role in inspiring soundscapes that evoke the mystery of the infinite. Composers have translated the rhythms of the universe into melodies and harmonies. For instance, Gustav Holst's The Planets Suite embodies the traits of different celestial bodies, transforming the essence of Mars, Venus, and Jupiter into orchestral music that resonates with listener emotions. The grandeur of the universe becomes not only a backdrop, but a central theme, allowing audiences to experience a sense of wonder through sound. Literature, too, reflects the influence of cosmic exploration. Writers have crafted narratives that explore themes of existence, the unknown, and the human condition through the lens of the universe. Science fiction, in particular, has blossomed with the dawn of space exploration, allowing authors to imagine distant worlds and engage with profound philosophical questions. Works like Arthur C. Clarke's 2001: A Space Odyssey and Ray Bradbury's The Illustrated Man not only speculate about the future of humanity and the cosmos, but also explore deeper existential themes, merging science with profound inquiries about life and our purpose in the universe. The cosmos has become a wellspring of inspiration, shaping how we express and explore the human experience. From the breathtaking depictions in visual art to the awe-inspiring compositions in music and the thought-provoking narratives in literature, our understanding of the universe continues to encourage creativity and deepen our connection to our surroundings, both earthly and cosmic. Throughout history, diverse cultures have looked to the sky, interpreting cosmic events in ways that reflect their unique worldviews, religions, and societal norms. For many ancient civilizations, celestial bodies like the sun, moon, and stars were not just distant objects, they were imbued with meaning and often personified as deities. For instance, the ancient Egyptians revered the sun god Ra, associating him with life, death, and rebirth. This connection led to their meticulous observation of cosmic events, which were often integrated into their agricultural practices and religious ceremonies. In contrast, indigenous peoples of North America often viewed the cosmos through a narrative lens, using constellations as a framework for storytelling. The Lakota, for example, see the stars as guides and educators, infusing their myths with the lessons derived from the night sky's patterns. This storytelling approach not only helped in navigation but also fostered a deep respect for nature, as the positions of stars and planets were believed to influence earthly events, such as seasons and animal migrations. In Asian cultures, particularly in Chinese astronomy, there exists a rich tapestry of celestial lore that intertwines with philosophy and medicine. The Chinese zodiac, with its 12 signs based on lunar cycles, demonstrates how time and fate are interconnected. Events like solar eclipses and meteor showers were meticulously documented in historical texts, often interpreted as omens or signals from the divine, infusing the cosmos with both fear and reverence. Moving into the contemporary world, modern interpretations of cosmic phenomena often blend traditional beliefs with scientific understanding. People around the globe regularly celebrate events like solar eclipses and meteor showers, embracing both the spectacle and the science behind them. These cosmic occurrences continue to stir universal wonder, bridging cultural divides and fostering a collective appreciation for the mysteries of the universe. In this way, the cosmos serves not just as a stage for celestial events, but as a mirror reflecting the rich tapestry of human culture and belief. The discovery of cosmic phenomena has profoundly shaped human self-perception and our understanding of our place in the universe. For centuries, civilizations viewed the Earth as the center of existence, a belief known as geocentrism. This view was profoundly challenged by the heliocentric model proposed by Copernicus, which positioned the Sun at the center of our solar system. As technology advanced and astronomers like Galileo and Kepler made observations of celestial bodies, this shifted our focus away from the Earth, revealing our planet as just one small part of a vast cosmos. As we continued to explore the universe, the realization that we live on a relatively small planet, orbiting an average star in a galaxy filled with billions of stars, prompted a profound existential reflection. The advent of space exploration, especially with missions like the Hubble Space Telescope, expanded our perspective on the universe. Images of distant galaxies, nebulae, and even the eerie beauty of our own Milky Way have illustrated how small and interconnected we truly are. This reality can be both humbling and awe-inspiring, evoking a sense of wonder and curiosity about the universe and our significance within it. Furthermore, the discovery of cosmic phenomena such as black holes, pulsars, and the cosmic microwave background radiation has spurred scientific inquiry and a new age of understanding in physics. Discoveries such as the Big Bang theory have shifted the narrative from creation myths to a scientific account of our universe's origins and evolution. This can lead to deep philosophical questions about life, consciousness, and the nature of existence itself, prompting people to re-evaluate their beliefs, cultures, and connections to one another. Ultimately, these cosmic discoveries encourage us to view ourselves not only as inhabitants of Earth, but as part of a broader cosmic narrative. This perspective invites us to consider the huge questions of why we are here and what our role may be in the grand scheme of the universe. As we continue to explore the cosmos, our understanding of ourselves and each other is likely to evolve further, guiding future generations in their quest for knowledge and meaning in an ever-expanding universe. The limitations of current space travel significantly shape our ability to explore the vast universe. As of now, humans rely on chemical propulsion systems, primarily based on rocket technology that has remained relatively unchanged for decades. These systems are effective for reaching low Earth orbit and traveling to the Moon or Mars, but they have constraints, especially when it comes to the distances involved in deeper space exploration. For example, journeys to the nearest star system, Alpha Centauri, could take over 4 years, even if we traveled at the speed of light, which is impossible with our current technology. Moreover, the challenges of human endurance in space add another layer of complexity. Prolonged exposure to microgravity can lead to serious health issues, including muscle atrophy and bone density loss. Protecting astronauts from harmful radiation during extended missions is another significant hurdle. Current spacecraft lack adequate shielding to provide safety from cosmic rays and solar radiation outside the protective envelope of Earth's atmosphere. These health risks necessitate a careful approach to long-term missions, making deep space travel more complicated and therefore slower. Financial constraints also play a critical role in limiting the scope of space exploration. Space missions are expensive endeavors that require extensive funding and resources. National space agencies and private companies are continuously trying to innovate and refine technology to make missions more economical. But budget limitations still dictate how far we can reach and how often we can send missions into space. The need for international collaboration has never been more important, as pooling resources and knowledge can enhance our exploratory efforts and reduce costs. While our current technologies impose restrictions, they also inspire innovation. Concepts like ion propulsion or solar sails show promise for future exploration, potentially allowing us to travel deeper into space and study celestial bodies that are currently beyond our reach. As we develop new technologies and learn from each mission, humanity's journey into the cosmos will continue to evolve, pushing the boundaries of what we know and where we can go beyond the confines of our home planet. As we look toward the future of space exploration, humanity's ambitions are soaring to new heights, both literally and figuratively. One of the most audacious goals is the establishment of a sustainable human presence on the Moon. The Artemis program, led by NASA, aims to send astronauts back to the lunar surface in the coming years. But beyond just landing, The plan includes building a base to support long-term exploration. This would serve as a jumping-off point for deeper exploration into our solar system. Simultaneously, Mars is capturing our imagination more than ever. Numerous missions are planned to explore the Red Planet, with the ultimate goal of sending humans there by the 2030 organizations like SpaceX envision colonization, while NASA's Perseverance rover is currently gathering data that could one day assist human explorers. The potential for the discovery of life, past or present, adds an extraordinary layer to these plans. Terraforming Mars, or making it habitable for humans, is yet another ambitious concept that scientists are beginning to explore. On a broader scale, there are initiatives aimed at exploring the outer planets of our solar system, particularly Jupiter and its intriguing moon, Europa. Scientists believe that under its icy surface lies an ocean that may harbor conditions suitable for life. Missions like the Europa Clipper, set to launch in the coming years, will study this moon further, looking for signs of life and understanding its environment. The search for extraterrestrial life is a guiding force behind many future missions. Beyond our solar system, the quest for exoplanets has gained tremendous momentum. New telescopes like the James Webb Space Telescope are enhancing our ability to detect planets in other star systems. The ultimate ambition is to find a potentially habitable planet, akin to Earth, and learn more about the possibilities of life beyond our solar system. As we push the boundaries of what we know, these ambitious goals remind us of the insatiable human desire to explore and understand our place in the cosmos. As we look into the future of space exploration, advancements in technology promise to revolutionize our capacity to venture beyond our solar system like never before. The development of more powerful telescopes, for instance, has already begun to change our understanding of distant exoplanets. With improved resolution and sensitivity, these new instruments allow scientists to identify planets orbiting other stars, some of which may even harbor conditions suitable for life. This lays the groundwork for targeted exploration efforts in the years to come. Moreover, propulsion technology is undergoing rapid advancements that will transform our journey through space. Traditional chemical rockets, while effective, limit the speed at which we can travel. New concepts like ion propulsion and nuclear thermal propulsion strive to significantly increase the velocity of spacecraft. These systems use advanced methods to harness energy more efficiently, promising quicker trips to our cosmic neighbors and reducing the travel time to potentially habitable worlds. Imagine reaching the closest star system, Alpha Centauri, within just a couple of decades rather than tens of thousands of years. This could soon shift from science fiction into realistic planning. Additionally, developments in artificial intelligence could greatly enhance the exploration of our universe. AI can analyze vast amounts of data far more quickly and accurately than humans, allowing for better mission planning and execution. It can identify promising signals from distant stars or analyze the composition of an exoplanet's atmosphere. This could help researchers prioritize which destinations are worth investigating and enable space agencies to focus their resources efficiently. As we stand on the brink of these technological breakthroughs, the dream of exploring beyond our solar system feels more achievable than ever. With improved telescopes, revolutionary propulsion systems, and the power of artificial intelligence at our fingertips, humanity's journey into the cosmos is set to progress in ways we are just beginning to imagine. The universe, vast and mysterious, beckons, and we are preparing to answer that call. As humanity gazes toward the stars, the prospect of space colonization beckons with both promise and challenge. One of the most pressing ethical considerations is the question of ownership. If we venture to Mars or the Moon, who has the right to claim these celestial bodies? International treaties, like the Outer Space Treaty of 1967, declare that space is the province of all humankind. Yet, as technology advances, the potential for private ownership and exploitation raises complex moral dilemmas. Can we justify colonizing another world when there's still so much to be resolved here on Earth? Another vital concern involves the potential impact on any life forms that may exist in outer space. Should we discover microbial life on another planet, the ethical imperative to protect it becomes paramount. Colonization efforts could inadvertently harm or even extinguish these ecosystems. This calls into question both our responsibility as caretakers of life and the motivations behind our exploratory spirit. Are we driven by wonder and curiosity, or by the impulse to conquer and exploit. Additionally, the social and cultural implications of space colonization cannot be overlooked. Any futuristic society we establish in outer space will likely reflect the values and structures of those who create it. This raises concerns about creating new forms of inequality or mirroring the injustices and conflicts found on Earth. As we consider creating new communities in space, we must think about how to build inclusive societies that respect diversity and foster cooperation rather than division. Finally, there is the consideration of our own psychology as we leave Earth behind. The experience of living on another planet will not just impact those who venture forth, but could reverberate back to our home planet. What lessons will we learn about sustainability, society, and humanity itself as we explore beyond our atmosphere? The ethical implications of space colonization challenge us to reflect on who we are and who we aspire to be as a species venturing into the cosmos. As humanity stands on the cusp of unprecedented exploration in the coming decades, prioritizing our efforts will be crucial. We are entering an era where advancements in technology and science pave the way for exploration beyond our planet. Among the key areas of focus will likely be the Moon, Mars, and the broader expanse of deep space. Each destination presents unique challenges and opportunities for understanding not just our place in the universe, but also the implications for life on Earth. The Moon is poised to be a primary target for exploration. With plans for human missions returning to its surface, this celestial body serves as a testing ground for technologies that could one day support missions to Mars and beyond. The Moon's resources, such as water ice located in permanently shadowed craters, could be vital for sustaining a human presence, supplying oxygen and even fuel for deeper space missions. Additionally, the Moon offers a unique vantage point for astronomical observations, unhindered by Earth's atmosphere. Meanwhile, Mars captures the imagination of many scientists and space enthusiasts alike. The ongoing exploration by rovers has revealed a landscape that once bore water, raising questions about its potential to have hosted life. As we examine the Martian soil and atmosphere, we seek to understand not only whether life ever existed there, but also if we could potentially live on Mars in the future. This ambition will push our technological and scientific boundaries, fueling innovations that could also benefit life on Earth. Beyond planetary exploration, our gaze is increasingly set towards deep space, particularly with missions to asteroids and the outer planets. These bodies hold clues about the early solar system and the formation of Earth itself. Efforts to capture small asteroids for sample return missions promise to deepen our understanding of organic materials and the building blocks of life. In balancing these exploration efforts, humanity will not only seek knowledge, but also endeavor to safeguard our planet, understanding the delicate and interwoven fabric of life across the cosmos. Throughout the history of cosmology, each mystery that science has unraveled has often opened the door to even more intriguing questions. When a celestial riddle is solved, scientists gain crucial insights into the workings of the universe, but these answers typically raise additional queries, much like peeling the layers of an onion. This process of discovery is fundamental to scientific progress, wherein clarity in one area often highlights the shadows in another. For instance, when researchers first understood the phenomenon of black holes, they celebrated the completion of a puzzle that had perplexed them for decades. However, this achievement sparked deeper inquiries about the nature of space and time around these mysterious entities. Questions arose about what happens inside a black hole, whether information is lost forever, and how they relate to the evolution of the universe itself. Each answer generates a ripple effect, challenging scientists to consider where their understanding ends and the mystery begins. Likewise, the discovery of dark energy was a watershed moment in cosmology. Researchers had initially aimed to measure the rate of expansion of the universe, only to find that it was accelerating due to this enigmatic force. This new knowledge did not conclude the inquiry. Instead, it propelled further studies that seek to uncover what dark energy is, how it fits into the cosmic puzzle, and its long-term implications on the fate of the universe. As we advance our grasp of cosmic phenomena, new technologies and methods also emerge that allow us to ask different kinds of questions. With each resolution, we discover more intricate layers of the universe, deepening our understanding while simultaneously expanding the frontiers of knowledge. In this way, solved mysteries become stepping stones leading to ever more profound questions, reflecting the dynamic and evolving nature of scientific exploration. Theoretical physics plays a pivotal role in unraveling the mysteries of the cosmos. At its core, this branch of science allows researchers to develop models and frameworks that explain the fundamental forces and particles that govern the universe. Unlike experimental physics, which relies on observations and experiments, theoretical physics explores concepts mathematically and imaginatively, forging pathways into understanding phenomena that are not yet directly observable. One of the most significant contributions of theoretical physics is its ability to make sense of the unseen forces that shape our universe. For instance, consider dark matter and dark energy, two enigmatic components that constitute about 95% of the total mass energy content of the universe. Although we cannot detect them directly, theoretical physicists utilize formulas and cosmological principles to infer their existence and influence on cosmic structures. This approach helps us to form a more complete picture of the universe, pushing the boundaries of traditional knowledge. Additionally, theoretical physics allows us to explore the early stages of the universe and events like the Big Bang. By applying concepts from quantum mechanics and general relativity, physicists can create models that simulate conditions just after the birth of our cosmos. These models generate predictions that, although they may not yet be testable with current technology, pave the way for future discoveries and experiments that could confirm or challenge these theoretical frameworks. Theoretical physics serves as a guiding beacon, illuminating the dark corners of our understanding. It invites us to ponder profound questions about existence, unfolding new realms of thought as we strive to comprehend cosmic enigmas. Each new theory adds another layer to our rich tapestry of knowledge, welcoming intrigue and curiosity in our collective journey through the universe. Scientists navigate the intricate relationship between empirical evidence and theoretical conjecture with a thoughtful and disciplined approach. Empirical evidence is the backbone of scientific inquiry, derived from observations, experiments, and data collection. Theories, on the other hand, are frameworks that help to explain and predict phenomena based on existing knowledge. The balance between these two essential components is critical to advancing our understanding of the universe. To achieve this balance, scientists begin by formulating hypotheses, which are educated guesses grounded in theoretical frameworks. These hypotheses guide experiments designed to test predictions. For example, when scientists proposed the theory of gravity, they observed falling objects and crafted experiments to measure their motions. The outcomes of these experiments generate empirical evidence that either supports or refines the original theoretical conjecture. However, empirical data alone isn't enough. Interpretation plays a key role. Scientists must critically evaluate their findings, often comparing them with existing theories. If observations align with predictions, it provides strong support for the theory. Conversely, if there's a discrepancy, it can lead to new inquiries, revisions of the theory, or even the development of entirely new concepts. This dynamic interplay fosters a culture of continual discovery, leading to a more profound comprehension of the natural world. Ultimately, the relationship between empirical evidence and theoretical conjecture is symbiotic. Theories fuel the design of experiments, while empirical data informs the evolution of these theories. Together, they drive scientific progress, leading to breakthroughs that enhance our understanding of complex phenomena, from the minutiae of particle physics to the vast expanses of cosmology. This balance is not just a method of inquiry, it is the essence of what makes science a powerful tool for unraveling the mysteries of our universe. Cosmology is a fascinating field filled with profound questions that invite stretching the imagination and driving scientific inquiry. Among the most pressing mysteries are those surrounding dark matter and dark energy. Although we can observe their effects, their true nature remains elusive. Dark matter, which makes up about 25% of the universe, does not emit light or energy, making it invisible and detectable only through its gravitational influence. Dark energy, on the other hand, is thought to account for nearly 70% of the universe and drives its expansion. The big question here is, what are these entities made of, and how do they interact with the visible matter we can observe? Another significant inquiry centers around the origins of the universe itself. The Big Bang theory provides a widely accepted framework for understanding how the cosmos began approximately 13.8 billion years ago. However, the details of what happened in the first moments of the universe's existence remain speculative. Questions about what might have preceded the Big Bang, whether there was anything before it, or if the universe is the result of a cyclical process, are topics that intrigue both scientists and philosophers alike. These considerations touch upon the very nature of time and existence. The fate of the universe is yet another profound question that continues to puzzle cosmologists. Observations suggest that the expansion of the universe is accelerating, likely due to dark energy. But what does this mean for the long-term future? Will the universe continue to expand forever, leading to a cold and dark state? Or conversely, could it eventually collapse back into a singularity in a scenario often referred to as the Big Crunch? These possibilities inspire extensive speculation and research, as they could reshape our understanding of cosmic evolution. Lastly, the search for life beyond Earth encapsulates one of humanity's most enduring questions. While scientists have identified numerous exoplanets in habitable zones around distant stars, the evidence for life remains tantalizingly out of reach. Understanding whether life can exist elsewhere in the universe not only influences our view of cosmic reality, but also our understanding of life itself. The resolution of these questions would profoundly impact our conception of humanity's place in the vast universe, closing the gap between the microcosm of life on our planet and the grand tapestry of the cosmos. The process of scientific discovery acts as a powerful catalyst for the human sense of wonder. At its core, science seeks to understand the intricacies of the universe and the fundamental principles that govern our existence. Each breakthrough, whether it's uncovering the structure of DNA or exploring the vastness of space, adds another layer to the tapestry of our understanding. This perpetual unveiling of the mysteries around us instills a deep curiosity, prompting people to ask questions and seek answers. Discoveries often reveal the unexpected, igniting awe and expanding our perception of what is possible. For instance, consider how the detection of gravitational waves confirmed a century-old theory proposed by Albert Einstein. This realization not only validated previous scientific endeavors, but also opened new avenues for research and exploration. Each discovery can inspire future generations to look beyond what is known, encouraging an ongoing pursuit of knowledge that fuels creativity and innovation. Moreover, the stories behind these discoveries are as compelling as the findings themselves. They often involve bold ideas, rigorous experimentation, and sometimes even spectacular failures. Scientists share their insights and experiences, creating a narrative that resonates with people. This human element of dreaming, exploring, and persevering connects us to science on a personal level, nurturing a sense of wonder about the universe and our place within it. Ultimately, the process of scientific discovery invites us to ponder profound questions about life, the cosmos, and our origins. It encourages reflections on our humanity, our challenges, and our aspirations. By fostering a sense of curiosity and exploration, science not only answers questions but also inspires new ones, reminding us that the universe is a vast, wondrous place, waiting for us to discover and understand. As we gaze into the vastness of the universe, we often find ourselves grappling with profound questions that stretch the limits of our understanding. Despite centuries of exploration and discovery, there exist facets of the universe that may forever elude our grasp. This possibility raises intriguing considerations about the nature of knowledge and the limits of human reason. One significant area of mystery lies in the realm of dark matter and dark energy. Together, they constitute about 95% of the universe's total mass energy content. While scientists are aware of their existence due to their gravitational effects, the intrinsic properties of dark matter and dark energy remain largely speculative. This unknown has led to numerous theories, but the fundamental nature of these components may always be beyond our complete understanding. Another aspect to ponder is the concept of infinity. The universe could be infinite in extent, meaning that it has no boundaries. If this proves true, it raises philosophical questions about the nature of space and time. How do we truly comprehend something boundless? Such concepts challenge the very fabric of human cognition. which is often constrained by tangible experiences. Furthermore, there are aspects of time that may defy our comprehension. While we experience time linearly, the true nature of time could be far more complex. Some theories in physics, such as the idea of time as a dimension similar to space, suggest that our linear perception may not capture the full reality. As science continues to evolve, it pushes the boundaries of what we can understand, leaving some enigmas unresolved. These mysteries remind us that the universe, while increasingly revealed through science, retains depths that may never be fully fathomed. Scientists continually strive to expand our understanding of the universe, often in the face of limitations imposed by current technology. To cope with these challenges, they employ several innovative strategies, combining creativity with collaborative efforts across disciplines. One major approach is the development of new observational techniques. By enhancing existing instruments or designing entirely new ones, researchers can gather more detailed data about celestial objects and phenomena. For instance, advancements in telescope technology have enabled astronomers to observe distant galaxies with unprecedented clarity. Another key strategy involves leveraging existing technology to its fullest potential. Researchers analyze data from multiple sources, such as space telescopes and ground-based observatories, combining information to create a more comprehensive picture of cosmic events. This integrative approach allows scientists to overcome the physical limitations of single instruments. By using sophisticated algorithms and computer simulations, they can model phenomena that are difficult to observe directly, such as black holes or the formation of stars. Collaboration also plays a pivotal role in bridging technological gaps. Scientists around the world share their findings and work together on large-scale projects, pooling resources and expertise. Initiatives like the Event Horizon Telescope, which captured the first image of a black hole, demonstrate how collaboration can lead to groundbreaking discoveries, even when individual technologies may have limitations. By building international partnerships, researchers can tackle more ambitious questions and push the boundaries of what we can know. Finally, education and public engagement enhance this effort. By fostering interest in science and technology, future generations can develop new tools and techniques that will help unlock the secrets of the universe. Through outreach programs and collaborative research opportunities, scientists are not only tackling current limitations, but also inspiring a continual cycle of innovation, ensuring that our understanding of the cosmos will keep expanding well into the future. Humility plays a crucial role in scientific investigation. At its core, science is about constantly seeking knowledge, understanding the universe, and recognizing that our current answers may not be definitive. Scientists must remain open to new ideas, even when they challenge long-held beliefs. This trait allows for the necessary flexibility to adapt to new evidence and theories, which is essential in a field where information is always evolving. When researchers display humility, they acknowledge the limits of their own understanding. They recognize that no matter how many experiments they conduct or theories they propose, there is always room for improvement and further inquiry. This mindset fosters collaboration and encourages the sharing of ideas among scientists. When researchers work together, combining their expertise and knowledge, they can tackle complex problems more effectively and arrive at deeper insights. Furthermore, humility in science helps guard against cognitive biases that can hinder discovery. Scientists must challenge their own assumptions and preconceptions, as these can cloud judgment and inhibit innovation. By accepting that they might be wrong or that their interpretations may need revision, scientists create a culture of skepticism and critical thinking. This environment is essential for scientific progress, as it leads to rigorous testing of ideas and hypotheses. Ultimately, humility enhances the integrity of scientific investigation. It encourages transparency when reporting results, whether they confirm or contradict existing theories. This accountability is vital for the reliability of science, as it fosters trust within the scientific community and with the public. In a world where science can impact policy and daily life, maintaining this trust ensures that science remains a credible source of knowledge. Sustaining public interest in space and science presents a multifaceted challenge, particularly given the complexities involved in these subjects. Yet, the wonder of the cosmos and our quest for understanding can captivate audiences from all walks of life. Two crucial elements emerge in fostering sustained engagement. education, and storytelling. By providing compelling narratives around scientific discoveries, such as the unfolding mysteries of black holes or the astonishing details of distant galaxies, we can illuminate the significance of space research beyond the confines of the laboratory. One effective approach to maintain this interest is through educational initiatives that reach diverse populations. Schools, museums, and public lectures can create environments where curiosity is encouraged. Citizen science programs also play a vital role. By involving everyday people in actual scientific research, be it classifying galaxies or monitoring local star patterns, we empower individuals to feel a personal connection to the scientific community. This equips them with the knowledge to understand complex topics while promoting a sense of ownership in the ongoing exploration of the universe. Moreover, media plays a crucial role in shaping the public's perception of science. Documentaries, podcasts, and even social media platforms disseminate new discoveries and ongoing research in engaging ways. Visual storytelling, featuring stunning imagery captured by telescopes or footage from space missions, ignites the imagination. Informative yet entertaining content can transform daunting scientific concepts into relatable ideas, making the vastness of space feel accessible and inviting. Finally, collaboration between scientists and communicators is essential. When researchers take the time to explain their work in clear, inspiring terms, they bridge the gap between complex science and public understanding. Events like World Space Days, stargazing nights, and interactive exhibits can keep the momentum going. By cultivating a vibrant dialogue around space exploration, we can ensure that the public remains not just informed, but excited about the universe and our ever-evolving place within it. Imagination and creativity are vital forces in the scientific exploration of the cosmos. While rigorous observations and experiments form the backbone of scientific inquiry, it is often the imaginative vision of scientists that allows them to ask profound questions and propose innovative theories. Every time a researcher glances at the stars, they are not merely counting celestial bodies. They are dreaming of the possibilities that lie beyond what is currently understood. Take, for instance, the way scientists conceptualize black holes. The notion itself is born from creative thought, crafting a way to visualize regions of space where gravity pulls so strongly that nothing, not even light, can escape. Without the power of imagination, such theoretical constructs might never have taken shape. They inform and guide mathematical modeling, helping to provide a framework within which scientists can explore the universe, leading to groundbreaking insights about the fabric of space and time. Moreover, creativity plays a central role in developing new technologies and methodologies used in cosmic exploration. Consider the evolution of telescopes. They started as simple lenses but have transformed into colossal structures that can observe light from billions of years ago. This leap did not just result from optimizing existing tools, it originated from an imaginative leap, envisioning what could be rather than merely improving what exists. Scientists and engineers alike harness their creative instincts to push boundaries, allowing us to see farther and deeper into the universe. Finally, imagination fuels the stories we tell about our place in the cosmos. From ancient myths that inspired early astronomers to modern narratives around space exploration missions, these stories not only captivate our hearts and minds, but also inspire future generations to look at the sky with wonder. In the vast and complex realm of cosmology, imagination creates a bridge between what is known and what is yet to be discovered, nurturing an eternal curiosity that propels humanity forward into the mysteries of the cosmos. The multiverse theory suggests that our universe is just one of a potentially infinite collection of universes, all existing simultaneously. Each of these universes may operate under different physical laws and constants, creating an extraordinary tapestry of realities. The concept arises from a variety of scientific theories, including those stemming from quantum mechanics, string theory, and cosmological inflation, which propose mechanisms through which other universes could exist alongside our own. One of the most fascinating aspects of the multiverse theory comes from the way our universe appears to have been finely tuned for life. Certain constants, such as the strength of gravity or the charge of an electron, seem perfectly balanced to allow stars and planets to form. If any of these constants were just slightly different, life as we know it could not exist. The multiverse theory offers a potential explanation for this fine-tuning. If there are countless universes, each with varying constants, it becomes more likely that at least one would be suitable for life, including our own. Support for the multiverse theory is more indirect than direct. For instance, the cosmic microwave background radiation, a remnant of the Big Bang, shows subtle fluctuations that some scientists suggest could be the result of interactions with other universes. Additionally, the mathematical framework of string theory leads to various solutions that include multiple dimensions and, inevitably, multiple universes. Yet proving the existence of these alternate realities remains a substantial challenge, as direct observation of other universes is fundamentally out of reach with our current technological capabilities. Despite the elusive evidence, the multiverse theory continues to fuel discussions in cosmology and beyond. It raises profound questions about the nature of reality and our place within it, inviting us to ponder the possibilities that lie beyond the stars we see. It captures the imagination, suggesting that the universe we inhabit may merely be one chapter in a much larger cosmic story. The concept of parallel universes often stirs the imagination, suggesting the existence of alternate realities where choices lead to different outcomes. In popular culture, this idea is somewhat vague, capturing the curiosity about what could have been in our own lives. However, when we delve deeper into the realm of physics, particularly through the lens of quantum mechanics, we encounter a more structured interpretation known as the many worlds interpretation. The many worlds interpretation proposes that every quantum event branches into multiple possibilities, leading to the creation of distinct, coexisting universes. For example, when a particle can spin in two different directions, the universe splits, allowing each outcome to occur in its own separate reality. This means that every decision we make, every event that unfolds, spawns a new universe where alternate outcomes play out. It creates an intricate web of realities, all existing in a broader multiverse. In contrast, the broader notion of parallel universes can encompass various models and theories. These might include universes with different physical laws, dimensions beyond our perception, or entirely different forms of matter and energy. Some of these universes may not even interact with our own, unlike the interconnected outcomes proposed by the many worlds interpretation. This distinction highlights that while parallel universes may cover a range of possibilities, the many worlds interpretation remains a specific framework within the quantum mechanical understanding of reality. Ultimately, both ideas invite us to rethink our understanding of existence and the nature of reality. The many worlds interpretation offers a fascinating perspective on the branching possibilities of quantum outcomes, while the broader concept of parallel universes taps into a rich tapestry of hypothetical worlds yet to be explored. This interplay between the known and the unknown continues to challenge our perceptions of the cosmos and potentially our place within it. The concept of parallel universes has fascinated scientists and philosophers alike, igniting discussions that stretch beyond the boundaries of our known reality. Scientifically, theories about parallel universes often stem from quantum mechanics, which posits that every decision we make can lead to branching paths of reality, creating a multitude of outcomes across different universes. This idea suggests that there may be infinite variations of ourselves and our experiences coexisting in different realms. From a scientific standpoint, the multiverse theory extends not only from quantum mechanics but also from cosmic inflation. This theory posits that after the Big Bang, our universe underwent rapid expansion, potentially giving rise to other bubble universes, each with its own distinct physical laws and constants. The notion that there's a near infinite number of universes prompts us to reconsider our place in the cosmos and the fundamental nature of existence itself. If these universes are real, it might mean that everything we experience could be just one of countless possibilities. Philosophically, the implications are equally profound. The existence of parallel universes challenges our understanding of identity and individuality. If every choice creates a new reality, what does that mean for our notion of self? Are we defined solely by our experiences in this universe, or do alternate versions of ourselves exist in those other realms? Such questions not only delve into the nature of consciousness, but also touch on ideas of fate and free will. Additionally, the implications of parallel universes inspire deep metaphysical questions about morality and consequence. If every possible outcome of our decisions exists somewhere, how does that shape our moral landscape? Do we hold the same accountability for our actions if alternative versions of ourselves are leading different lives? As we examine the scientific theories and philosophical questions surrounding parallel universes, we find ourselves at the intersection of knowledge and wonder, confronting the vast complexities of existence and reality. String theory and quantum mechanics together play a significant role in the intriguing concept of a multiverse, a realm where multiple universes exist beyond our own. At its core, string theory proposes that the building blocks of matter are not point-like particles, but rather tiny vibrating strings. These strings can exist in numerous configurations, which allows for different particles to emerge based on their vibrational states. This idea challenges traditional views of physics and opens the door to the possibility of countless alternative realities. On the other hand, quantum mechanics introduces an inherent randomness to the universe at the smallest scales. It suggests that particles do not have definite states until they are observed. The famous thought experiment known as Schrödinger's cat illustrates this concept, where a cat can be simultaneously alive and dead until someone opens the box to check. This ambiguity leads to interpretations suggesting that all possible outcomes of quantum events actually occur, branching off into different dimensions or universes, creating a multiverse where every potential reality coexists. When string theory is coupled with quantum mechanics, these two frameworks enhance one another. String theory, with its various dimensions beyond the familiar four, proposes that our universe could be just one of many possible configurations in a larger space. Each universe within this multiverse could have its own distinct physical laws and constants, depending on how the strings vibrate in that particular corner of the cosmos. This fascinating interplay invites us to rethink the nature of reality. Instead of a single universe, we might envision an endless tapestry of universes, each a reflection of different possibilities shaped by the intricate dance between strings and quantum states. As scientists delve deeper into string theory and quantum mechanics, the notion of the multiverse expands, sparking curiosity and profound questions about our place in the cosmos and the fabric of reality itself. The idea of parallel universes, or multiple realities coexisting alongside our own, fundamentally challenges and expands our understanding of existence. In traditional views, we often consider our universe as the only one, governed by specific physical laws and constants. However, the notion of parallel universes suggests that there could be countless other realities, each potentially having different laws of physics, histories, and even forms of life. This concept can stimulate profound questions about identity and choice. For example, if every decision we make spawns a new universe where the alternative choice was taken, what does that say about free will? It implies that our lives unfold within a vast tapestry of outcomes, where every possibility is realized somewhere. This can foster a sense of complexity and wonder, but also a sense of uncertainty about our roles in the grand scheme of things. Furthermore, the existence of parallel universes could reshape our understanding of fundamental scientific principles. If other universes operate with different constants, it might explain why our universe has its specific set of rules. This could lead to advances in fields like quantum mechanics, suggesting that particles exist in multiple states at once due to interactions with alternate realities. Within this framework, the very nature of reality becomes more intricate and multifaceted than we ever imagined. As we delve deeper into these theories, we not only explore the limits of our scientific knowledge, but also the philosophical implications of our own existence. Understanding parallel universes can provoke intriguing thoughts about what it means to be human in a potentially infinite multiverse, inviting us to ponder our place within this vast cosmic expanse. Such inquiries remind us that reality may be far more mysterious and expansive than we have ever known. The concept of time travel has fascinated humanity for centuries, and various theoretical models in physics propose intriguing possibilities that make it a topic of serious scientific discussion. At the core of these ideas is the theory of relativity, developed by Albert Einstein. According to this framework, time is not a fixed entity. Instead, it is intertwined with space to form what we call spacetime. This means that the passage of time can vary depending on speed and gravitational influence. Essentially, the faster an object moves, or the stronger the gravitational field it experiences, the more it affects its perception of time. One of the most discussed concepts regarding time travel involves what are known as wormholes. These hypothetical tunnels in space-time could create shortcuts between distant points in the universe. If such structures exist and could be stabilized, the theory suggests that a traveler could theoretically enter one end of a wormhole and emerge at a different point in time and space. While wormholes remain speculative, their examination opens discussions about the nature of time and whether it can be traversed in non-linear ways. Another fascinating area of exploration is the idea of closed time-like curves, routes through space-time that loop back on themselves. This concept arises in solutions to Einstein's field equations and suggests the possibility of returning to an earlier point in time. However, these scenarios often lead to paradoxes, most famously illustrated by the grandfather paradox, where a time traveler could potentially prevent their own existence. Such contradictions highlight the complexities and challenges intrinsic to time travel, making it a topic of both theoretical appeal and philosophical inquiry. Moreover, physicists also consider the implications of quantum mechanics in the context of time travel. Some quantum theories suggest that parallel universes or alternate timelines could emerge from decisions made in the past. This idea raises questions about the nature of reality and the multiverse, thereby expanding our understanding of potential time travel mechanisms. While practical time travel remains firmly in the realm of science fiction, these theoretical frameworks provoke thought and spark the imagination about the fundamental structure of our universe and the mysterious nature of time itself. Time travel has captured the imaginations of scientists, philosophers, and the public alike, but it is rife with paradoxes and challenges that make it a complex topic. One of the most famous paradoxes is the grandfather paradox. Imagine a time traveler goes back in time and inadvertently prevents their grandfather from meeting their grandmother. If that happens, the time traveler would never have been born, creating a logical inconsistency. This paradox raises fundamental questions about causality and the nature of time itself. Another intriguing challenge is the concept of closed time-like curves, which arise from solutions to Einstein's equations of general relativity. These curves suggest that it may be theoretically possible to return to a previous point in time. However, the very nature of these curves introduces complications. For instance, if a person traveled back to alter a historical event, it raises the question of whether they could actually change anything without creating contradictions, or if their actions were always part of the timeline, thereby preventing change altogether. In addition, theories of time travel often require conditions or materials that are not currently known or observable in our universe. Concepts like negative energy, wormholes, or exotic matter remain speculative and present their own challenges in terms of feasibility. Understanding the laws of physics as we know them raises more questions than answers about the practical implementation of time travel. Can the universe permit such phenomena, or are they mere flights of fancy born from human imagination? Finally, there's the philosophical dimension to consider. If time travel were possible, it could profoundly alter our understanding of history and personal identity. Philosophers debate whether a time traveler would be the same person after experiencing different timelines, or how multiple versions of individuals existing at once would affect our perceptions of reality. These challenges create a fascinating tapestry of inquiry that continues to engage thinkers in both scientific and philosophical realms. Time travel has captured the imagination of audiences in modern science fiction in remarkable ways, manifesting in films, television shows, and literature. From the iconic DeLorean in Back to the Future to the intricate time loops of Looper and even the complex narrative of Doctor Who, these stories present a fascinating array of interpretations of time travel. Each depiction often explores the implications of altering the past or the future, raising thought-provoking questions about fate, agency, and the nature of time itself. These narratives often serve as a mirror reflecting our societal hopes and fears. For instance, the ability to change one's past can evoke a sense of nostalgia or regret, as characters often grapple with decisions that could shape their futures. In many cases, these stories highlight moral dilemmas, suggesting that meddling with time could have unintended consequences. This allows audiences to engage with the concept of personal responsibility. What would you change if given the chance? and what is the true cost of such alterations. Modern science fiction also introduces concepts like multiverses and alternate realities, expanding our understanding of time beyond linear progression. The Netflix series The Umbrella Academy, for example, intertwines time travel with themes of family and personal growth, illustrating how these journeys influence relationships and destiny in profound ways. Such discussions invite viewers to ponder about the fabric of reality, suggesting that time may not be as straightforward as we perceive. Ultimately, these imaginative portrayals of time travel do more than entertain. They provoke deep philosophical questions. Could time travel be a mechanism for exploration, or is it fraught with peril? Through science fiction narratives, we confront the limits of human understanding about time, gaining insight into our own lives and choices. This genre does not just seek to depict travel through time. It invites us to consider how the concept of time shapes our very existence. The concept of time travel captures the imagination and has been a popular theme in science fiction for decades. But what if we take a moment to explore some of the scientific theories and technologies that could, in theory, make time travel possible? While it remains firmly in the realm of speculation, advancements in physics give us a glimpse into how time travel might one day be feasible. One of the fascinating theories comes from Albert Einstein's theory of relativity. According to this groundbreaking work, as an object approaches the speed of light, time begins to slow down relative to an outside observer. This effect, known as time dilation, suggests that if a spaceship could travel incredibly fast, astronauts aboard would age more slowly than people on Earth. While this has been demonstrated with particles in scientific experiments, it poses significant engineering challenges for future spacecraft and travel. Another compelling concept involves the warping of space and time through wormholes. These hypothetical passages through the fabric of space-time could connect distant points in our universe or even link different times. Though theoretically proposed by physicists, producing and stabilizing a wormhole presents daunting obstacles. Creating a wormhole would require vast amounts of exotic matter with negative energy density, which has not yet been discovered. Finally, let's consider the intriguing idea of closed time-like curves. These are paths in space-time that loop back on themselves, potentially allowing travel to the past. While mathematically plausible, the implications of such travel, like the famous grandfather paradox, pose significant philosophical and scientific dilemmas. Scientists continue to explore these ideas, expanding our understanding of the universe and the enigmatic nature of time. It's a fascinating journey that reveals the complexities of time itself and the tantalizing possibility that one day time travel might cross from speculation to reality. The concept of time travel has fascinated both scientists and storytellers for generations. If we could ever find a way to travel through time, it would fundamentally shift our understanding of not just time itself, but also the very nature of history. Traditionally, we regard time as a one-way stream, a linear progression where events are experienced in a specific order, past, present, and future. However, the ability to move through this stream could introduce complex questions about causality and the fabric of time. Imagine being able to visit key historical moments. It could enhance our grasp of significant events, but at the same time it would raise questions about the integrity of history. Would witnessing a pivotal moment change our perception of it? Moreover, if we could alter past events, this could unleash unpredictable consequences, leading to a so-called butterfly effect, where small changes lead to drastic alterations in the present. This notion challenges the understanding of determinism in our universe and suggests that history is not as fixed as we perceive it. Time travel could also lead to the exploration of alternate timelines or parallel universes, where different decisions yield different outcomes. This idea could push the boundaries of what we consider reality, presenting a multiverse of historical paths. It not only invites philosophical debate about fate and free will, but implies that history itself might be more malleable than we think, shaped by the decisions we have yet to make or the paths we have yet to consider. Ultimately, if time travel were ever achieved, it would require a radical re-evaluation of our perspective on time as a constant sequence of events. Our understanding of time would no longer be merely about measuring minutes, hours, or even centuries. Instead, it could become a rich tapestry of experiences, where consequences ripple through existence. and the past is not a solitary narrative, but an intricate web of possibilities waiting to be explored.